Check 1 2 3 4 5. Yeah, it's always for me for the closed captioning. It's kind of like a double test. Oh, that's right. Yeah. Yeah, I noticed that's kind of cool. Yeah, because you don't want to put it on the Zoom because it screws up stuff, doesn't it? Oh, that's okay. Everybody's watching on YouTube. That's right. Yeah. Check. Yep, there it is.
Andrew, good morning. Do you want to check your audio? Go ahead, try that again, would you, Andrew?
Hey, are people there?
Yeah, keep talking for me, would you, please? Andrew, can you hear me all right? Andrew, can you hear me? Andrew, can you hear me?
Yes, I can.
Great. Can you talk for a little bit? I want to make sure I got a good audio from you, please.
Sure. Okay. Yeah. So I got your note asking if I could hear you, and I couldn't because my speakers were not turned on.
Oh, no problem. Good. Okay, we're good now. Okay, good. Yeah, I can hear you fine. Great. Thanks.
Okay, perfect. Can you see
Yep.
my PowerPoint? Yeah. Okay.
Yep. Everything's great. Thank you.
Awesome.
You just kind of press and hold. Yeah. It's either on or off.
Good morning, Andrew. Can you hear me?
Yes, I can. Can you hear me?
Yes. I guess I can see that you saw the chat. So we'll get started here really soon, in a few minutes. But yeah, I just want to let you know, I'll send you a quick reminder when we have about 5 minutes left. The talk is scheduled for, let me get my schedule out really quick.
Yeah.
So from 9 to 9:40. So you have about 40 minutes, but I'll give you maybe about last 5 minutes, and then we can have some questions.
Yeah, that sounds good.
Okay, wonderful. So we'll get started here maybe 5 minutes.
Oi, Andrew.
Was that Sabre?
Yeah, we were hoping to see you here.
Yeah, I'm sorry. I've been swamped and I was on travel for the past 2 weeks and we've got the all hands and I just decided that I needed to actually spend some time at home. So
Yeah, so probably we'll see you next week. So
absolutely. Yep. Next week. And yeah, and you won't be able to make it to the algorithms workshop.
no, yeah, but
Not-
the man is okay.
Yeah.
Great.
Excellent.
Okay. I think we'll get started here. So good morning. Welcome to the Quantum Science Center's, to day 3 of the Quantum Science Center's 4th annual Quantum Summer School. My name is Colton Fruling. I'll be the moderator for this morning session. For this morning session. I guess I will first introduce our first speaker. His name is Andrew Sornberger. Andrew is a multifaceted research scientist and a thought leader in the areas of neuroscience, statistical data analysis, and quantum computing, with a passion for helping organizations move beyond the present, obvious, and known. Dr. Sornberger is a quantum algorithms and simulation lead at the Quantum Science Center in Los Alamos National Lab. Take it away.
Thank you very much. So I'll be talking today about, about some work that we've done over the past, 5 or 6 years in quantum machine learning and with a specific focus on what's called quantum compiling, and I'll describe what that is. and then I'll also talk about some ways that you can use it. And the reason that I'm kind of talking about this is to give you an idea of what the things are that are different about machine learning in the quantum context relative to the classical context. And so there are a few things that I'll talk about. So the title's learnable and unlearnable in quantum machine learning. So first, I'll talk about this very cool result that you can trade, kind of input-output pairs that you might be training a machine learning algorithm with for entanglement. And so this is kind of a resource exchange that you can make that can give you an exponential improvement in the resources that you might want to use for machine learning. And then I'll talk about the difficulties with, or one of the main difficulties with quantum machine learning, and that is what's called barren plateaus. And then finally, I'll talk about generalization. I'll describe what that is, why it's important, and the fact that you can get some really beautiful generalization bounds for quantum machine learning. And then I'll conclude. I mean, it's not the last thing I'll talk about will be a use case for quantum compiling in quantum simulation, and some recent extensions that we've made to continuous variable quantum compiling, which would be for systems that like photonic systems, which are continuous variable. So, okay, let me get started. So I'm going to be talking about quantum machine learning, and largely from the point of view of this talk, I'll be talking about what are called variational quantum algorithms. I'm sure you guys are familiar with these, but let me just, kind of recap what they are. The idea is that you have a problem of interest, maybe finding the ground state of some Hamiltonian, for instance. And so you construct a cost, and the cost is made so that if you optimize the cost function, it'll give you a solution to your problem. And typically it'll be an approximate solution. It might be good up to 10 to the minus 3, 10 to the minus 8, something like this. And the cost is computed on a quantum computer. And the idea with these algorithms is that you compute the cost on the quantum computer, but then you perform the optimization of the parameters going into the quantum circuit that you implement on the QC classically. And so it's called, these are called variational quantum algorithms, or sometimes called hybrid quantum classical optimization, something like this. But you get the idea that what you want to do is make it so that the hard thing to compute is computed on the quantum computer, and that's the cost. So the use case that I'm talking about is called quantum compilation, and this is the problem of finding an unknown unitary. And so the idea is that somebody gives you a unitary. In this case, I'm using V to represent that unitary. And then you have a parameterized unitary U. And you'd like to, change the parameters in U via some optimization method and make it match V. And so you can see here that if U really were equal to V, I'd have V here, I have V dagger here. And so V dagger would annihilate each other. And what I put in, it would be what I would get out. And so so that's the basic problem of quantum compiling is finding this U to match V by varying the parameters theta. And so there are a lot of ways to do it. You can do it this way. You input a state, you output a state. But the thing to notice here is that here I put as an example, all zeros. And so I should measure the all zero state on the output. But that only tells me about one particular direction in the Hilbert space that's represented by V. And so I also need to test this on all of the possible input vectors that are input states and test that I get all of those states out faithfully when once I've done this optimization correctly. And so that's a problem. That means that I need an exponential number of input and output states in order to learn this unitary. And so that's costly, right? So I mean, one of the benefits of using a quantum computer is you have this huge Hilbert space to play with. And then one of the downsides of this particular implementation of quantum compilation is that, you have to explore that entire Hilbert space. And so that's not so good. So it turns out that you can do something else, which will, like I said earlier, you can trade entanglement for training states. And so this circuit here is what we call the Hilbert-Schmidt test circuit. And it computes something called the Hilbert-Schmidt inner product between two matrices. And so let me talk a little bit about how this works and the fact that you can trade this entanglement here. So notice the structure here is that I have a register, the A register of input. I have the B register, which is simply ancillas, and they would normally be initialized as zeros. But it's these ancillas that become entangled with the A register, and that's the entanglement that I'm talking about that can give you an advantage. So let's just try and understand a little bit why this circuit computes the Hilbert-Schmidt inner product and how it does it. So let's just simplify this down. So we're going to take the A register and we're just going to make it into a single qubit. And we'll take the B register and also make that into a single qubit. And then each of these H's followed by a C naught, we'll put that in. And then we have U, which now is also just going to be on that first register. And so remember, U is this parameterized unitary that we're trying to figure out what the parameters should be so that it'll match V dagger. So if you just do out the calculation for what this small circuit does, I've written it out here just kind of from the linear algebra point of view, and then down here I've written it out from the conventional kind of notation that people use for quantum computing. And if you do this multiplication, if the input is the 0, state, what comes out is what's called a Choi state. Okay, so this little circuit implements what's called the Choi-Jamiokowski isomorphism. And what it does is it takes the elements of U, and in this case, it's just a single qubit, so there'll be 4 elements, U11, U12, and so forth. And it encodes them in the coefficients of this output state. And so it's an isomorphism because it takes the elements from a matrix and puts them into a vector, but it does it as an isomorph in a one-to-one manner. Okay, so that's kind of interesting. We've got this Choi state. It's got all of these elements in it, and so that describes what's happening in the first half of this circuit. And then the question is why is it doing what I claimed that it would do, which is to compute this Hilbert-Schmidt inner product? And the reason it can do that is you can see once you add in the second part of this circuit, which just gives you the adjoint choice state. And so if I take a choice state and then follow that by the adjoint, it gives me an inner product. And that inner product consists of is effectively equivalent, so analytically or mathematically equivalent to taking the trace of the full matrix U times the full matrix V dagger. And that is the Hilbert-Schmidt inner product. In other words, the inner product between these two matrices. And so that means that if the whole matrix U matches the whole matrix V, if I put in zeros on the left, so zeros for the input and the ancilla, and I get zeros out on the right, that not just the zero state matches with the zero state, but every single element in U is going to match every single element in V. So what I've done is I've traded this large number, exponential number of inputs and outputs that I need for this circuit in order to, I've traded that for entanglement in terms of these ancillas, and I get this nice result that I can compute the entire Hilbert-Schmidt inner product with this circuit here. So, so again, I've been able to trade either an exponentially large number of input-output pairs for a single register of n ancillas, where n's the size of the register, entangled with the n input qubits. And so that's that's an exponential reduction in the, or a logarithmic reduction in the resources that you need in order to train this circuit, or in order to train the unitary. So we, once we got the circuit, we tested it. We tested it in simulation and also experimentally. So here you can see if I take, so it's possible, I haven't gone into the details, but it's possible kind of one by one to remove these ancillas. And then, so if I have no ancillas, my circuit here is essentially the same as my original circuit, where I have to run every input state through U and V to get every output state. And so this yellow or gold set of points is showing the risk of using a particular number of input-output pairs, and the risk will go to zero if I am able to learn the entire unitary. And so you can see that I can't do very well if I use one training pair. If I use a few, I do better, but I have to use all 64 input-output pairs in order to learn the entire unitary. Whereas if I add just one ancilla, I can have that. And if I add another, I have it again, and so forth, all the way down to just needing, for the full ancilla register, one input-output pair. And so this was a while ago that this was published, but we tested this on one of the early Rigetti systems, just in the single qubit case. So basically the exact this exact circuit here. And you can see that, again, in gold is where I have no ancillas, and you can see that I need two input-output states to learn that unitary, but I need only one once I bring in the entangling ancilla. Okay, so this was a big success. We were very pleased with this. With a relatively simple circuit and some entanglement, we could basically get rid of the problem of having to generate all of these input and output states and just trade them for entanglement. And so that's what I think of as a success for quantum machine learning. And now I'm going to turn to some difficulties with quantum machine learning. And they're called barren plateaus. And they're going to show up actually in this circuit. So a barren plateau, it's a concept that shows up in classical machine learning, as well as quantum machine learning. In classical machine learning, it's called a vanishing gradient. And what as the name kind of implies, the idea is that what you would like, if you want to do some optimization, is you'd like it to be very obvious that you can, which direction to go in order to reduce your cost. And that, for instance, in this landscape is straightforward. In this landscape, not so much. It's a flat landscape, and it's difficult to figure out where to go in order to minimize your cost. So small gradients equals the fact that you need high precision in order to figure out what minimization direction to go in. And so that's very resource intensive. The number of shots that you need is high, and if your gradient gets exponentially small, then the number of shots that you need to measure is exponentially large. And so how do you translate that into figuring out whether something is trainable or not trainable? The easiest, or the way to do it is to take the derivative of your cost with respect to the parameters. So these will be what we call cost gradients. And for a barren plateau, the cost gradients vanish. And excuse me. And from Chebyshev's inequality, you can show that that you can bound the cost gradient with the variance, or this function of the variance of the cost gradient. So here, a small variance of the cost gradient means you've got a small cost gradient, because the small variance gives you the bound. And so just briefly said, if, for instance, like I said, if you find that this variance is going down exponentially, then the probability of getting a non-zero gradient vanishes also exponentially with the problem size. And so that's where you get this huge resource requirement in order to minimize your cost. And so these barren plateaus were initially discovered by Jared McLean and others at Google in this paper. This was kind of the first discovery of barren plateaus, at least from the quantum context. And then people have investigated a number of situations where they can show up. They can show up because you have too many parameters in your ansatz, in this quantum circuit that you're trying to optimize. You can have too much entanglement, and it can also have to do with the choice of your cost function. And in particular, we showed that if you have a global cost, meaning you have to measure everything coming out of the cost, all of the qubits coming out of the cost, then that can lead to barren plateaus. So this is an example of a global cost. You have some ansatz, it's got parameters in it and so forth, and you would like to put some input state in. For instance, in the Hilbert-Schmidt test circuit that I showed, we had the initial state of the inputs and the ancillas. And then on the far side, you measure everything. And if you get, so for instance, if I put in all zeros here and I got all zeros here, I would be guaranteed that I'd found the U of theta, which matched V. The problem is that this cost has a barren plateau, and it has a barren plateau at all depths. So it's extremely difficult to find minima, even though you can, just by adding these ancillas, you only need one input-output pair to train it. So the thing another thing that was discovered was that, however, if you use a local cost, which is a cost that's just measured on a kind of small polynomial number, or actually not even that, on a fixed number of qubits, then that cost can be reduced. It can be that cost can avoid barren plateaus. And so here you can see, for order log depth circuits, you can avoid barren plateaus completely. For a little bit larger, you can ameliorate them. But then, of course, at some point, depending on the depth of the circuit, you run into a barren plateau. So the protocol now for computing the Hilbert-Schmidt test, which we studied by looking at this circuit, actually you have to find a local cost that will perform the same calculation. And we were able to do that with this quantum circuit, which is called the local Hilbert-Schmidt test circuit. And you can see here we just measure a pair of outputs. And in fact, the full cost is the sum of the different paired outputs on the different qubits. And so to a certain extent, at least for moderate depth circuits U, which have, U being U of theta, this still will work. And so we can still make use of this training pair for entanglement trade-off. Okay, so at this point, I've kind of covered this this concept of being able to exchange entanglement for training pairs, input-output pairs in a variational quantum algorithm in a quantum machine learning context. And then I showed that you actually have to be a little bit careful because you run into these problems with barren plateaus. So here I'm going to move on to talk about the fact that whether you can solve a problem or the problem, the ability to learn a unitary that would solve a certain problem can depend on the target problem that you're interested in. And so I'm going to talk next about a physical situation which looked like we would be able to use this Hilbert-Schmidt test type approach to learning it, and I'll show you how it turns out that you can't do that. And so this is now, so the cost function here can depend on or the cost function that you have to write down in order to solve a particular problem can be the thing that determines whether you have barren plateaus or not. So here's this cool problem. It's called the Hayden-Preskill thought experiment, and it comes. So I have a background in cosmology, and this problem comes from the black hole literature, the quantum black hole literature. And the idea is you have a black hole. It's described by a unitary. Alice she wants to destroy her diary, so she throws it into the black hole. And the question is can Bob recover it. We're going to assume that Bob has, you know, some futuristic quantum computer, and he can send in input-output pairs and you know, investigate the black hole U. So, okay, so this thought experiment actually was put forth because of questions in terms in black hole information, and you know, the fact that people think that black holes, you know, they radiate information. It's pretty thermal, you know, and the question is, how the hell could you get that information back out? But the fact is if it's a quantum black hole and it's described by a unitary, excuse me, then by doing measurements on that unitary in a similar way that we've been using quantum machine learning, if you can learn the unitary, then you can invert it, and then you can reproduce the information in the dictionary that Alice had tried to destroy. So the question, how can you learn that unitary? And you know, that's what I've been talking about. You could learn it using quantum compiling. However, due to barren plateaus, it turns out that there's no way that you would actually be able to implement that learning. So this particular target problem in the Hayden-Preskill thought experiment, which sounds like a good idea, actually won't work, because you would have to know already the black hole unitary U. Okay, so I'll give you a little bit of a background. I'm going to go through this relatively quickly, talking about I'll talk about scrambling unitaries, learning them, which we know a lot about already, and why barren plateaus would stop us from learning that. So there are a lot of, so scramblers are widely known in the quantum computing, quantum information, you know, high energy theory literature. And a scrambler is a unitary that rapidly spreads entanglement through some many-body quantum system. And they're, you know, very important for all of these different applications. And they are, they're usually diagnosed with what's called an out-of-time ordered correlator, which you guys don't need to know too much about. But the main thing that you do need to know is that a scrambler agrees with a random distribution up to the second moment. Okay, in other words, up to kind of the variance. In other words, you can model a scrambler with just a particular kind of random unitary that's called a Haar unitary. People usually call this a two design. And so let me just say that that's how people model this this unitary that's supposed to describe the black hole. And so if you go through this whole procedure for you know, determining, diagnosing whether there's a barren plateau, you find that for a typical scrambler, that the cost landscape is flat. In other words, the cost gradient vanishes exponentially with the size of the problem. And you can see this. This was an example. We took a scrambler and you know, computed this landscape, and the scrambler has a parameter in it. Here, I think they call it G. And what happens is it has exactly the barren plateau. It gives back a barren plateau in exactly the way you would expect. As you turn on the scrambling with the parameter G, if G is relatively small, we get this kind of valley, which is relatively easy to find. But then as I turn G up, I turn the scrambling up, I get a flatter and flatter side, and I get a very thin, what's called a narrow gorge in the middle. And as G gets larger and larger, this narrow gorge gets exponentially small in terms of its width. So, you know, you might think that because you're describing the quantum black hole as a unitary that you could learn it, but the problem that the information, the way the unitary acts on the information prevents you from being able to learn it using some sort of a quantum machine learning protocol. So it turns out that Alice was, you know, smarter than you might have thought to go and throw this into a black hole, because it's going to take an exponential amount of time for anyone to try and to learn it. So let's see. I have another 8 minutes or so. So I'm actually going to skip this generalization. So let me just say about generalization that when you try and solve a problem like our quantum compiling problem, here it's just written in a little bit different notation, but U here is the unitary that we're interested in finding. Sorry, I've switched notation. U is the target unitary, and V is the unitary that's parameterized that we're looking for. And what we would like to know in terms of if we train this unitary on some data is how well it's going to work on data that we haven't seen yet. And that's called the risk. But we don't know that, obviously, because we haven't seen the data yet. Well, all that we know is the training cost that we got. So how well we were able to learn given the N train input-output pairs that we learned on. This is what we have access to. And so we've been able to set bounds given the training cost on this risk. And so that's more or less what I wanted to discuss in this section. And furthermore, what we do is we set the bounds in the case where we have what's called out of distribution generalization. So in distribution generalization is when your training ensemble is the same as your testing ensemble. So this would make some sense if you're trying to, you want to know what you're going to test on. As long as you were training on things that look more or less like what you were going to test on, that makes some sense. Out of distribution generalization, where your training ensemble is not equal to your testing ensemble, is kind of like, what? Why would you do that? And this work, I was involved with Matthias Caro and Robert Huang, and they were the ones that first identified the fact that we might be able to ask this question for this quantum compiling and actually more general quantum machine learning. And so it seems a little bit insane, because it's like you're training on parrots and you'd like to classify cats. But there are some reasons why it might be possible in quantum computing. One is that we're trying to learn a unitary which acts linearly on a state, and so maybe that situation is a little bit simpler than some of the ways classical machine learning is done. But let me focus a little bit on why would this be useful. The reason is that often if you might need to test on data that in a quantum circuit might be very difficult to construct. So it might have a lot of entanglement, it might require deep circuits and so forth. So it would be beneficial to be able to learn on something that's easier to construct and then test on something that's harder to construct. And it turns out that it's possible. And the main thing the main takeaway is that you can actually test on random product states. So these are very straightforward to construct. They can be compared with a single layer of single qubit gates, as opposed to, anything you might want to test on, which could be more difficult to construct. And the bounds that we've been able to place look like this. We have a risk over the testing ensemble, and we can prove that it's less than just 2 times the cost that we measure from training plus this extra term. So N here is the number of training states, and T is the number of training parameters. And one thing to remember about these generalization bounds is it requires that first you be able to do the training. So we're assuming that we were able to do the training with these gates that realize these parameters. And so, okay, so this bound basically says that we can do well for product states, training product states, training with product states. We can do well for any test states that we might want to encounter. And so why might that be useful? The reason is that if you're trying to set up a quantum compilation problem, the input states that you might need to input to it will be very easy and not take up much depth and much computational power in your quantum circuit. And so I'm moving forward here a little bit. We've taken this fact and we've applied it for a variational quantum simulation method that we've done. That method is fairly simple. It consists of approximating a step in a trotterization by performing quantum machine learning with a particular form of ansatz. In other words, the ansatz that we do has a diagonal form where we have eigenvectors, a diagonal matrix of eigenvalues, and then the adjoint of the eigenvectors. And it turns out that if you've learned a single trotter step to be of this form, and just by changing the parameters by hand in the diagonal matrix, if I learned this on one step, I just put in n the number of total steps I want in my quantum simulation, and I can perform a long time quantum simulation by doing this. And the point of this algorithm, the generalization results, is that it makes it so that the input data that you need in order to do the training just involves one column of single qubit gates. Okay, so this works pretty well. This is our method here, the fidelity of our method, and this is the fidelity of a trotterization. And you can see that this goes, kind of down to effectively random relative quite quickly, whereas our simulation method works well. So you can actually, so an interesting use case for this sort of learning is to have your target unitary, or to conceive of your target unitary as actually being a real experimental quantum process, and then learning that process in a set of quantum gates in a well-controlled part of a quantum computer, and then you can take these gates and put them in your pocket and study them at your leisure on your favorite quantum computer without having to go back to the experiment. We're actually doing this. You can do this in continuous variable systems, and we're doing it in a photonic system, which is shown here, and we have some nice results showing that as you change the squeezing parameter, which is related to the entanglement, that we get these same similar results to what I showed for the black hole. And this can actually be a benefit in training. So, I'll put these slides, online, or the summer school people will do that. These are some of the papers of interest, and I'll stop there.
Let's thank our speaker. I think we have maybe time for one short question, if there's a short question from the audience. Yeah.
Oh, thank you, Andrew. Very nice talk. My question about the OTOC, and I mean, as you know, the OTOC was developed to go from classical to quantum and describe chaos by calculating the quantum Lyapunov exponent.
Mm-hmm.
Do you know how one can connect this to entanglement?
Yeah, so I think the reason that you can diagnose with an OTOC whether something's classical or quantum is because the OTOC, is a metric for entanglement. I'm not sure. I can't do the derivation on the fly, but yeah, I mean, effectively for that reason, that same reason is the reason that we could use it in order to diagnose the scrambling.
Thank you. Let's thank our speaker one more time. Do you want to use? Okay. While our next speaker gets set up, let me introduce. If I can find it. All right. Our next speaker is Professor Sabra Kais. Professor Kais received his bachelor's, master's, and PhD degrees at the Hebrew University of Jerusalem in 1983, 84, and 89. From 1989 to 1994, he was a research associate at Harvard University, Department of Chemistry. Currently, he's a distinguished professor at the Chemical Physics and Electrical and Computer Engineering at Purdue University. He also serves as the director of the Center of Quantum Technologies, an NSF-founded industry university cooperative research center. He's published over 260 papers in peer-reviewed journals, and today he's here to talk about chemical reactions and quantum computing. So let's welcome our speaker.
Good morning, everyone, and I want to start by thanking the organizer, Sasha, David, and all others involved in this fantastic workshop for the 4th year here at Purdue. And I'm going to talk about quantum algorithms and simulation for chemical reactions. But before doing that, just to mention that in our group, we're also developing quantum computing algorithms for both electronic structure calculations and open quantum dynamics. And in the open quantum dynamics, we simulate the quantum master equation on a quantum computer. And last summer school, I talked about quantum machine learning for complex chemical systems. And I thought to update you of our recent results before I go to the simulation of chemical reactions. So at the summer school of last year, I talked about our quantum machine learning algorithm based on the restricted Boltzmann machine. So what is restricted Boltzmann machine? It's a very, very simple machine learning platform. You have 2 layers, the visible and the hidden, and you have local fields on both on the visible and hidden, and you have the connectivity matrix omega ij between the 2. Restricted, there is no connection between nodes on the same layer, but you have the connectivity between the 2 layers. And there is here another phase, which we call it the phase node, will give us the phase of the wave function. So what is Boltzmann? We sample from the Boltzmann distribution, which is e to the minus energy. And this energy, if you look at the structure of this machine, is exactly the Ising type Hamiltonian. We have local field on the visible, local field on the hidden, and the connectivity. So the energy of this machine is the Ising type Hamiltonian. So the idea, we sample from this one and get the wave function as a function of all the parameters in the system. And you have many parameters, local field, connectivity, and with the phase. And then these parameters will be optimized to minimize the energy of the Hamiltonian. And our contribution, we developed a quantum computing circuit that can do this sampling and implement it on a quantum computer. And then we show early that this machine can be used to obtain simple potential energy surfaces for simple molecular systems and valence band for materials. And then we generalize it to both valence band and conduction band. Again, this was a simple calculation with unit cell, 2 different arrays. And the new results, we keep pushing this to machine learning based on restricted Boltzmann machine to more complex systems. And with my postdoc Manas and collaboration with Professor Alien from physics, we're trying to push one and do this restricted Boltzmann machine for chain of spin 1 system. And the idea was to recover the structure in the Haldane phase. And the results were published in Journal of Chemical Physics in 2022. So we were also successful to get a restricted Boltzmann machine to give us this complex phase. What happens? Oh. Another exciting result, we were looking at this material, and in a minute I'll explain how do we come up with this one. And we were looking at again, the electronic structure of this kind of materials. And it turns out this kind of materials has a very nice topological properties. And when I search the literature, it turns out organic chemists synthesize this material with different functional groups for over 20, 30 years. And when with my student, Rajan and Manas, they did the calculations, and it turns out that this material supports edge states and has a beautiful phase diagram. And this is the way to understand it. You can think about this one. What happens? So the way to understand this one, you look at the SSH model where you have 2 topological, 1 trivial and 1 topological phase, and you connect them together, and you get this material. So the exciting thing, when we start looking at the literature for this material, it turns out the chemist put together a patent back in 2010, showing that this material is useful for cathode for batteries. And now we have this edge state. We're trying to understand the conductive properties of this material and how this connected to the topological phases of this material. Another new results with this quantum machine learning. This is an ongoing collaboration with the group of Sasha and Vlad, and we have a joint PhD student. He just graduated last week. And the idea is to sample from quantum machine learning and use it for inverse engineering. And the idea, can you design materials with specific property? And the sampling was from a quantum, and the rest was classical machine learning. So now this was our updated results from quantum machine learning. And now I would like to move and talk about a simulation chemical reaction in a quantum computer. So I'll start with introduction about interference in chemical reaction and what is the role of interference in chemical reaction. And then I will talk about the algorithm and how do we simulate it on a quantum device. And again, the reaction that we simulated is the simplest reaction. It's like the hydrogen atom in atomic physics. We simulate the scattering of the hydrogen with H2, and this is a collinear simple reaction. You get HAB with HC. So this is a very simple reaction. It's like the hydrogen atom in atomic physics. And it's a benchmark calculation to show how one can do the scattering on a quantum device. And then I will talk about our future work and how do we generalize these results to more complex systems. So now when we talk about the quantum information quantum computing, we are taking into account or relying or using fundamental concepts in quantum mechanics like superposition, which give us the qubit, interference. And again, interference is the heart of quantum algorithms. And we selected 30 years of Shor algorithm for factoring. And the heart of Shor algorithm is interference. You encode your information in a superposition of large number of states. And the question is, can you design an algorithm that the constructive interference give you the answer? And in this case, the interference is giving the period of a function, that this function, from the period, you can calculate the 2 prime factors. So again, I would like to emphasize that the interference is the heart of quantum algorithms. And again, entanglement, which is a strong correlation with no classical analog, and in 2022, they got the Nobel Prize for the early experiment showing that entanglement is a true property of quantum mechanics. So I'm focusing on my talk only on the interference phenomena. So when we talk about interference, we go to the 2-slit experiment. And this 2-slit experiment already demonstrated experimentally for photons, electrons, neutrons, atoms, and recently even people did this kind of experiment with C60, large molecules as C60. So what is the idea? The idea, if you have 2, and I will show in a minute how this is related to the chemical reaction. So suppose you have 2 mechanisms, and one is 10 times the amplitude of this larger than this one. So again, if you just sum the amplitude here squared, you see the error is plus minus 1%. You square it and plus minus 1. But if I take the sum and then square it as we do in coherence, the effect is 20%. So the conclusion that here is just a small mixing will give us a big effect. And this was the argument in this paper by Dick Zaire at Stanford, where he looked at the quantum interference between H and D2. And he was comparing the exact semi-classical and experimental results. And when they look at the cross-section, they see oscillations. And the oscillation could not explain with the classical mechanics. So just to read the conclusion that from this paper, and I will show the results in a minute, the interferences are genuine phenomena that appear whenever 2 seemingly distinct classical trajectories lead to the same outcome. They were comparing how the classical simulations, people run classical simulation and see what is the cross-section. So they show in this paper, if you have 2 classical trajectories that they give you the same results, these are responsible for the interference in the cross-section. And then they run experiment and rigorous quantum calculation and classical trajectories to see the origin where this effect comes from. And then they follow this paper with a nice letter in Physics Today. And they looked at the diffraction cross-section as a function of scattering angle. And the red one is the classical calculations. The black one and the solid black is the full quantum calculations. And you see the experimental results. And this is the reaction from V0, vibrational and rotation 0, to 1, 1. And then they analyze the classical trajectories from their calculations. and they look at the deflection angle, a deflection function, which is a joint distribution with the total angular momentum as a scattering angle. And you can see clearly, like mechanism 1 and 4, they scatter with the same angles around 130. And you can see 3 and 2, the same is like around 170. So their conclusion from this paper that two distinct classical trajectory scatter with the same angle. And if you take the quantum calculation and look at this difference, you see the interference makes a difference between the classical and the quantum. Another beautiful experiment here done by Young-Chin in physics here at Purdue. And this was published in Physical Review Letter 2018. And you can see the title, Observing Quantum Interference and Coherences Control in Photochemical Reaction. And they were looking at rubidium with the laser. They excite the system and you form molecular system. The atomic system here, you form it or not depends on the initial configuration of the spin state. This was the experiment back in 2018. And you can see here they can manipulate the superposition with a magnetic field. And again, the idea is to look at this reaction from an interference point of view. So what they have done here, you can see this is the colliding atoms. And they thought about this experiment in analogy with the two-slit experiment. You have two pathways. And again, the goal is to go to come up with F equals 0 and M equals 0 in the molecular system. So you can get 0, 0 by scattering with 0, 0. These are the M sub F, or plus minus 1 or minus plus 1. So they explain this beautiful experiment by taking the interference between two pathways leading to the formation of this molecular system. So we'll not go to the details, but when they look at the theory for the rate of the reaction, when you include superposition and normalize it to the rate when you don't have superposition, so you can see these are coefficient in the wave function with the 0 and plus minus 1. Look at this term comes with the minus sign, which means that you will have a destructive interference in this case between the two paths. And when they run the experiment and look at the rate or normalized rate as a function of Raman coupling or detuning, and you see the experimental results here in red, and the theory, this is no interference, and this is destructive interference. So clearly the results show that you have a destructive interference between the two pathways in this chemical reaction. With my graduate student, Samit, we start thinking what the initial configuration should be to get constructive interference. In the experiment, they showed destructive interference. And in collaboration with the Young-Chin group, it turns out that if you take the total F to be 2, and you work out the rate for the superposition normalized by the power state in 0, you see that you change the sign from minus to plus, which means for this kind of reaction, you have constructive interference. And when you do the calculation, you see clearly that you enhance the rate of the reaction compared with the one that no interference. So this is the blue one with constructive interference. And again, this is the blue one with the constructive interference. So the message here that the constructive and destructive interference between the two pathways lead to the reaction, or you don't have a reaction based on the initial superposition. So this was the summary. You can get both. You change the sign by taking the different positions. So now the question is, can we repeat this kind of scheme for other degrees of freedom to control, for example, the rotational quantum numbers? And we have a discussion with Dick Zare a couple of years ago when he visited Purdue, because also in this kind of experiment, they can control the rotational quantum numbers. And the question, does a superposition of rotational quantum numbers can control the outcome of chemical reactions? And you can see we discussed here the superposition in the initial configurations. And another question was, is there any role for the entanglement in predicting the outcome of chemical reaction? And for that, you need a way to measure the entanglement. So if you go back to Bell inequality, this is a discrete, you have two apparatus here with Alice and Bob, and you look at the evaluation of this Bell inequality. But now when we talk about scattering, you have to generalize this from discrete values to continuous values. And this is done with my former students who now is professor in Northwestern University in China. And we generalize this one to continuous variables, where the aim or the goal is to look at the cross-section with different rotation, scattering angles, and look in the analogy of what we did with Bell inequality. Like you have two apparatus, you can think about the measuring in the z basis or x basis, and here superposition x plus z or x minus z, which equivalently in the experiment, you have to direct your molecular systems in different axes, horizontal, vertical, or in superposition 45 degrees. And look at this as you scatter in the continuous variable of the scattering angle. So just to wrap up this part of this one, I mean, we start asking, can we use superposition of initial reactant spin configuration to control the outcome of chemical reaction? And we have seen this from the experiment rubidium with rubidium. And now, can we use other degrees of freedom? This is an ongoing project to see if we can take the rotational quantum numbers or the vibrational quantum numbers to see how one can predict the outcome of these reactions. And again, the question, what is the role of entanglement, is not clear yet. And then we said, okay, can we examine this scattering process on a quantum device? So let me summarize what I'm going to do with this algorithm and then go through the details. So as I mentioned before, I'm going to show results for this, the simplest chemical reaction, which is the collinear exchange reaction of hydrogen with Hb. And here you change from V to V prime. So in order to do these calculations, people doing this calculation for 30, 40 years, fully quantum calculations and using classical trajectories. So what do you need to do this calculation? First, you need potential energy surface that describe the interaction with these three hydrogen atoms. And I will mention in a minute how this was developed, but people keep refining this potential energy surface. So for us, this is going to be a benchmark calculations on a quantum device that show at the end of the day, we'd like to get the probability for reaction as a function of energy. So we'd like to show that this results was obtained by fully quantum calculations can be repeated with a quantum algorithm. So this is the goal for this algorithm. And as you can see, the reaction coordinates, you can think about it. The way we're going to do it, we're going to prepare asymptotically the wave packet in the reactant channel, in the product channel, do forward in time for the reactant channel, backward in time for the reactant, with them both on the interaction region, and then calculate the correlation function. This is a procedure. And this is what people have done maybe 20, 30 years ago in these kind of reactions. So again, as I mentioned, that we have to prepare wave packets for the reactant and the product, and then forward in time, backward in time to the reaction center, reaction region here. And the idea, in order to calculate the scattering matrix element between alpha and beta, alpha for the reactant, the index, and beta for the product. So how do we calculate the scattering matrix element between alpha and beta? We calculate the correlation function, and the scattering matrix can be obtained from the correlation function by the Fourier transform. And then once we do the Fourier transform, I get the matrix element between the reactant and the product. The probability is getting by the absolute value square. So this is the goal. This is the way we're going to do it. So now for the potential energy surface, we're going to use the LSTH, and this the author. And you can see the dates. People start developing this potential in 1978. And the idea, the way they develop this potential, they use ab initio configuration interaction. I mean, you have a simple system. And in these calculations, they use hundreds of nuclear configurations to get the potential energy, and people fit it. Once you have all the data, you can fit it, so you can use it. And now people doing this kind of calculation with thousands of points on the potential energy surface, using DFT or other methods. But this was the potential given here was accurate enough to reproduce the experimental results. So the algorithm that we have 3 steps, both 1 and 3 are on a classical computer, which one prepare the initial state, and we discretize and get the Hamiltonian. So the only part of the algorithm, which is quantum, is calculating the correlation function between the product and the reactant wave packets. And once we calculate the correlation function, we go again classical processing and calculate the Fourier transform, which will allow us to calculate the scattering matrix element between the 2 channels. And from this, once we know it, we get the absolute value square, and we get the probability distribution. So again, we start looking at the asymptotic state in both channels, reactant and product. And again, once you have at this time, if the Hamiltonian, the asymptotic Hamiltonian, you have the interaction because you go from one atom to the center of mass of the diatomic system. And the relative one, this is relative, and interaction is the vibration because we excite the vibrational quantum number. So this is the Hamiltonian, which allow us to prepare the wave packet at the asymptotic limit. And we repeat this one for the reactant. So we have again asymptotic one in the reactant, and we have to prepare it in the same way where the interaction is you going from 1C, this atom, to the center of mass. And the interaction one is the vibration. So this is the wave function will be vibration times the wave packet in the asymptotic limit. So once we propagate inward, backward in time, then we have to look at the full Hamiltonian, which is the asymptotic Hamiltonian plus the potential which we get from the ab initio calculations. And now we have the full Hamiltonian in order to calculate the correlation function. So now, the formalism that people use, 30 years ago, they used the Moeller operator to define the Moeller state. Moeller states are the one that you propagate inward, go from minus infinity or plus infinity. So this will give you the 2 asymptotic wave packet going to the reaction center. So again, when you apply the Moeller operator, which is in the limit of plus minus infinite time here, if you start without, you get the minus sign, and you just remember this with the channel gamma prime for the product and the plus sign here for the reactant. We're going to propagate those with plus time, with the go from minus infinity to 0 and plus infinity to 0. So again, once we prepare the Moeller states, the plus and the minus, we calculate the correlation function with the full Hamiltonian. And then we know that if I have the correlation function, I do Fourier transform and get the matrix element, which connecting the gamma and gamma prime, these are the 2 channels. And again, as I mentioned, the rest will be done classically. I mean, doing Fourier transform, all this will be done in classical computer. The only thing I have to do in the quantum is the correlation function. So how do we calculate the correlation function? It's a very, very simple algorithm. We go back to the standard Hadamard test. So what is Hadamard test? Hadamard test will calculate the expectation value of a unitary operator, psi h, u psi, and you have the real part and the imaginary part. And this is standard in quantum computing. You can calculate the expectation value of u by one ancilla qubit here, and then these qubits sitting here on the second register to prepare the wave function. You do Hadamard, and again, Hadamard will to plus, you have combination 0 and 1, and you do control U, and then Hadamard, and if you do this quantum circuit, this very simple circuit, give you the real part, and if you include before the control U, the phase shift, this will give you the imaginary part. So now we don't have we have phi1, phi2, we have two functions here. So now the question is, we have to prepare the modified Hadamard test in order to calculate the correlation function. So again, to calculate the correlation function for the Hadamard, the modified Hadamard test is easy if you have two unitaries that can prepare psi1, psi2, or phi1 and phi2. So we apply first two unitary to prepare two different functions, and then we calculate the modified Hadamard test, which will give us the correlation. So again, this is the algorithm, or the main thing in the algorithm, how to calculate this. You start with the ancilla qubit, and here for our calculation, we use 10 qubits. And we have two unitary operators, U1 and U2, and U1 and U2, they are going to prepare the two Muller states, phi1 and phi2. So once we calculate phi1 and phi2, then you can see we run the Hadamard test. So this is the quantum part of the algorithm. So for the time, I will not, I mean, it's very simple. You can work it by yourself. I mean, it's very simple to show why this algorithm can give us the probability, because at the end, when you run the two unitary operators and look at what is the probability of getting 0, this will give you the real part of phi1 and phi2. So you can calculate the correlation function by the modified Hadamard test. Now you have to put all the details in the quantum circuit. What is U1, what is U2? And you can see the sequence of all the needed operator to get the phi1, which is the Muller state for the reactant, and getting all the needed propagation to get the Muller state in the product state, and then run the modified Hadamard test, which allow you to calculate the correlation function. So this is the very simple algorithm. So my student Samit ran the calculation, and from minus 4,000 to 4,000 atomic units. And again, just to remind you, the way we do the calculation asymptotically, you have, I mean, when you start with R1, and you look at how the atom HA interact with the center of mass here, and then when you look at the HA in R1, this is the vibrations. So you can go from the reactant channel, product channel, these are Jacobi coordinates, and then in the reaction region, you use bond coordinate, which is X and Y, and you can calculate the correlation function. So this is the numerical results here, and again, this is, I mean, I will leave the notes if someone would like to follow the procedure here for the calculations. And what we end up here, we get the correlation function. And now, when we say classical and quantum, again, classical is doing full quantum calculations. Sometimes it's confusing, people use the classical, but Classical here means full quantum calculation, and a quantum means quantum simulations on a quantum device. And you can see we have a full agreement between the full quantum calculations and the quantum simulation for this simple reaction, which is just H plus H2. And you see the difference here, we go 0, 0, and here we have 1, 1. So you start with the 0, the vibrations, and you move to 0 in the product, or you start from 0 and move to 1. So you excite the vibration states. And again, the full quantum calculation for this was done back, and you can see it's 94 by David Weeks and David Turner, where David Turner now he's at Weizmann Institute. And he did these calculations. I mean, you can see it's almost 30 years ago. So again, we have seen that we can get accurate results on a quantum simulator and compare with the full quantum calculations for this kind of scattering. And now on a classical computer, we calculate the probability goes 0, 0 by just doing the Fourier transform. And then once you do the Fourier transform, you take the absolute value square, and you can see the full agreement between the classical and the quantum for both 0, 0 and 0, 1. Now, okay, you can ask, okay, where the errors will come from for this kind of calculations. We have two sources of errors. So the first one is sampling. You have to sample to get these simulations. And it goes like if the precision epsilon and you look for the probability success of 1 minus delta, it goes like 1 over epsilon squared. So you need thousands of samples to get the simulation going. And then the second source of error is the Trotter decomposition, because remember, you're going to write the Hamiltonian as a sum of Pauli string matrices here. And then we did, in these simulations, we took Trotter approximation to second order. So you can see the error comes from sampling and from Trotter approximation. So again, we just put all the results for anyone who'd like to go through the results and the appendices. We have all the math and how the algorithm works on the archive. And you can see we put it, the second version last week. Just like one more comment, which I did not mention here, is like, remember once we write the Hamiltonian matrix with the basis functions, we have to write it as a sum of all Pauli matrices, where we have this 4 x, y, z, and tensor product, depends how many qubits are using here. And this coefficient can be obtained by trace of this Hamiltonian on these projected Pauli matrices. So now, just to summarize, first we show a couple of slides about the importance of interferences in chemical reaction. And we show that one can get constructive or destructive interference in the photoassociation of the rubidium-rubidium by controlling the initial superposition. You can see you have a reaction or not. And then the question, how do you use it for other degrees of freedom? This is an ongoing for rotational states. And then I describe a simple algorithm based on the modified Hadamard test that calculate the correlation function, which allow you to calculate the cross-section or the probability distribution for the reaction H plus HBC. And this, again, just a benchmark, simple calculation. And the results show that one can use this algorithm to get accurate results. So I would like to end here by thanking my students. And again, this quantum information, quantum computing is a true interdisciplinary research. I have students from chemistry, physics, computer science, and ECE. I will thank the different agency and the part from computation, from quantum machine learning is the project that we have at the Quantum Center. And I thought to end this talk by showing this, as we discussed in summer school and other schools, how chemistry can benefit from quantum information, quantum computing, and quantum chemistry on a quantum computer. And just to remind you, I mean, what we have in this field, we have over 80 years of research. We developed so many different approximations and different methods from ab initio, semi-empirical, DFT, non-conventional methods. And you can see we have 6 Nobel laureates in the field. So if we're going to say now we have a new tool, which is a quantum computer, and we're talking about getting accurate results, which we call chemical accuracy within 1 kilocalorie per mole. The only method that gives us this kind of accuracy with the control error is the variational method, which is the CI. And you can ask how many electrons chemists can do accurately with chemical accuracy. The answer, as far as I know, only 24 electrons. With 24 electrons, you can do full CI and get very accurate results up to the chemical accuracy. But then if you this list and this method, there is no one method that can solve all the problems. So I think the message is, again, we have a quantum computer here, but the question is, what is the problem that we're trying to solve? And in many problems, could be the hybrid is the way to go. And Susan yesterday, I mean, she gave us beautiful talk about using a model Hamiltonian for the spin system, but you have to use a classical method to come up with this model Hamiltonian. So it looks like I mean, way to go for a couple of, like in the near future is to continue with the hybrid classical and quantum calculations. And the question is really not the method itself. The question is, what is the problem that we are solving, and what is the right approach? And if it's hybrid or quantum or others, it depends on the problem. And again, thank you all for your attention.
Thank you for the great talk. Are there any questions? Yes.
Thank you very much for the very outline. You are calculating so your quantum computer calculates the correlation function.
Yes.
So what I'm not 100% understanding is, so you are basically using the same method as the classical calculation, but you do the correlation function with the quantum computer.
Yeah.
So why would you be surprised that you get the same result if you basically use the same method? And it's just at the end kind of seems to me that the question is how accurate and with which cost you actually can calculate the correlation function, right? Is that correct?
Because the heart of this algorithm is the correlation function, because once I know the correlation function, I do Fourier transform, I get the scattering matrix element, and from this I get the probability. I mean, you can say, okay, can we generalize it to also come the initial as you?
My question is more It basically, the quantum part boils down, and I really say that in quotes because I know it is very complicated, so at the end, it's a question of what is the cost of calculating your correlation function. Mm-hmm. And I mean, you say here that the computational cost goes exponentially with system size. Does that change if you do it with your quantum computation correlation function method?
Yeah, here I'm talking about electronic structure, and there we talk about the dynamics. So I'm saying for electronic structure, I mean, usually people argue it's like we have to scale it up and come up with a polynomial algorithm that give us the same accuracy. But in that one, I'm talking about dynamics, and doing full quantum dynamics, people can do it only for a few degrees of freedom. And this calculation, there's nothing new and no advantage whatsoever. It's a simple reaction. And the whole goal was with this calculation to show up a proof of concept that I can run this one simple as a benchmark calculation, get the cross section, and compare with the full. Do we have advantage? No. I mean, it's like.
Is there any promise that you if you kind of scale that up or so?
Yeah, this is what our goal is now, to see now once this is running on we know how to run it and get the matrix element. The question is, how do we generalize it to more complex dynamical problem where even full quantum calculation has difficulty to get the cross section?
Yeah, I think we'll save, if there are any other questions, I think we'll save them for the break. We're going to have a 10-minute break. We'll thank our speaker one more time. So we'll meet back in 10 minutes at 10:35. we find our seats, please? Huh? Yeah.
You want to follow?
Yeah. Can we find our seats and we'll we'll reconvene? Yes. I know. All right, welcome back. I'd like to introduce the next speaker. Her name is Raksha Kariwada. Professor Kariwada is an assistant professor at Illinois Institute of Technology and associate scientist at Fermilab. Kariwada earned her bachelor's degree in physics and mathematics at Linfield University, followed by a PhD in physics from Purdue University. She completed postdocs at the University of Washington in Seattle and Fermilab. Kariwada is engaged in quantum information science research with special focus on applications in fundamental science, and she's here to talk to us about sensing. So let's welcome her.
Hello, everybody. Thank you for having me here. Thanks to the organizing committee. So in the 40 minutes or so I have today, I'm going to talk about quantum sensing for fundamental science. So this topic is slightly different than what you have been hearing, which is probably more focused on quantum computing. So what I hope to provide you with is some sort of like a very high level introductory slides and information on what is quantum sensing, what are some of the challenges that we see in high energy physics, and what we hope to achieve with quantum sensing for high energy physics in terms of probing fundamental science. And so I will also include some of the slides of my own group that highlight some of the activities at IIT and Fermilab, followed by the summary. So so here is a slide that kind of outlines general motivation on why we want to use quantum sensors. So here in blue, what I have highlighted here is this science drivers for high energy physics. So high energy physics, not just collider physics, but this kind of like general ensemble of like fundamental science that can benefit from using these quantum technologies that I highlight here in yellow. And so you can see it's very relevant for science of like ultralight dark matter, QCD axion dark matter. This is one type of dark matter. And there's light dark matter regime in this energy scale. And then this cosmic microwave background radiation type of probes also. So these science drivers could use quantum technology highlighted in yellow that are, kind of classified under these different categories here, clocks, AMO, NMR, coherent sensors, pair breaking, and quantum non-demolition photon measurements. And so basically I'll kind of try to, as you can see, this is a very broad area here. So I'll kind of try to give you a survey summarizing some of these different types of detectors and what kind of quantum phenomena they use, how they work, very, very high level. So I apologize if there's tons of information on my slides. So the main thing to focus here is if you look at the electronic band gap of silicon, it's about like 100 eV or so. And so we're talking about regime that's like sub eV. That's kind of like the regime where this quantum technology is like highly relevant. So if I want one thing for you to take away from this slide is that quantum technology is really, really good for harnessing sub eV energy scale. So this is a slide from this survey that we put out in arXiv earlier last year around November. It's called Quantum Sensing Sensors for High Energy Physics. Check out if you are interested. And so since you saw a huge parameter space for science driver is very dark matter focused. I might just give you a brief introduction on like what some of the types of dark matter could be. So the two main dark matter types of dark matter that could utilize quantum sensors are called these like wave-like dark matters, you know, and then this particle-like dark matter. So the distinction comes around like a kilo electron volt here. And so anything higher, you can think of them as like individual particles scattering like billiard balls, and anything below that, you can think of it as like coherent wave of dark matter. So of course, you can imagine the technology that is relevant for harnessing this tiny energy that comes from dark matter particle interacting with your detector is going to be very different for these different types of dark matter. So for the purpose of quantum sensing, what we are interested in is not just the quantum 2.0 detectors, which is basically described by superposition and entanglement-based detectors. We are not just interested in that because we are at that stage, we are still kind of like trying to achieve that, but we still need to leverage on some of the classical detection technology. So what we have broadly defined as like this quantum sensor, which is more inclusive, is that any new quantum device or technique that has the potential to achieve great reach force beyond the standard model physics, then that achievable through conventional techniques traditionally used in HEP, not just superposition and entanglement based. So for the purpose of all of this, you know, if you see some detector technology here that I'm talking about that you are like, that's not superposition and entanglement based, that's because of this reason. So one thing I can highlight is, so there's a US detector R&D community under this coordinating panel for advanced detectors. And it has like a bunch of these different collaborations, and one of them is quantum and superconducting detectors. And I'm one of the two coordinators. So basically we're trying to coordinate detector R&D for superconducting and quantum detectors for high energy physics under this umbrella. So this is something to note. So I'm going to do a very poor job of summarizing the types of detector we have. And the first type, so I'll have 4 types. The first type is pair breaking sensors. So as the name stands, we kind of, this pair breaking comes from superconductor detectors where the Cooper pairs are broken. And you have, you know, like all these detectors relying on that pair breaking, but then they kind of work slightly differently. So you under this, you have microwave kinetic inductance detectors, transition phase sensors, superconducting nanowire single photon detectors, quantum capacitance detectors, and superconducting qubits and their variants. So the principle of operation for these kind of detectors is usually like something like a resistance or a quantum capacitance, or in terms of like qubits, coherence, or in terms of kinetic inductance detector, like kinetic inductance, that changes in your system somehow, right? And so that's kind of like how it operates. One thing before I move further, so one distinction between quantum computing and quantum sensing is that for quantum computing, you want to avoid decoherence and you want to avoid errors. On the flip side, in quantum computing, you want to use those readout mechanisms as mechanism for sensing the signal coming from like dark matter or some sort of particle and radiation interaction. So it's kind of like the flip side. We want to couple our signal to the qubits, let's say qubits and superconducting devices, and see the decoherence or some sort of like error, right? So that's kind of like the one distinction. So some of the advantages of this kind of detectors is you can do single photon counting, and some of them have like lowest dark count rates, and some of them have like low energy single excitation sensing and high quantum efficiency. So those are all really good advantages. And so basically all of that summarizes into like them enabling this standard quantum noise evasion. So I don't know if you guys are familiar with like a standard noise limit. Basically, if you are measuring two non-commuting quadrature, let's say like phase and amplitude, you have this fundamental uncertainty that you can't surpass, and that's going to be your standard quantum limit. And so a lot of these traditional detectors have that limitations that we use for dark matter searches, and so evading that has been one of our fundamental goals. And so some of these provide that by really literally photon counting, where you kind of get rid of that phase information. You're just counting, which is just the amplitude. So what has been demonstrated with that? So there is this slide that I put for hidden photon dark matter search, which is one of the ultralight dark matter that I showed you, kind of like lowest mass, one of the lower mass ones. And so this was using a superconducting qubit and a 3D cavity. So this is your Hamiltonian cavity qubit mixed state. And so basically, when a photon, that is the signal of this dark matter, comes to this like storage cavity, if its frequency matches to this storage cavity's frequency, you can couple this qubit and this readout cavity to this storage cavity and check for the presence of signals photon here, single photon here. So that will alter your Hamiltonian. And so what you are looking at is like your excitations from like ground to excited state. And then depending on how many number of photons, you have this stark shift. So basically using that technology, my colleagues put this very sharp limit here that kind of is along this ADMX limit, which is like wall limits on axion and hidden photons. That took us several years, if not a good part of a decade. And so this integration time was like 8 seconds. This was not a designated dark matter search. This was just to prove and do a proof of principle prototype demonstration. And this was taken over 8 seconds. So that's kind of the sensitivity we're talking about we get from like quantum sensors as opposed to traditional detection technology. So we have some other variants of superconducting qubits. This is a variation of charged qubit. This is very broadly used in far-infrared spectroscopic missions. This is called quantum capacitance detectors. JPL makes this, and so we're trying to use this as a single photon detector for terahertz regime. And so in the terahertz regime, there's no ultralight dark matter detection technology, and so we're kind of trying to reduce its background rates, and we hope to see something like the single photon events. So you can see qubit-based detectors are highly sought after and a hot topic of study right now in particle physics. So the second genre of sensors are coherent wave sensors. So this includes, you might be already familiar with like traveling wave parametric amplifiers that's used as a first stage amplifiers in a lot of qubit-based experiments. Squeezed receivers, which is also fabricated with these amplifiers, and then microwave to optical transducers, superconducting RF cavities, RF quantum up converters, etc. So you're kind of like, as the name stands, talking about like coherent wave as opposed to like single photon counting or anything like that. So the principle of operation, as I mentioned, is parametric amplification. Some of these look for like high Q resonance cavities. So Fermilab has these like really high Q quality factor superconducting cavities. And so these fall under that. And we have these technologies where you can convert lower frequency to higher frequency by like pumping. So that's also kind of the technology that falls under this bigger umbrella. And so the advantage is low noise readout for these amplifiers, and we have potential for dark matter searches with magnetic field and high Q cavity. So one of the main mechanisms of detection of dark matter for this like very ultralight dark matter is like we use resonant cavities. So high quality factor is really good because you can think of it as like having these like dark matter waves coming in and like them spending more time in your apparatus if the frequency matches to that of this resonant cavities frequency. And so having that high Q is really good. And so the enabling technology is a standard quantum limit. you can perform like squeezing, etc., and gain some sensitivity to the standard quantum limit. And so we have already demonstrated this in astrophysics. So for instance, here is another axion source, which is another type of dark matter, light dark matter, ultralight dark matter. So this was done at Yale, and the experiment is called Haystack. And so they used a squeezed state receiver, and they had twice the scan speed as when compared to when there was no squeezed state receiver. So basically, they got very competitive limit here in purple. These are long sought after benchmark models here. And so the main idea is, unsqueezed noise would be something like this. If you have like squeeze on one quadrature, it will be kind of lower on the noise in that quadrature. If your signal from dark matter comes in green and interacts with like this noise that's kind of already squeezed in this quadrature, when it's further amplified, this amplification has like much lower noise than what it would be without squeezing. So that's kind of like the general gist of it. And 4 dB squeezing was achieved. And so we're implementing these quantum technologies in particle detection. The third type of sensors are called these AMO, clocks, ferrometry, NMR, optomechanical sensors. So we have kind of lumped all of these different really broad range of sensors all together. This is just purely from like organizational point of view. There's nothing much too deep here. So this includes these systems like neutral atoms, trapped ions, magnetometers, spin precision, optomechanical devices, and entangled probes. And so typically the principle of operation depends on like some sort of like atomic energy level shifts or like some change in strain, acceleration, and entanglement induced correlation in quantum states. And so some of the advantages of this kind of technology is, of course, noise suppression, high sensitivity, also long distance quantum coherence, long wavelength radiation detection, and you can use this for like directional resolution of astronomical objects by using like entangled probes over like longer distance. So the enabling quantum technology is, there's something called Heisenberg's limit, which basically tells you how precise you can measure with like different N probes. And so with these entangled sensors, theoretically you can get this Heisenberg's limit, which is better than the standard quantum limit. So these are the other type of sensors, and what has been demonstrated with these. So here is an example of this tiny slither is this dark photon source around 48 gigahertz. And so this was using trapped electron. And so here is a limit. You can see it's pretty competitive and surpasses some of the existing limits. And similarly, here is another example of using entangled photons. So basically, there is this something called Illinois Express Quantum Network, which is a collaboration between Fermilab, Argonne, Caltech, Northwestern. And so what they demonstrated is high fidelity quantum teleportation that was achieved between multiple nodes, 50 kilometers apart at Argonne and Fermilab. And some of the milestones were achieved, like picosecond level entanglement distribution and clock synchronization. So basically, this is a one step forward towards quantum networking over longer distance scales. So this is the type of really fun, interesting work that is already being done with the third type of sensors that I talked about. And so the fourth type of sensors, I kind of lumped all of these under novel materials theory and simulation. So this is perhaps the least understood of all of the sensor types, at least personally for me, because I don't do material science. So this includes, this very, very broad range of materials. And so probably material quantum materials person would laugh at me lumping all of these together, but this includes quantum and metamaterials, low bandgap materials, including Dirac, while sapphire, high TC materials like spin liquids, nitrogen vacancy centers, and topological insulators, etc. So basically, all of these, host some sort of like exotic quasi-particles, like, magnons, spinons, phonons, and have some surface properties that are very unique, and which these quasi-particles can boast like quantum behaviors. And the hope is to harness these topological states for surface properties and low threshold excitations. So that's kind of the advantage. And the enabling quantum technology is, pretty much like coherence, entanglement, quantum transport, novel quantum mechanical states. So out of all of these, we started at least with a very simple sapphire crystal. So my group is itself involved in. So here, as a demonstration of like our simulation effort, I have put this graphic that shows phonon kinematic simulation in a 6-qubit silicon chip. So as I mentioned, these materials are interesting because we want to harness these like excitations that can be utilized to harness tiny energy deposition from dark matter interaction. And so sapphire is like of interest to us because it has these 100 millieV to 40 millieV optical phonon modes. And so we hope to excite those with dark matter. And so here is a phonon kinematic simulation showing that in a silicon chip, and we're working on sapphire qubits too. And so sapphire qubits, when I say sapphire qubits, I'm talking about qubits on sapphire chip. So here is a phonon caustic measurement that my student did. This is from literature. This is his actual simulations. And so we are doing a lot of study of phonon physics in these exotic materials, some of these exotic materials. And so I'll mention why that is relevant in a few minutes. So let's kind of recap like why we need these low energy excitation or low bandgap materials. So if you look at what the community needs in terms of like light dark matter is, if you look at this blue region, that's like the reason that doesn't have current existing technology to probe dark matter. So you can see below mega electron volt for like scattering processes like nuclear and electron scattering processes does not have current technology. And even though this is like less than mega electron volt, this is the dark matter mass. But if you consider that only a fraction of their mass is going to be transferred to the target material, so we are looking for sub-EV energy threshold that we want to detect for these dark matters. And this is precisely why we need these extremely low bandgap materials, preferably that have excitations energy of like, tens of milli-EV. Same for absorption processes where you have dark matter particle directly being absorbed in the system. So sub-EV here also we look for those kind of systems. And so my group is working on looking at this bunch of different novel materials. So silicon and germanium are the traditional dark matter detectors that have been utilized in these like very some of the most popular names that you have heard that look for dark matter, like super CDMS and other experiments. So those use silicon and germanium. However, theorists have proposed that like there are other interesting materials that would allow us to harness this extremely tiny energy, and so we are interested in that. And so in order to do that, we're kind of doing this simulation using GEANT4, which is this particle interaction simulation. G4CMP is a toolkit based on GEANT4. And so this particle simulation toolkit basically allows us to the detector response. And so we simulate what if you have like some sort of like energy deposition coming from either dark matter or radiation on your substrate of your qubit or like any device, how does that energy dissipate? Like, what is the phonon kinematics behind that? And so that's kind of like the study that is happening at Fermilab. And so here is a sapphire one that we produced. Here is a gallium arsenide one. So this is to enable this particular toolkit, which is really interesting. We recently put out a paper here estimating some energy threshold for phonon-mediated superconducting qubits for like energy relaxation sensing scheme. So it turns out to make dark matter detectors, you really, as you guys are familiar, like there's no one type of qubit, right? So depending on what qubit you use, what readout mechanism you use, and what type of fabrication parameters and the geometry itself, that's going to impact what kind of sensitivity threshold for energy deposition, certain energy deposition we can get for particle physics. So turns out estimating energy threshold for these qubit devices is not actually easy. And so that's one of our goals. So that's for particle detection. However, understanding phonon kinematics is extremely relevant for quantum computing also. As you are already familiar, perhaps, there has been, so I put this example from like Google Sycamore chip, but there have been these studies that show that like cosmic muon and terrestrial gamma rays can deposit several order of magnitude higher energy than your aluminum band gap energy and produce havoc in this quantum computer, right? So there's like correlated errors produced in this like 61 chip Google Sycamore chip that shows that not only this kind of decoherence was localized, but it kind of was all over the chip, like it kind of migrated. And so one of the main mechanisms of energy dissipation is phonon kinematics. Like we need to understand how that works, because it will, like in highly energetic event like this, there will be electron hole pair production, but then also phonons, and those phonons will down convert. Some fraction of all of that phonon is going to go to the superconductor, break the superconductor, and produce quasi-particles. That's what you don't want. That will cause the qubit decoherence. And so understanding that and coming up with mitigation technology is very relevant. So we try to do this phonon kinematic studies with both of these quantum sensing and quantum computing in mind. So there's also some topics in quantum that keeps on popping. For instance, like, I already talked about this. And there is also correlated charge noise and relaxation errors in superconducting qubit. And there are also these threshold of excess quasi-particle, a thermal quasi-particle, that are not going away despite how cool you make your physical temperature, right? Like there's always this excess baseline quasi-particle population. And so an active area of research is, where does that come from? And so some of the research has been, some suggestions has been that like there's stress-induced source of phonon burst, this quasi-particle poisoning, meaning like you actually have these microfractures in the substrate of the superconducting device that it was fabricated in, that is causing some phonons and causing some baseline broken Cooper pairs that is causing this baseline noise. And there is also some suggestions that the qubit themselves kind of act like antenna and coupled to these photons that also are causing this like baseline number of quasi-particles. So we really don't know, and that's really an active area of research. And so we have these low background facilities. So what Fermilab is great on is like we have built particle detectors underground. And so for these semiconductor, silicon and germanium based dark matter detectors, we had to worry about the same problem, because the cosmic muon and terrestrial gamma rays, they produced several orders of magnitude higher energy in these silicon germanium detectors too. So we kind of like hid them underground. So we want to, and we are in the process of doing a lot of this work, tests and studies underground, and do a comparative test above ground and underground, and kind of like understand these processes. So here is an underground facility we recently built. There is a dilution refrigerator inside this clean room, and there is like lead shield and everything. And so we're in the process of literally posting this paper in arXiv, where we did a study. This is the first stage of the studies after in this Nexus facility that is a dilution refrigerator, originally dedicated for dark matter studies, where we kind of think that, as I mentioned, qubits are sensitive to charge jumps on qubit islands, right? Like, so you kind of have a general understanding that these charge jumps are going to be proportional to some sort of like ionization radiation in the qubits, like I said. And the measurement of such charge jumps with a lead shield and without a lead shield, you would think that the gamma ray, background gamma ray, will be you'll be able to see the difference. If you're underground, you're shielding the muon flux due to this like earth, right, that you're under. And so what you actually have like gamma, and if you have lead shield open and shield closed, will be able to show you the difference on those flux charge jumps. And so we operate in multiple qubit chip for hours without correlated errors. So this is coming in our in arXiv, so stay tuned. I don't want to talk in detail about that before it comes out. So I might have ran out of time. So in conclusion, I want to part with saying that quantum technology has very broad applications in HEP. And so this dark matter thing is one of the things that I'm interested in. And at FirmLab and IIT, we're very much involved in that. But some of the work we do is highly applicable in quantum computing too. As you saw, the phonon kinematics, understanding that, and like our facility and everything. So that puts us in a good position to simultaneously understand implications on both quantum computing and sensing. And so there is some coordinated effort in like detector R&D going on throughout the US, since quantum sensing is like kind of newish, area. Yeah, so there's still a lot of synergistic efforts that could happen between HEP and quantum. We're still kind of trying to flesh that out, and we're going to have exciting next several years. So with that, I would like to open for questions.
Thank you for the great talk. Are any questions?
Yes.
Next.
Hi.
Hi. So 2 questions. One is, other than dark matter detection, these superconductor qubits, is it good for some more conventional particle nuclear physics experiments? What I mean is, I know, for example, transition edge sensor has been very nice, like energy or some kind of a calorimetry type application.
Yes.
So are these qubits going to give a better detector for some known, I mean, we don't know what dark matter is or even is there, but some known particle or photons for some more kind of near-term particle physics experiments?
Yeah, so very good question. So the reason so this is one of the things that I'm working on as my early career thing. So let me go to the slide. So maybe I will start with here. So this place here, like as I mentioned earlier, so below this, like there's no technology. And so what you talked about, the current technology is very much like electronic band gap energy, like around that 1 EV of like silicon and germanium. So those are the type of detectors that we use. So there's going to be fundamental limitations, above EV, in terms of sensitivity for those kind of detectors, current technology that you talked about, like TSS and MKIDs, etc. So below sub-eV is the regime where you want to think that the qubits are interesting. And so what we are doing at Fermilab, and so this is kind of like my group also, is like, there is several things we need to flesh out before being able to say, okay, we have sub-eV sensitivity, you know, like what that means is like, if you have some dark matter interacting with some sort of choice of substrate and using a qubit detector, you are able to see if it deposits like sub-eV energy. In order to get there, there are several things that need to be fleshed out. You know, like you have to understand the superconductor sensor threshold itself, right? First, like how well, like, you know, if you deposit energy on the superconductor itself, how, you know, like does all of it show up? And, you know, like how much can you read, right? Like there is a limitation on like how well you can read with qubits. Like, so the first paper that I told you that we just published shows that if you, you know, like if you just use like silicon qubits, you know, silicon substrate qubits, you don't have really good sub-eV sensitivity, you know, like for dark matter, if you use a relaxation, T1 relaxation scheme as a readout mechanism. However, recently what I'm studying with the help of my student is using another readout scheme. Looks like we have slightly better sensitivity. So to answer your question, it's actually not straightforward to come up with a, you know, like concrete answer, say, okay, qubits have like sub-eV threshold. It's looks like it has very high potential because of like how little energy it takes to break the Cooper pairs, you know, which is like 0.3 milli-eV or so. And when we're talking about sub-eV dark matter depositing, you know, like couple of orders of magnitude higher energy, you would think like you would be able to see it. So intuitively, we think that like it has the sensitivity, but like fleshing out the details and exact readout scheme, that's going to impact. So that's going to have a huge impact. So that's just the detector sensitivity. Now couple the substrate part. So if you have energy depositing from the dark matter to the substrate, there is also efficiency loss in like how well that can couple to the superconductor, because the signal comes from like how much of that, what fraction goes to the superconductor, right? Like that's what shows up in the readout scheme. So that is another level of you know, understanding that we have, and that's exactly where the phonon kinematics understanding that helps us. So we are trying to look at first Sapphire, because it has this like very low gapped phonon modes, like 100 milli-eV to 40 milli-eV. And so if you excite those phonon modes with like dark matter, we want to see, okay, can we see some fraction of that in our qubit readout? And so that's kind of like what we're trying to do right now. But ultimate goal is, let's say we are able to say concretely, the qubit will be able to see, you know, sub-eV dark matter. Then comes a point where we'll be like coupling it to different novel materials where the, you know, like the dark matter interaction will take place, and we use qubit as a readout mechanism. So sorry for the very long convoluted answer, but the point is, it still needs a lot of work. Non-dark matter. So are you saying like, is there anything else we can do other than dark matter? Yeah. So basically, so single phonon excitation and single photon applications are broadly relevant in Hebb physics. So for instance, I can tell you the exact phonon sensing for like sub-eV phonons. Turns out people who work on neutrino nuclear scattering, they also look for something like this. So I was recently having a chat with my collaborator, or like my colleague, who was saying, you know, like, this is the exact type of stuff that they're looking like. They need like to harness the nuclear recoil, the phonon that comes from nuclear recoil. And so the fraction of that, you know, the energy that goes into those phonons is exactly sub-eV. Yes, to answer your question, there are other experiments or particles that that could use the same thing.
Let's thank our speaker one more time. Is the next speaker on Zoom? Must be. Okay, and I'd like to introduce our next speaker. Make sure, Mal, can you hear us? Are we set? Good to go?
Yeah, I can hear you.
Okay.
Hey, Nathan, bring the computer up.
Can you hear me?
Yeah, I can hear.
Okay,
Can you?
great. So our next speaker is Mao Lin. Mao Lin is a scientist at Amazon Bracket. His past research focused on theoretical condensed matter physics, particularly in topological phases of matter. He studied at the University of Illinois, where he received his PhD in physics, and the National University of Singapore, where he received his Bachelor of Science in Physics. Let's welcome our next speaker.
Can you see my screen?
Yes. Yes.
Let me split. Okay.
That's great.
Okay. Yeah. Thanks so much for the nice introduction, and thank you for the opportunity to speak in this very nice organized summer school. So in the next 50 minutes, I will introduce Amazon Bracket with a focus on analog Hamiltonian simulation. Okay, hang on a second. Okay, so let me start with a brief introduction of Amazon Bracket. So Amazon Bracket is a cloud service in Amazon Web Services with a goal to allow anyone with a laptop to get access to quantum computers on demand. So here I show you a typical workflow on Amazon Bracket. So so step one is a user that write a program on a typical, say, Python language in his or her laptop and send it to Bracket Cloud Service. And after receiving the quantum program, Amazon Bracket then send the quantum program to the user select device. And the quantum device will execute a quantum program and send the result back to Amazon Bracket. And the next step is Bracket will save the result in a safe place that we call Amazon S3 that the user can access in the future. And at the same time, the result will send back to the user for next step post-processing. So today there are several kinds of quantum computers available on Bracket. So in the first row, I show you what we call gate-based device that can run quantum circuit. And today we have three types of quantum computers, three kind of gate-based quantum computers from Rigetti, IonQ, and OQC. And the next row that I show you is a special purpose machine from Kira that can run we call analog program, which is the focus of today's talk. So let me first introduce what I mean by analog simulation. Let me start with quantum simulation first. So quantum simulation is the early motivation for us to develop quantum computer in the maybe 90s. So the idea is, I suppose we have a quantum system of interest that we would like to study its states or dynamics. But we know that to classically simulate this kind of quantum system is hard, which require exponential runtime or memory. And the idea of quantum simulation is, I suppose, we have another quantum system that we call quantum simulator down here, that we can, one, easily prepare its state, and two, easily control the dynamics or the evolution of the quantum simulator. If this is the case, then we can measure the final state of the quantum simulator, which will then tell us some information of the system of interest, right? So this is really idea of quantum simulation. So today, there are different kinds of approach to do Hamiltonian simulation. So in this table, in the slides here, I show you two approaches that we call digital and analog Hamiltonian simulation. So the first one, digital Hamiltonian simulation, is really just quantum circuit, right? So in writing this quantum circuit, you specify in which qubit you would like to perform which kind of quantum gates, say Harman gates here or CNOT gate here that I show here. However, for analog simulation, the component is quite different, and mindset of designing this kind of quantum program is quite different. For analog simulation, you are not specifying gates. On the other hand, you're specifying a time continuous Hamiltonian that is acting on all the qubits at the same time that governs their quantum evolution. There are different advantage or limitations for these approaches. I just highlight one. I just highlight several for doing analog simulation with Ripple atoms here. So with Ripple atom, one of the advantages that you can, as we'll show later, you can place atoms in almost arbitrary 2D geometry. This is different from certain kind of gate-based device that you have to work with a fixed layout. So in this way, you can avoid some overhead in that aspect. And another one is that suppose you're interested in certain Hamiltonian that is closely resemble the Hamiltonian of the hardware, then the quantum simulation using this analog approach can be scaled up to a quite larger system size. So there's some, but however, there's some downsides on doing analog simulation, one of which is that the programmability is limited in this approach. As I show in the picture here, in doing this analog simulation, the control or the laser here is acting on all the qubits at the same time. And suppose you want to address individual qubits or atoms, it is limited at this moment in this approach. So let me just show you two canonical use cases of doing analog Hamiltonian simulation with Ripple atoms. And the first kind is really problems based on some physics problems. So for example, you would like to study the ground state or some dynamics of, say, spin liquid that I show here, or some lattice gate theory from high energy. And the second type is coming from optimization. So there has been research showing that Ripple atoms is suitable to solve the so-called maximum independent set problem, and which is essentially solving some Ising model behind. So for the past few years, there has been quite a large set of research done on Ripple atoms, in particular simulation. So here I show you 4 of them from Harvard's group. So they have been be able to simulate many-body dynamics as well as probing the topological spin liquid and study phase transition of up to 2056 atoms, as well as solving the maximum independent set problem using atom arrays. So in the next few slides, I will show you how you can reproduce one of the results from here, a kind of a scaled down version of the results here through Amazon Bracket. Okay, so so this result is from 2017, where they studied the phase transition, among other things, the phase transition of this Ripple Hamiltonian. So if you look at this Hamiltonian, it's really a Ising type of Hamiltonian where you have an X term, and this is the Z term, and this longitudinal interacting terms here. And in this Hamiltonian, you have control over 2 parameters, which are the coefficient of X and Z terms that we call omega and delta. And one example of the time-dependent omega and delta is shown here, where you tune delta from negative value to a positive value at the end of evolution. At the same time, you control omega, which is shown in red here, from 0, and you ramp up to a positive value here, and stay constant and ramp down to 0 at the end of evolution. So they were studying a a 1D chain of atomic arrays. Here I show you an example of 13 atoms here. And they were able to show that with this kind of annealing schedule, you can observe a phase transition from the initial state where all the atoms are in ground state to the antiferromagnetic state shown here, where the atoms is occupying the Rydberg state and ground state alternatively. And by tuning the atomic distance, they can show that they were able to realize different Z2, Z3, as well as Z4 states. So and in the next follow-up work, they were able to do a similar experiment on 2D lattice with 2056 atoms, where different phases are realized by tuning the interacting term in the Rydberg Hamiltonian. So, we can now next. Let's show that how we can reproduce kind of the results on bracket. So the first step is to initialize the atom arrangement that we call register. So you initialize this object called atom arrangement, and you put in the atoms one by one, basically the coordinates of atom one by one. So here I show one example of a atom array with 9 atoms, which is the one shown here. And the second step is to design the power schedule that tune the parameters omega and delta. And the idea is you specify several time points and as well as the value of the omega and delta as shown here, and finally put them together as a piecewise linear function, which is the one shown here. So for this kind of curvy power schedule, we can approximate it as well using the piecewise linear function on bracket. And the next step is to assemble the two objects that we just defined into the objects that we call analog Hamiltonian simulation. And at this step, you have basically defined a program that is ready to run on the QPU, on the QPU. But before that, right, you would like to make sure the program is behaving as you expected. And the way that we can do it on bracket is you can define this local simulator, and then you can run this program on a simulator to check, the result is what you expect. And after that, you can define this AWS device object that is, here I show you an example for Aquila, because we're running analog simulation program. And finally, you can do device.run program with the number of shots that you would like to run. So here I show one result from the hardware, and it reproduced the antiferromagnetic states for 9 atoms. You can ramp this up to around a few 10 atoms on Aquila today. So there has been some research done on today's Aquila device. So here I show you one example that was carried out by AWS researcher and external partners, where they study a novel optimization approach, and they use that to show that it can solve the maximum independence problem with up to 137 nodes. And they were able to show that the approach is doing relatively good compared to other approaches here. So if you're interested in research of this kind, you can search the keyword AWS Quantum Block, where we routinely post research done in Amazon Bracket and Amazon and as well as some features available on Amazon Bracket. So with that, that's my last. I'm happy to take any questions.
Are there any questions? If not, I have a quick question. I was wondering, what do you think is the biggest barrier of entry to Amazon Bracket? Is it the syntax, or is it understanding systems? What do you think is the biggest barrier of entry?
Yeah, that's a good question. So one barrier that I have been seeing is to get familiar with the cloud service. So when I first started, I'm actually not familiar with cloud service at all. And I imagine that is probably the case for most grad student as well as postdoc. And we have a dedicated team that we can help interest researchers to get familiar and ramp up with a cloud service such that they can use Amazon Braket to do their research efficiently. Yeah, that is one of the barrier that I keep seeing. Yeah, from time to time.
I see. Thank you.
Yep.
Are there any other questions? If not, let's thank our speaker one more time.
Okay.
Chris, are you on Zoom? I'm not, I can be. Yeah, please. You just share your screen from Zoom and then you don't even have to hook it. All right. You have the link? I don't have the link.
Okay, while he's setting up, let me introduce him. Our next speaker is Chris Monroe. Chris Monroe is the Gilhooly Family Presidential Distinguished Professor of Electrical and Computer Engineering and Physics at Duke University. He's also the co-founder, former CEO, and chief scientist of IonQ Incorporated, the first pure-play public quantum computing company. Monroe has pioneered nearly all aspects of trapped ion quantum computers and simulators for demonstrations of the first quantum gate, monolithic semiconductor chip ion trap, and photon interconnects between physically separated qubits. To the design of fabrication, the use of full stack ion trap quantum computer systems in both university and industrial settings. He's a key architect of the US National Quantum Initiative, a fellow of the American Physical Society, Optical Society of America, the UK Institute of Physics, and the American Association for the Advancement of Sciences. He is a member of the National Academy of Science. Let's welcome Chris.
Slide here. All right, I guess we can just do it from there. This cable's not working at all, huh? It should. I mean, I don't know if anybody's tried to do it today or not. Oh, okay. You know what I'm saying? All right. I'll check it out and we'll just do that. Sorry for all the drama. There we go. Okay, we're good. All right, very good.
Okay, thanks. Sorry. Thanks for the patience, your patience. So I have some time to talk a little bit about this field of quantum computing from both an academic viewpoint and also an industrial one. So this is kind of a funny title. And what I think I'll try to convey is it's certainly an interesting time for this field, but I think there's a lot of tension going on. And I think I think universities and government and industry aren't quite yet, they're not playing in sync, let's put it that way. And it makes it interesting. I think there's lots of attempts from all sides to bridge that gap. And I'll sort of tell you what I mean as we go on here. So thanks for the introduction. I will speak on mostly behalf of Duke University, but also talk a little bit about the company I know best, that is IonQ. We'll just go from there. So we all know that Shor's algorithm pretty much got this field going. Before that, it was quite nascent, the idea. I mean, we didn't even use the term qubits and quantum gates so much. But with Shor's algorithm, there was a concrete application. If a quantum computer existed of a certain size and a certain very low error rate, we could do something very interesting that we think we cannot do classically, and that is factor large numbers. And the cool thing about Shor's algorithm, of course, is that we know exactly what that program will look like, how many gates it will involve, and so forth. I mean, there's probably tricks to be determined in compiling, but it did change the complexity class of factoring, the best known classical algorithm, where n is the number of bits in the number you want to factor, to a polynomial law. So this was a really big deal, and because you could prove, it is a probabilistic algorithm, but the probabilities after running a few times are pretty high that you can factor. So this is a very fundamental result, and I think the academics loved it because you could have these proofs. I won't go through this. But on the other hand, there are applications out there that I think businesses have been attracted to that are more heuristic. You can't really prove anything about them. And so academics don't tend to think much about these applications, like the traveling salesman problem. We're pretty sure that a quantum computer cannot solve this one, finding the shortest path between a bunch of cities on a map. It's a combinatorial optimization problem, and the physics of it, of course, is the gaps between the shortest path, the ground state, and the next one gets exponentially small with n. However, a quantum computer might be able to, I would say it this way, you cannot prove that a quantum computer cannot do better than a classical computer at approximating the ground state. And so I think academics tend not to like that because there's no proofs. Theorists are kind of out of luck. You have to build these machines and hope they will come. This is a little bit of a leap, but I also consider many physics problems and chemistry problems as similar to optimization, how a bunch of electrons optimize their conformation around a molecular stem. That's sort of an optimization program. It has some quantum mechanics in it already, but again, it doesn't look very promising in theory. None of these things. So to me, this is a little bit of the first, little bit of a disconnect in the way we look at problems from an academic standpoint versus an industrial standpoint. Now, this is a slide that you'd never see in an academic talk. It's a hockey stick, kind of a hockey stick curve that you need to do if you're going to start a business or you're going to show that you can actually make money with these things. This is a plot of I don't know if there's a famous book called The Innovator's Dilemma by Christensen. The idea of a disruptive technology that is better than previous technology, but it's very expensive to start with, and it just takes time. You have to find the market, but then it will eventually take over. A great example is flash memory, which when it started 25 years ago, it was not competitive at all with RAM on computers or hard drives, but they found a niche in digital cameras, and that got them, that there was enough investment that they could make it better and better. And now, of course, it displaces most of the storage we use on our computers. And so the idea in quantum computing is that, well, it's going to take over where classical computer leaves off. And this is, you might say this is hype, At the same time, I think our academic sense knows the size of the universe, and these combinatorial optimization problems, the number of configurations grows exponentially, so that there are problems that we'll never ever solve classically, period. We just won't. It doesn't mean we will with quantum, but if we hope to gain access to 10 to the 1,000 configurations, it will have to be quantum or even something more radical, because there's just not enough space in the universe. So that sounds hypey, but it's a very reserved statement that if we're to solve these big problems, it'll have to be quantum. And apparently that's been enough to get lots of investment in the field. Of course, another interesting, maybe it's too strong or controversial to say it's a disconnect, but I think a lot of the, I would say most of the technology that's being proposed for quantum computing is based on this wonderful success we call Moore's Law. And it's super useful always to go back in history and look at what stimulated the growth of classical computers. I think we would all agree that this was a huge, it's not, it shouldn't even be called a law, it's also a heuristic, but because we found uses for computers, it just funneled more money to make it cheaper and cheaper to pile transistors on chips. So this is a log plot of the number of transistors normalized to 1978 over the last few decades, and that's a factor of 10 every decade or something like that. That's Moore's Law. And that, of course, gave us all the growth. You can see that it's tapering off because we're getting down to a few nanometer transistor size, and there's just not enough space. And I like to connect this to Feynman's wonderful speech. You probably know this one from 1959, shortly after the development of the first solid-state transistor, when he said, when you get down to the bottom, there's plenty of room at the bottom. When you get down to the bottom, there's no new opportunities for design. And I think the opportunity is very clear, that when you get down to the bottom, these new laws of physics allow you to do computing in a different way, and that's quantum. We often forget the other Moore's laws. These are more economically driven. The cost per transistor. There's no way you can field billions of transistors on a chip if each one's $1. So the cost per transistor has to really come down, and of course it did. This is sort of a corollary to Moore's law pose. There were use cases, there was commercial interest, so we learned how to make them cheaper. This is the transistor price scaled appropriately. It's a log plot over time in the last few decades. This one's a little different. This is the scaled cost per transistor. I guess it's linear, I'm not sure, it's a pretty vague plot. But the x-axis here is the size of the transistor, and as you know, we're approaching a few nanometers, and it may be that the cost goes up. It might be still worth it to do it, but if it goes up exponentially, it won't be. So these laws, I think people don't, especially in industry, for some reason, I don't think people are paying attention to these laws in scaling up quantum computers yet. And that, well, it's not a bad thing. I think companies are now doing lots of research, and that's a good thing, especially if you're a researcher. So this quote I stole from my colleague Bill Phillips at the University of Maryland and NIST, and he's fond of saying that a quantum computer is more different than a laptop than that laptop is from an abacus. And what he means by this, I think what he means by this, well, is that the laptop and the abacus are both Turing machines. We have classical models of how they work. One is super fast and much more useful than this, but they follow the same laws of physics, if you will, even though the laptop has different different components. Whereas there's very little in terms of commonality in describing the fundamental physics of how a quantum computer works with a classical computer. And I think this fact leads us to wonder why we should ever think of a quantum computer to even look like a classical computer. It's so different. So this shows sort of the different technologies that are out there. You can't see it on the bottom here, but this is quoting a Science article. The editors did a review of the technology out there back in 2016. So this is a long time ago. I even had to add a couple of columns here of the new technologies, kind of update these things. And I also I reordered the columns to the left ones and the right ones. The left ones, so-called natural qubits, atoms, electrons, photons, things like that. And the right ones we call synthetic qubits, almost always solid state. And what's interesting here, I think, is that the big behemoth companies are really invested in solid state quantum computing. It doesn't surprise me because that's what got Moore's law. And many of these companies either started Moore's law or derived benefit from Moore's law. So they certainly believe, look, if let's face it, if you're Intel or AMD and you want to invest in quantum computing, it's going to be silicon because you're a silicon company. To me, this is very interesting and great for academic research because these synthetic qubits have, well, it's great for everybody because these big companies have brought so much attention to the field and a lot of funding from different sources. But I think that the natural qubit systems, which this is just very interesting to me, which historically have been confined at university laboratories. These are physics labs where you have individual atoms, atom traps, ion traps, single electrons, things like this. What's interesting is that these things really should be over far in industry because the qubits are kind of done. I mean, if you have a single electron and it's isolated, you're not going to improve its properties. It's a fundamental particle. You can't do anything with that. The yield is 100% in a sense if you can, control them. So it's about control. There's a lot of engineering needed, but I don't want to say that physics left, but there's not much physics of the qubit itself left. Whereas these systems, and you've heard in the summer school as well as most conferences on quantum computing, there's a whole lot of great physics going on. How to realize maybe an emergent particle that is self-error correcting, things like this. That's really hardcore fundamental physics, and big companies are doing it. It's great. I wish big companies would be doing more engineering of these systems because these systems need the engineering. And even though I'm a professor of engineering and physics, engineering really doesn't happen at universities. We teach it, we can do research in it, but come on, you don't manufacture things at a university. That's not the role of a university. And plus nobody's gonna buy it because it's not gonna, I don't know, would you, I love saying, would you hop in a helicopter that was built by a bunch of grad students? Of course not. The idea of reliability and high yield, this is something that it's very hard to teach. It's very hard to do on a campus. So that's a disconnect, I think, continues. It's a very interesting one. It's sociological. And I think it's an interesting time. I think, thank God for these big companies for bringing attention to the field, but my God, I don't think they're serious on really building one. Okay. So with that strong statement, let me jump into the technology I know best, of course, these trapped atomic ions, very similar to trapped neutral atoms that you heard about earlier in the week. And this is a plot, continuously gets updated, and you should take it with a grain of salt. This is largely considered to be the bottleneck of quantum computing is the quality of the 2-qubit gates. These are the ones that entangle, that you can use to make a universal gate set, to make adders, multipliers, and do algorithms. So the 2-qubit gate, very much like the NAND universal gate in classical computing. So this is, there's also sociology in this plot. This is over time, the gate error, which is roughly 1 minus gate fidelity, if you want, over time. And we see these 3 technologies, which I would say are sort of leading in terms of being built into systems. And one thing very interesting, the neutral atom platform is really coming on strong now, but somehow they only got started in 2010, whereas all the physics behind it was done 10 years earlier. It's interesting. I mean, it would be nice if they had had another 10, 15 year start. In trapped ions, we did get started way back then. So the aspect that you should really take this plot with a grain of salt is that these are usually experiments in a physics lab with isolated qubits of exactly 2, or not too many. They're not worried about scaling or making a system. So this is, it's necessary to know what limits are of your fidelity, but it's not sufficient. You really have to enjoy such low error rates in a system, in the context of a scalable system. And with these atomic systems in particular, we know that the ground is in some cases even below 4, below 10 to the minus 4, the error per gate. We haven't hit it yet. This last point, very recent from Honeywell Quantinuum, 99.96, I think, in their trapped ion system. And all the references are here if you want. So the trapped ion platform you haven't really heard about in this summer school yet. This picture you've probably seen, this is exactly 80 individual ytterbium ions that are electromagnetically confined above this chip. This chip, there's nothing quantum about it, even though it is made of silicon, just because you can etch silicon with lots of tools. It's coated with gold. And there's about 100 electrodes. You can't really see the detail here. But the ions occupy a space of about half a millimeter. And they're 1/10 of a millimeter above this bow tie, above this little chip. And the reason it's in a bow tie is that we have to shine laser beams to hit the atoms, but not hit the electrodes, which is not hard. If you're 100 microns away and you have a 1 micron beam, you can do that. But this isthmus really helps with the optics there. So the architecture is here. Each atom is a qubit, and you're wondering why they're separated. Well, they're charged atoms, they're ions, so they form the Coulomb repulsion forms a crystal. It's made to be linear. There are many different geometries. The easiest one is a linear one. And we do that by making the trap very weak in one dimension compared to the other 2 dimensions, if you want. And we basically poke these atoms with laser beams, much like you would pluck a guitar string. The atoms move, and because they're charged, they can convey information stored within the atom. Now, the qubit is in the spin states, if you want, internal electronic states of the atoms. And let me just go through very quickly. This is a very naive picture of how a gate works, but the physics in some regimes is spot on. The idea is, if we want to entangle any 2 of these qubits, we send laser beams to those 2 qubits, and the force applied, these are optical tweezers. By the way, unlike neutral atoms, we don't need optical tweezers just to hold the atoms. The atoms are held by electric forces. We use the optical tweezers, we turn them on and off only when we want to hook them together. And what's important is that this optical tweezer force, due to selection rules and subatomic physics, is very well established by now, starting with Serac and Zoller almost 30 years ago. The idea is this force is a state-dependent force. So if the qubit's in one state, it moves up. If it's in the other state, it moves down. So spin up moves up, spin down moves down. And if you just look at the physics here of just these 2 atomic ions, what happens is, depending on which state the pair is in, they will have different Coulomb energies. If they're in the same state, they're the same separation. But if they're in odd parity states, up, down, or down, up, they're a little further apart. And so they pick up a phase factor due to this defect in the Coulomb energy. And this, you see, goes like 1/r³, which is too bad, because if you're really far apart, then this, the difference in distance is very small. But we get around that, and I'll tell you in a minute. So if you look at the 4 possible states of those 2 qubits, the odd parity states pick up this phase shift, and so that's your gate. That's actually it. This is a nonlinear gate. It's fully equivalent to a controlled NOT gate. It's a universal gate when accompanied by single bit rotations, which are fast and easy and cheap, just single laser beams hitting single atoms. When you set this phase equal to pi/2, that's the one that gives you full entanglement. Now, back to a few shortcuts I made. Number one, the basis is not the z basis. The force is in the x basis. That's kind of a detail. But what is more important is that the time scale of this gate is relatively slow. In fact, you might wonder what happens to all the other ions when you pluck 2 parts of a guitar string, the whole string partakes. And the bad news is you have to deal with that. And so there are lots of coupled modes of motion. It's a very classical problem. Mass is connected by springs, except every atom is connected to every other atom by a spring. So it's a little more complicated than your Physics 101 version. But the good news is when we can deal with those normal modes, it's a classical algorithm, and we can actually pulse shape the laser in such a way that all the modes are involved and they're all delocalized, but they can all decouple at the right time while we get this phase shift. So that's a classical control problem. It's not exponentially hard. It's linearly hard with number of qubits, but we know how to do that pulse shaping. And the good news is you get rid of this 1/r³. In fact, the time to do a gate is independent of distance. It's a fully connected graph, very powerful. So this is the architecture for a trapped ion quantum computer, basically, the basic architecture of dealing with lots of ions in a single crystal. And the ideas were first proposed by Sir Akinzoller, which had some serious noise problems, not fundamental, but nothing's fundamentally impossible. But in practice, nobody uses this. They use the one by Molmer and Sorensen. The gate of Molmer and Sorensen is about 25 years old now, and it hasn't changed, which is good. Sort of like the NAND gate. We still use the NAND gate classically. We're done with that. It's the only platform, I think. Maybe there's some superconducting gate standards out there. But ions, I think, are the only platform where the gate's nailed. It's done. We're no longer changing the gate. So we can move up the stack if you want and think about how to build systems out of it. Well, if you want to build a system, this is probably why the big companies were scared of trapped ions at least 10 or 15 years ago. It is a physics lab. And even though there's an ion trap, there are actually 2 ion traps on this table. They occupy almost no space. The atoms certainly don't occupy any space, but you need lots of table space and lots of people. They're even duplicated somehow in this funny picture. Lots of controls, and it's all optics. This is just optics. Optics, optics, and optics. Inputs and outputs. Our eyes, ears, and sense of smell of these ions are laser beams, optics. Which is actually not a bad thing, because optics is a mature field. There's lots of technology out there. It's changing every year. And something like this is actually turning into something a little more manageable. This is a picture of a more recent system we built several years ago, and almost everything in that previous picture, without much exaggeration, there's a little exaggeration, is inside this box, which is kept closed for many months at a time. There's a vacuum chamber in there with atoms on a chip. And the optics that we need to steer and adjust, it's all done on electronic mounts. So we have automatic calibration procedures and so forth. Now, building this was really outsized for a university to do. And I would say IARPA and NSF, the STACK program, really bankrolled a lot of this, especially IARPA in the early days. There were a few mini $10 million grants just to build this, and it allowed us to work with companies. I didn't mention Sandia makes the chip trap. We're not going to go in there and make chips. They make the chip trap and they send it to us. They have a very capable team. We worked with Cold Quanta on vacuum chambers, AOSense, you don't see under here, L3Harris and Coherent on optical controllers, make lasers, especially for our application. And my colleague Jungsang Kim at Duke has worked with Cold Quanta to miniaturize the vacuum chamber itself, which in the latest version is actually sealed right on the chip itself. The ion pump is not shown here, but it's actually very small. It's a little finger. And even at room temperature, they can get really good low pressure that allows these trapped ion systems to be built. Okay. I mentioned the stack. Well, we can, with this hardware, we can think about now climbing up the stack. We have a universal gate set. How do you compile them most efficiently for a particular algorithm? And what other applications are out there? So we find ourselves kind of up and down this stack with this trapped ion platform at a university, which is fun, but it means we've left the physics department, for sure. Not only that, we've left the engineering department. We're starting to interact with people from all different trades. It comes back right around to physics in some cases, in many cases, because that's what we know. But I think in our last talk, we heard a little bit about quantum simulations, and a lot of those applications are in the realm of condensed matter physics. And I probably won't have too much time. I'll maybe talk about one example of that. But with ions themselves, I mentioned the pulse shaping of the optics. We need pretty fast and agile optical modulators to allow us to hit the target atomic ion qubits and not any others. Now that noise is actually very small, but there's stuff going on in the background we have to mitigate against, and there are ways to pulse shape to take care of that. I mentioned, maybe I didn't mention, but the gate, the Molmer-Sorensen gate, is actually an Ising gate. We call them Ising gate sometimes. It's not a NAND gate or a controlled NOT gate. It's an Ising gate. It's as expressive as a C-NOT gate, but going back and forth when you have a big circuit is pretty tricky. And if you're not careful, you'll end up, if you read a circuit from a textbook in C-NOTs and Hadamards, and you bring it over to Ising gates, you're going to end up with a balloon explosion of the number of gates. And there are ways, these are heuristics themselves, there are ways to compile this though. Some of them compile in a very smart way that cancel certain errors. So there's a lot of art, black art up here. And I will admit, I probably am least familiar with the stuff that goes on there, these compilers. I'm a little more familiar with some of the applications at the high end because they're based in physics, as I mentioned, condensed matter physics, for instance. So it's been a lot of fun with this machine and its predecessors and its descendants in the collaborations we've had with government labs throughout academics throughout the world, industry, and so forth. And again, I obviously don't have time to talk about much of this, but in fact, very recently we've been working with Alex Schukert, who's a postdoc at JQI, University of Maryland, on observing a phase transition in 1 dimensions, in 1D. And again, a phase transition is not supposed to happen in 1D. And the trick here is that we don't have just local interactions, we have long-range interactions, and that's sort of the trick in condensed matter physics that allows it to work. And in this setup, it's a quantum simulation, not a gate-based evolution. And I tend to blur the lines between quantum simulation, analog quantum computing, and gate-based quantum computing. And you can ask me a question about error correction later if you want, but I'm not going to talk or comment on error correction at all because errors are really low right now. The errors are so low that we're sort of limited by the number of qubits we have. So we're not yet needing error correction. And so analog or digital quantum computing, I don't know, to me it's the same thing. This experiment, we implemented an all-to-all Ising interaction that has a particular form. Actually, it falls off exponentially with distance, and we can tune that exponent. I won't get into the details here. This is not a ground state phase transition. We make many states with different in the energy landscape, and watch them evolve. And again, there's an archive paper on this if you'd like, showing with up to, I guess, it's a small number of qubits, only 13 qubits. The theory on the right, the experiment on the left, showing that as we make different states of different energy density, we can sort of see, you might not want to call it a phase transition with just 13 qubits, but maybe a crossover if you want, from the paramagnetic phase to ferromagnetic phase. One other example of a quantum simulation, we've been working with Diego Porras, a Spanish theorist, on implementing the SSH, the Sue Schrieffer-Heeger model in a bunch of spins. Here we have this all-to-all Ising interaction. You've seen that before with a transverse field. And of course, these two don't commute. So there's an interesting interplay between those two parts of the Hamiltonian. But then we have a dynamical part of the Hamiltonian. It's actually a site-dependent, it's easier to display in a picture than the equation here, but it's a site-dependent magnetic field that oscillates. And we have it pairwise so that the first 2 qubits see one phase of that dynamical field, and the next 2 are 180 degrees out of phase and so forth. I think there are about 25 qubits here, and we're only paying attention to the central 22 of them. We need an even number because you can see that sort of the pattern here. Well, when we eliminate, whenever you have a harmonic term in the Hamiltonian, there's an effective Hamiltonian with some assumptions behind it. But when we find that effective static Hamiltonian, it's this SSH model, which is a flip-flop. It's sort of an XY model that has alternating bonds as you go through the chain. And it does have a somewhat, it's not nearest neighbor only, so the SSH is usually nearest neighbor, so it's modified here. And the sign of that, whether you have a strong bond on the edge or a weak bond on the edge, we can control by the parity of this modulation force. So this is the one that's interesting, actually. Having a weak bond on the end is what the SSH model is about. And when you have a weak bond on the end, it turns out this chain of spin 1/2 systems in 1D has these so-called topologically protected edge states in the system. So we can directly observe this, and it's sort of a smoking gun here. And this is, I think, 22 qubits. And when we excite, again, this XY or flop Hamiltonian allows an excitation to conserve energy and have sort of spin transports through the system. when we excite either edge, the left right edge or the right edge, the time goes from top to bottom here. The excitation pretty much stays on the edge, or at least more so than when we excite the bulk. When we excite the bulk, it sort of diffuses away. And so this is, again, it wasn't infinitely long-lived, but the excitation on the edge was significantly more long-lived than in the bulk. And that's the signature of this SSH dynamics. And again, there are long-range terms as well, so it has to be modified, and there's a lot of, even a little debate on whether this should be even considered SSH. Well, whatever. It's an example of a many-body system that sort of preserves and keeps a excitation alive, if you want. And it does have connections to topological quantum computing different materials. To me, it's a very nice example of using a very controlled quantum system to simulate something maybe that's harder. Okay, let me now pivot a little more to the business side. And this is a paper actually it's 10 years ago now, that it's not a review paper, but it occurred to us, especially me and Jungsang Kim and Ken Brown, that we sort of have a platform that we can scale indefinitely by using photons. By atomic qubits and trapped ion qubits, they're optically active. They can actually emit photons in a way that we can entangle at a distance. And it sort of made us think of this modular architecture where you have a bunch of crystals in even separate vacuum chambers that can be connected by single photon interfaces. That's the hard part. Everything to this side is classical. We can have beam splitters. This is a cross-connect switch and a CCD camera. And you can herald the entanglement, holistically herald the entanglement of any pair of ions in any one of these modules. And so this paper is PhysRev A, and it turns out a very well-known venture capitalist read this paper. I didn't know VCs read PhysRev A, but this guy has a Harry Weller. He had an undergraduate degree in physics, so he wasn't afraid of reading something like PhysRev A. He came to my office in 2014, and that's what he said. He said, "This thing reads like a business plan." We weren't thinking business at all, of course. And Jungsang Kim and I kind of told him, we're funded very well by IARPA. Thank you for your interest, but this is not going to happen. That just got him. He kept going, and eventually, of course, funded what became IonQ. And after he seeded us a few $1 million to get IP, to hire a CEO, he passed away very tragically. In his sleep, very healthy guy. So it was a very strange thing. This is 2016. We did form the company in 2017 and got a bunch of people. You might recognize some of these folks. A lot of them are physicists. And New Enterprise Associates and GV were the two VC firms that contributed. But AWS also started in the early days. And the big news, of course, a couple of years ago, the company went public. And now it's like 400 employees at IonQ. And their market cap is something like $2 billion right now. And what's remarkable to me, even just in trapped ion technology, if you look over the last 10 years or so, there's more than $1 billion, probably well over $1 billion, that's gone into investment, that's gone into this technology, trapped ion quantum computing technology. IonQ is the lion's share of it, but Honeywell and Quantinuum, that number is probably outdated as well. And of course, the government, this is just in the US. So it's been a kind of a, trapped ion quantum computing is not making a whole lot of noise. They're sort of in the background, but they're in an engineering phase for sure. Anyway, I just wanted to kind of point out that there are tensions. There will continue to be tensions because IonQ needs to sell systems. They need to sell hardware. They need to get their systems on the cloud. They've done that. But when you put a quantum computer on the cloud, it's not going to be the latest and the best one. It can't be, because it needs to be up 24/7. So it won't be improving. And we're in a steep slope of improvement right now, all around. But it's interesting, as IBM really proved, that having a cloud system is really exciting at the highest levels of the stack. How to learn to compile, how to learn to program in this different way. So it's important to put them on the cloud, but actually it turned out it was very important to put our systems on the cloud because it forced us to do the engineering to get our systems to work around the clock. or at least 90% of duty cycle. We have to turn them off every once in a while to tweak things up. But doing that is something we don't do at the university, and we're not taught to, and we shouldn't do at a university. And of course, like other companies, IonQ has partnered with many other commercial outfits that are interested in quantum computing. They're even paying to use our systems, our latest system, to do baby versions of algorithms that are of interest. And these are, I won't talk about any of these because none of them, all of these applications you can simulate on your laptop. But that's true in pretty much everything going on in this field right now. And the real story is of scaling. How do you scale? Now, I haven't talked about it yet, but when you have a single crystal of ions, you can get up to, you might ask, well, how come you only have 13? I picture of 80. Well, 80 is a pretty big number. We're not going to get 8,000 in a single crystal, but we can deal with maybe up to 100 in a single crystal with laser beams and so forth. But how do you get beyond that? One approach is to move atoms around between different zones in a single chip. Dave Weiland and I thought about this a long time ago, 20 years ago, and it's sort of a brute force approach. If you have two groups of 100 qubits, you can actually physically move atoms between those zones. You have to recool them. There's all kinds of technical issues. I would say Honeywell Quantinuum, which spun out of Honeywell, really has gone the furthest in this direction, making ring traps that allow atoms to fly around. Their architecture, they work with only 2 ions at a time, but they have a reservoir of up to, so far, maybe 30 or 40. I don't know what their latest one is. But they're engineering these geometries. I hinted at the other way to scale optically. And this is something I want to comment on for a couple of minutes. I know I'm running out of time. But in that paper in 2014, this large-scale architecture, we realized that this graph here, by the way, it's a fully connected 8-node graph. It's a crystal of 8 ions in a line. Now, one of them is a special atom. It's going to emit a photon. And with probability P, we collect that photon, and we do it twice, here and there. Now, the photon is entangled with the atom, its parent atom, either through polarization or other ways. And when we have a 50-50 beam splitter here, and we detect a coincidence event of the 2 photons on these 2 detectors, it turns out these 2 red ions are entangled. This is a very well-known so-called Hong-Ou-Mandel interferometer. And the rate of entanglement goes like P squared. And unfortunately, P can be pretty small. It might be 1%. And 1/2 tau. The tau comes from the attempt rate, and the 1/2 is that we make half of the Bell states. And so this was first demonstrated a long time ago in our trapped ion systems, and it's been reproduced in all the other optically active systems. And again, another picture of this modular architecture. It's easy to put pictures like this together on PowerPoint. A lot harder in the lab to do these connections. But the cool thing about this architecture, it is fully connected, even as you scale. And there's no other architecture I know of in quantum computing that has this. That's huge algorithmically. You don't have to swap and move information through a very sparsely connected graph. And we're learning in many of the superconducting architectures, as they make them bigger, they're less and less connected to minimize crosstalk. With optics, we're not going to have that. The real problem is this rate is really slow. I mean, even the gates between a node I mentioned are, or maybe I didn't mention, are tens of kilohertz, 100 kilohertz. Well, this rate is much slower than that even. And we've been working on improving that rate. This is, let's see, this is a speed in hertz over time for the last 20 years. The red line is sort of the gate speed of the Mulmer-Sorensen gates. I mentioned 10 kilohertz, maybe 50 kilohertz. When we started this in 2007, the rate was 10 to the minus 3 hertz, which is a really slow clock speed for any computer. But we knew the limits were we weren't collecting photons very efficiently. And very recently, we've hit maybe 1/50th of the rate inside. And by the way, this is Jungsang Kim next to the largest optical switch ever built when he was at Bell Labs. It was telecom photons, but the technology for making this modularized is out there. Groups, not so much us. Jungsang's group at Duke is doing a little bit of this, but integrated optics is something we haven't even started, which I love because that's going to give us even bigger gains in the future. But so going back to the university where we've, I think, done the best work on this photonic connections, this is an apparatus that you would only find at a university. It's an ion trap that has two very high numerical aperture A spheres in vacuum with 3D piezo controllers. So you can, it's not a cavity, but it passively collects 20% of the light up and down. And in this experiment, we sort of did a little trick. We trapped 3 ions. I'll tell you about the third one in a minute. But each of the 2 barium ions were centered on its A sphere. And we actually did photonic entanglement between the 2 ions. Even though they're in the same trap, they could have been in separate traps. And because we're collecting light so efficiently, we were able to realize about a 250 hertz connection rate. And that third ion was crucial because this third ion is a different species. It allows us to sympathetically cool the 2 ions, because when we're trying to make photons, the atoms recoil, they heat up, and they end up not forming a nice image. So anyway, you can't really see on the bottom there, you can't even see the archive here. But this is the fastest rate really in any photonically connected system. It's this dot here. We barely beat the Oxford guys from a few years ago. This is fidelity and rate. And again, we started way down here, this point here, low fidelity and really low rate. But you know, things are moving up. It's still slow. We still have work to do. Integrated optics is really going to help. Now, to get higher fidelity, you'll notice the fidelity is not even, it's 95% or something. To get higher fidelity, previously we used polarization encoded qubits, which have issues, especially with vacuum windows and going through fibers and noise. By storing the information in a time bin qubit, which is, I think professionals do, certainly if you go long distance, we can make an early or late photon, depending, it's a different atomic scheme, I won't get into that, but now the atom is encoded spin up early, spin down late, and we do the same type of interference, and this is much cleaner, gives us much higher fidelity. The one caveat is that the ions are moving, and they need to be in the same position for early and late, and so we have to synchronize the attempt rate with the trap frequencies. So we set all these to be integers. These are the 3 modes of motion of 2 ions, one there and one there. But we can do this. It's not that hard to do. And the preliminary data, I think we're going to do better than 97. It's a lower rate. It's not the same apparatus, but we think we can get well beyond 97%. And in fact, this architecture is also appropriate for QDITs, multi-level logic, where you can have any number of time bins. It's scalable. There's only 2 polarizations, but there's infinitely many time bins. And so Misha here, Shalev, raise your hand. You might recognize the name. He's sort of spearheaded our ideas of storing information in a metastable up to 5 or 6 levels, and shelving down here and making early, middle, and late photons, and showing QDIT entanglement in that system. So sorry, I know I'm running out of time, but you know, this cost per qubit is something that, you know, returning back to industry, that we really have to focus on. And while we are focusing on making things small, this is data, this is a picture, I think it's from ETH Zurich, but it might be Lincoln Labs, but there are some groups that are starting to integrate optics on ion traps. This is a big deal. It's just going to make things not just cheaper in the long run, but we're going to have higher performance, because the whole optical table will be on a chip, and the atoms are indexed to that chip. So when the truck goes down the street, the whole thing vibrates together, so the performance is even going to go higher. And so this is a big deal. This is really why I'm still bullish on trapped ions. You may have heard we have small numbers of qubits, but we have this roadmap. It's very clear what the roadmap is to get to levels where we can start to do error correction and then scale indefinitely. So you know, I spent a lot of time in Washington. I was here earlier in the week, unfortunately, lobbying for the National Quantum Initiative renewal. And the argument there is that building a quantum computer is probably not something a university will do. Industry is starting to do it, but you know, the engineers we need from industry, some of them don't believe in this black magic of quantum to begin with. So it's an interesting kind of divide. And I think, you know, national labs are a natural place that you might bridge this gap, and that's sort of what the National Quantum Initiative was all about. Now at Duke, we're actually trying to do what we can at a conventional university. We have several groups we have up to 6 trapped ion quantum computing systems at different levels of maturity that we can run algorithms on with collaborations. And the so-called green system is going to shuttle between 4 zones of up to 32 ions each. So this will be up to 128 qubits. Again, this is in the works. And we have 17 faculty. I should add one more here in the math department we just hired. Lots of trapped ion people. We have a couple of neutral atom people, Travis Nicholson and Hongchen Lo are joining us this summer to work on Rydberg arrays. These are optically active qubit systems, and we want to build them and explore the entire stack. So it's a little bit of an ad for, there's a lot of students here. Duke Quantum Center is a great place if you want to study algorithms at the very top, or even atomic physics of neutrals and trapped atomic ions. So my last slide here, we all know that we're always beyond the range where we can say something could not be done classically, we can do it with a quantum computer. We think we're very close. You only need about 100 qubits and 10,000 operations to not be able to simulate it. It doesn't mean it's useful. Useful stuff's probably deep into this pink range here. This is, by the way, the number of qubits, and this is the number of operations. Shor's algorithm is way up there. It's still out of bounds. But to get there, I constantly tell my friends in the intelligence agencies, they probably know this, that to get there, you have to get here. Because it's not because you're gonna inch your way up to there, but to get to here, it means that somebody will pay for the rest of the way. The current rate of spending in quantum, it will not pave the way all the way there. There has to be commercial activities like Moore's Law. That's why Moore's Law worked. There was commercial activity that paid the understanding of how to miniaturize silicon, how to do VLSI, how to do lithography, and all that. So we desperately need that in quantum. And with that, I guess I'll stop. Thank you.
Yeah, thank you for the great talk. Very interesting. Are there any questions?
So one question I had was related to like how to get industry excited about it. And are there any like intermediate applications with trapped ion that industry would be very excited about to like help build the technology and then, try to help get the quantum computing, further improved?
Yeah, absolutely. And this is true of, I think, all the platforms. We're currently running baby versions of algorithms that when we scale the hardware will presumably produce something interesting. And there's a lot of ifs in there in that statement. But our hope is that at least the structure of the programming, the compiling, there's a lot of black magic in that, and it will transfer over to a bigger system when we scale. So the only reason industry is interested is that there's a roadmap for scaling. Oh, yeah, good question. Boy, that to me, that's what makes it exciting. I will say, honestly, I have no idea. I don't know what the application. I'm quite sure, I won't prove it, won't be able to prove it, but I'm quite sure in 20 years, there will be, 10 years even, there will be use cases for quantum computing. I have no idea where they're going to be. I might say AI and machine learning just because I don't know what I'm talking about, like everybody in that field, because they're also heuristic. But when I look at image pattern recognition, I mean, you've heard the usual cliches of cat versus dog. That's one bit of information, cat, dog. But you have all these pixels, and our brain is able to pick out that one piece of information due to certain correlations, lots of them, shape of the tail, all that stuff. And somehow quantum computers should be able to capture that. But quantum computers, unfortunately, have very low bandwidth inputs, very low bandwidth outputs. So how do you don't upload the data, you don't upload pixels into a quantum computer, that would be way too slow. Somehow you have to, I think there has to be a different way to think about the problem. And I just don't know what that is. It's very exciting and it's frustrating that we can't come up with, concrete examples. I do think you've probably heard, about modeling ground states, chemical reactions, things like this. Those are niche applications. They're not going to pay the way for Moore's Law, but maybe if they get us over the hump, it'll get more people involved. I think we just need more people to think about these things and not think about quantum mechanics or qubits, but think about how to use these qubits. How's that?
I think in the end, Yeah, I think in the interest of time, we'll save questions for the break. We have an announcement right after this, but please let's thank our speaker one more time.
Okay, is it on? Perfect. So what I wanted to say is that I hope you're enjoying learning about successes in science and research and technology. And before we proceed to launch, I would like to remind you that behind any success is visionary leadership. And it gives me great pleasure to introduce our leader of our Elmore Family School of Electrical and Computer Engineering, Milind Kulkarni. Milind, please.
Thanks, Sasha. I do want to say that I am not the visionary leader. I just get to brag about the successes of our true visionary leaders, folks like Vlad and Sasha and Young and all the folks here at Purdue doing incredible stuff in quantum science and engineering. So unlike you guys, I was standing in the back and I could smell the food. And so I'm not going to take too much time so that I'm not keeping you guys from lunch. I'm sure you're all getting hungry. I just want to welcome everybody here to Purdue on behalf of the Elmore Family School of Electrical and Computer Engineering. I like to tell people that one of the really great things about the School of ECE here at Purdue is just how broad we are and how excellent we are in so many different aspects of what somebody might want to do in the areas of electrical engineering or computer engineering. And honestly, I think events like this one really emphasize that and really make that clear. I get to be here and talking because one of the names on that board over there is the Elmore Family School, but there's another name on that board you'll see there called the Emerging Frontier Center for the Crossroads of Quantum and AI. This was actually sponsored by the namesake of our school, Bill Elmore, because he saw in ECE here at Purdue the potential to do work that crosses disciplines and crosses boundaries in a way that we really can't do anywhere else. And so he with his support, we were able to bring together teams of folks on the quantum side of the world, Sasha, Vlad, and folks like them, as well as teams in the areas of AI and ML to really think about what we can do at that intersection. And I think that's what we try to do in ECE is figure out how we can bridge these boundaries between all of the different areas that combine to form our modern world to do really exciting things. And this summer school is one of those examples of what we can do when we put all of our resources together. One final thought I want to leave you with. So my own area of research is not quantum computing. I work in compilers and programming languages. But one really hot and interesting area these days in my field is thinking about compilation for quantum computing and programming languages for quantum computing. So I certainly encourage people to think about that. The obstacle I've always had when thinking about quantum computing is I didn't start thinking about these problems until much later in my career. And so it's much harder for me to wrap my head around all of the amazing details and complications and also fascinating aspects of quantum computing. You guys, the students in this room, are in a really fortunate situation. Thanks to the efforts of all the organizers of this event, you get the opportunity to kind of expand your horizons and expand your vision for what we can do when you're younger and your brains are a little bit more plastic and flexible than mine. So I really look forward not just to what the organizers in this room keep doing in the next years, but what all the students in this room are going to do in the years and decades to come. So thank you again for coming. And that's all I have to say before lunch.
Thank you very much, Milind. And I just would like to remind everyone that tomorrow we will also cover machine learning, neuromorphic computing, and beyond to connect it with quantum. Thank you, Milind.
Okay. Hello, everyone. We're going to get started in about 5 minutes. So Okay, so we're going to get started for our afternoon session. My name is Jeffrey Simon. I'm going to be announcing. Our first speaker is Eugene Demler. Eugene Demler received his PhD in theoretical physics at Stanford in 1998. He was a junior fellow in the Harvard Society of Fellows, became an assistant professor at Harvard in 2001, and a full professor there in 2005. In the fall of 2021, he moved to ETH Zurich, Switzerland as a full professor. Demler was a recipient of the 2006 Johannes Gutenberg Lecture Award from the University of Mainz. In 2015, he was the winner of a Humboldt Distinguished Scholar, Humboldt Research Award Humboldt Distinguished Scholar at the Max Planck Institute for Quantum Optics in Munich, Germany. In 2021, he received Hamburg Prize in the theoretical physics. His research focuses on understanding strongly correlated quantum systems from electrons and solids to dilute atomic gases to photons. His recent work addressed questions of unconventional mechanisms of magnetism and superconductivity, light-induced states of matter, many-body physics with ultra-cold atoms and optical lattices, nonlinear quantum optics, and quantum sensing and simulation. Please give a warm welcome to Eugene.
Thank you. It's a pleasure to be here, and I think the organizers, especially, kind of loud. We'll adjust it. Okay, especially Sasha and Vlad for inviting me. I'm happy to share with you some of the work that we have been doing, trying to understand the field at the intersection of optics and many-body physics, and probably some of you have heard about some of the interesting possibilities of light-induced states of matter, and I'll talk specifically about experiments on light-induced superconductivity. And I'll spend most of I want to begin by acknowledging my collaborators. So the beginning of my talk will be about light-induced Meissner effect, and here all the credit should really go to younger people, Marios, who is a postdoc at the Max Planck Institute, and Duilio, who is currently a visiting student in my group at ETH, and this was done in collaboration with Patrick Lee, and some of the all the work was also done in collaboration with Marios, Pavel, Sambuda, and John. And of course, what makes these theoretical studies very exciting is that we can collaborate with our experimental colleagues, and especially with the groups of Andrea Cavalieri and Rick Averett. So optics, of course, has a long history of being an important tool in solid-state physics, and the simplest problem that we all know is Fresnel light reflection, where we know that we can express reflection coefficient in terms of the index of refraction, which in turn can be related to dielectric constant and or conductivity. And in the last few years, and this is linear response. So in the last few years, people also started getting interested in nonlinear response. Say, our colleagues at Hamburg have been doing two-dimensional spectroscopy, terahertz frequencies of Josephson plasmons, which allow them to provide characterization of disorder of superfluid density. But in this case, even though it's not linear response, one can still treat a response of the system in powers of incident light beams. So what my talk is about is a kind of different regime of when perturbation theory doesn't apply, and this is something that agrees with our everyday intuition. If we want to study a person, we often find it useful to take them outside of their comfort zone, and this is more or less how people perform pump probe experiments. They identify frequency range in which one can excite the system very efficiently, and then look at properties of the transient state. And questions which arise when analyze this transient state is whether we actually achieved some interesting dynamical regime. For example, a popular picture is to say, well, imagine we have a free energy landscape, and by photo excitation, we take the system from a true minimum to a metastable minimum. Whereas another possibility is that nonlinear dynamics revealed something unusual about the underlying equilibrium state, and often it is very hard to disentangle the two. And I'll try to show you that, at least in the case of superconductivity, often simple interpretation in terms of local quasi-equilibrium state may be misleading. And I also want to point out that when we talk about pump probe experiments in solids, they have kind of a very natural connection to the subject of photonic crystals, which I know is dear to many people in these rooms. And although it is, I guess, most usually discussed in the context of optical frequencies, but the idea is that one needs to modulate index of refraction at frequencies comparable to the frequency of light. And these type of phenomena naturally happen in pump probe experiments because pump pulses, they excite collective excitations, and collective excitations in solids naturally have their frequencies in terahertz range, and then interrogation is also done in terahertz range, so we can think about properties of these transient states as systems which are oscillating at the frequency comparable to frequency of light which we used for probing them, and that's something we'll discuss later. Okay, so this is the outline of my talk. I'll first talk about, give you a couple of examples of puzzles that came up in experiments, and then I'll try to sort of provide you at least our perspective on these experiments. And the first one will be dynamical Meissner effect, and second one will be so-called light-induced plasma edges, and both of them have been interpreted as signatures of light-induced superconductivity. Okay, so let's start with just giving a brief review of experimental facts which motivated our study. Well, reminder maybe for people who sort of studied solid-state physics a while back, but didn't think about it recently. So what is Meissner effect? It's the kind of smoking gun signature of superconductivity that if one applies magnetic field in a superconductor, magnetic field is expelled. So it's kind of perfect diamagnetic response. What is important for us is to recognize that often, well, actually no realistic experiments, magnetic field is expelled from the interior of the system. Actually, the density of magnetic field lines becomes higher right outside of the sample just by conservation of magnetic flux. And as I said, like usually this is sort of like as kind of waterproof demonstration of superconductivity as it gets, but kind of within the last couple of years, there was a very striking experiment done by our colleagues in Hamburg who look at the material above TC. So this is in the family of high TC cuprates. I'll not go through the entire phase diagram, just say, well, okay, the function of chemical composition, there is transition temperature, and they're doing experiments basically from TC all the way up to room temperature. And they start the experiment by pumping the system strongly, by exciting phonons, IR-active phonons. We'll also discuss them later on, but for now, just sort of some terahertz light shining on the sample. And based on some earlier indications of light-induced states, they wanted to measure signatures of Meissner effect. But this light-induced superconductivity lasts picoseconds. So they have to do a measurement of magnetic field on these very short time scales. So the way they do it is that they actually use gallium phosphide as a detector of magnetic field. So angle of Faraday rotation is proportional to magnetic field experienced by gallium phosphide, and this measurement of the Faraday angle can be done very quickly. But they also want to make sure that the pump pulse doesn't do anything, doesn't compromise the gallium phosphide, and that's why they protect it from incident light by the mask. Therefore, if we think about some light-induced superconductivity, so like the argument, at least the scenario which they envisioned, is that it's only excited basically outside of the mask, and therefore they're measuring magnetic field sort of outside this region, which can go superconducting. And based on what we said before, well, in this case, diamagnetism should show up as increase of magnetic field, right? We're probing right outside of the superconductor. And indeed, they saw this kind of burst, an increase of magnetic field, which is quite dramatic. So if we compare static diamagnetic response in these materials, it's above TC, right? So it's not a superconductor, so it's just 10 to minus 5. But if we look at the kind of paramagnetic response which they measure, right? So they're measuring paramagnetic response, but they argue that this implies diamagnetic response inside the light-induced superconductor. So like this paramagnetic response, if we just take it at face value, it's 2 orders of magnitude larger than static diamagnetism. So clearly it's a very dramatic effect. Okay, so now let's talk about early experiments, and this is Josephson-Plasman edges, so I'll have to explain to younger people what we're talking about. So consider 2 superconducting layers, and we write dynamics of the condensate between the layers. So we can write standard equations such as that for the relative phase between the layers, time derivative of the phase is difference of electrochemical potential, right? Charge conservation, and that current is proportional to sign of the phase difference. So you can combine them all together and see that equations for the relative phase looks like the usual physical pendulum equation, and which corresponds to this collective kind of frequency. Notice that basically Josephson coupling is proportional to the square of the Josephson coupling between the layers. Okay, and so now what you can do, you can apply this knowledge of collective modes. Basically, we know our index of refraction. Okay, so you cannot probably see it from a distance, but if you look at the dispersion, you will see that that there is a finite gap in the spectrum, right? So below the Plasman frequency, there are no kind of polariton type modes, which you can think of as Meissner effect, right? Meissner effect doesn't penetrate, and the superconductor, and so if we're at low frequencies, it's kind of like a static system. And therefore, when one measures reflectivity, so at frequency below this lower Josephson-Plasman edge, reflectivity is 1, and then it suddenly drops. So that's the kind of Josephson-Plasman edge. And is commonly considered to be another golden standard of superconductivity that, let's say, if you don't see, like when you start seeing Josephson-Plasman edge, then the system really becomes a superconductor. But now let's look at the early experiments that have been done. Well, first of all, and again, the same type of IR sort of terahertz kind of boundary, like around 17 terahertz, like pulse sent into the system. And this is color coding of reflectivity. So before pulse arrives, you see this sort of Plasman edge, perfect reflectivity, small frequencies, then there is a drop. But then there is a new edge appears, and at sufficiently high frequency, and there was an interpretation that we have blue shift of the Josephson-Plasman edge, so by light we enhance superconductivity. And things are even more dramatic, again, in the pseudo-gap regime. So if one looks at equilibrium, reflectivity is just this dashed line, a very flat line, so nothing indicating that there is a Plasman edge. But after they excite the system, they see that the edge develops, which looks kind of like a Josephson-Plasman edge. But something, again, surprising is that the frequency at which appears is larger than kind of frequency that we have for Josephson-Plasman edges at 0 temperature in the same material. So if it is light-induced superconductivity, it is some dramatically strong light-induced superconductivity. Okay, so what we'll try to do now is think about explanation for this experiment and whether we're really dealing with a new light-induced state. Okay, so we start with the Meissner effect, and this is, okay, basically what we said before. They apply static microtesla field. They sort of get a response of the order of millitesla. And this is, if we look at the temperature dependence of this response, it disappears essentially at room temperature. right? So it's really high temperature phenomenon. Okay, so I need to bring up one more fact which will be crucial for our discussion, and this is in the context of Josephson effect, and this is the idea of Josephson vortices or solitons. So we know that the coupling between the layers is cosine of the phase difference. And therefore, the minimum of the relative phase corresponds to 0 or to pi, just a multiple of 2 pi. And then we can consider, therefore, we can have configurations where the system sort of makes a domain valve between two of these minima, let's say goes from 0 to 2 pi. And if we just look expressions for the tunneling current, we immediately see that this corresponds to transverse current changing directions. And of course, charge has to be conserved, so we're getting a current loop. So that's basically, that's why we can think about it as a vortex. So there is some magnetic field sort of generated in the system when there is such a vortex configuration. And there is a characteristic length, which is called Josephson length. Okay, so okay, we talked about Josephson plasmons. But in the real world, in the case of YBCO, there is another subtlety that actually unit cell has two layers, and coupling within bilayer is much stronger than coupling between bilayers. So we have a ratio of Josephson frequencies, which is 10, which means that the ratio of Josephson couplings that we discussed is the square of this. So it's actually 100. So we have 100 times stronger Josephson coupling within bilayer than between bilayers. And now this raises a kind of an obvious suggestion that actually in this material, when superconductivity is destroyed, it simply means that we no longer have we sort of lose coherence between bilayers. But within bilayers, we have such a dramatically strong coupling, we may still have appreciable superconducting correlations and locking of the relative phase. Therefore, if we think about the phase in each of the layers, it's actually fluctuating, but you see that the phase in its companion layer is fluctuating the same way, so that the phase difference is locked to 2 pi times an integer. And the first question you can ask, okay, well, is this model consistent with the small diamagnetic response? We're saying that there is still some residual superconductivity. So the static Meissner effect is when we apply magnetic field, and then we have to have currents like flowing through the entire system to screen this magnetic field. In this case, the system is broken into these bilayers, and therefore we can only get sort of tiny currents within bilayer, but we cannot have currents flowing through the entire system. So if one writes the usual kind of London equation and Maxwell equations which describe dynamics of magnetic field, you can recognize here, let's say, some simple limits. If everything is static, so then we just get this equation on magnetic field, which leads to exponential decay. That's the London equation in the static material. Or if there is no superconductivity, which means this basically lambda goes to infinity, we just have some propagating light inside the material. And of course, like with superconductivity, we get a gap. So now we have to generalize this equation to the case of our bilayers, because even though we're saying that there is no Josephson coupling between bilayers, there is still capacitive coupling. They're still coupled through Maxwell equations, and one can show that these are the kind of equations that we get on magnetic field sort of within bilayer and between bilayers. You can see that the term which looks like a Meissner effect, this 1 over lambda square, is only for the part of magnetic field which is within one bilayer. And so now one can solve the static regime of this equation and find that actually the kind of screening field that we find is of the order of 10 to minus 5. So it's kind of reasonable. It's what we know is the case experimentally. Okay, and now we ask, so what is actually happening in the driving protocols? So, okay, now we extend the equation that we had before, like physical pendulum, which is add spatial gradients, and I'm focusing on a single bilayer. And we also add static magnetic field, which sort of adds some kind of phase winding between the layers. And there is also incident light. Again, with the same Josephson relation, it makes the phase to wind. Then we also need to impose boundary condition, and the simplest boundary condition is to say, well, that there is no current flowing through the edge. And now let's just talk about the numbers. So static magnetic field is very tiny. Okay, we'll quantify it later on. It's so happen that they drive at frequency which is near resonant with the Josephson-Plasmon. But what's most dramatic, if we convert this strength of the pulse into kind of phase winding, even though distance between bilayers is just angstroms, actually the phase winding during the period is of the order of a few pi. So in fact, when they used kind of the largest light intensity that they had, they actually damaged their sample, so they had to scale down. So while looking at the Sine-Gordon model, driven way out of equilibrium. So what happens to the Sine-Gordon in this regime? So let us kind of, okay, just a technical trick. We move to the phase which winds with external magnetic field. Then equilibrium has the following profile, kind of in the bulk, this sort of I tilde is uniform, and then there are just slight deviations at the edge, which basically describe the small screening currents that we discussed before. Now we can also introduce kind of the net winding of this phase, which, as you can show, more or less corresponds to magnetic field, the net magnetic field sort of generated by the screening currents. Okay, and now what we do, we just look, let's just start with the static configuration and subject it to uniform AC drive. And you know, naively, uniform AC drive shouldn't do anything, it's not clear why it should make a gradient of the phase to go to the right or to the left. In fact, if there was no static magnetic field which create this tiny kind of like currents at the edge, like the system would evolve completely symmetrical because we don't know like which way the current should flow, left or right, up or down, because we have these rapid oscillations. But interestingly, what we find is that this tiny breaking of the symmetry by introducing this sort of tiny edge, and actually another way of thinking about this, if you just look at this kind of phase profile, it should remind you of these vortices which we talked about, except that these are very tiny fractions of the vortices of the order of 10 to minus 4. But then what happens after this strong pulse arrives, we actually amplify these tiny vortices by 2 or 3 orders of magnitude. So basically, you can think about it as some kind of like a vortex ratchet, even though we're moving up and down, but there is like a tail of the vortex, and it sort of gets sucked into the system. Okay, and then you can actually look at, so what's the amplification that you get, and you can easily generate kind of amplification, like even if we take a relatively early time, amplification of the flux, amplification of the screening field can be as big as like 2 orders of magnitude. If we look closer to the peak, it can be 3 orders of magnitude. And as I said, like, you can think about it as taking a tiny tail of the vortex and actually almost generating a full vortex. Okay, well, so where does it come from? So actually, sort of the first reference to somewhat related physics that we came across was the paper discussed in the context of cosmology by Starobinsky et al. So they looked at the Sine-Gordon model and asked the question, it's like a field theory extended in space, let's sort of move the system from its equilibrium at a uniform way, and then release it. So it will start oscillating. And naively, it would just start oscillating uniformly. Nothing breaks translational symmetry. But then they consider small fluctuations on top of these uniform oscillations. While now, for the small oscillation, this is some kind of time-dependent background. It's a Fleckier system. And they recognized that the system is unstable. Like small perturbations will grow exponentially, which means the noise quantum noise in their case will be amplified exponentially. And they actually connected it to kind of reheating scenarios after the inflation. This subject was later taken up by people interested in cold atoms, but they also considered this situation when you just create an initial configuration in which the relative phase is not at 0, but let's say displaced, and then it starts its own dynamics, sort of not driven by external fields. And they found that actually one can go beyond this analysis of early time and actually show that what develops is breathers, and for very sort of strong amplitude of oscillations, even solitons. And in our case, in a sense, we're sort of looking at these oscillations, but amplified because they're driven by this giant AC field applied to the system, and therefore kind of all these sort of instabilities, they become stronger. And what we're amplifying now is not this kind of quantum or thermal noise in the system, but rather these initial vortex configurations which were present at the edge. And we, as I said, can make, like from these numerical studies on the Saint-Gordon model, it's clear that we can make them larger by 2 or 3 orders of magnitude. So we can look at the numbers and kind of basically for the type of external magnetic field which they apply, the type of drive, like try to get the numbers of what would be the field that's measured. But here I have to add another fact. One thing you can sort of complain, well, you can point out is, look, I'm saying that everything interesting is happening at the edge. But if I have a bulk sample, well, I will get some kind of big field at the edges, but I'll not get a bulk field. Well, as you know, like solid state physics was called by some people solid state physics. So indeed, there is a lot of disorder. In fact, our experimental colleagues tell us that if we think about YBCO, we should really think about it as consisting of domains of the order of 10 microns. And therefore, in this mechanism, essentially these kind of current loops will be generated on segments of the order of 10 micron each. And if we then sort of take this flux density that gets generated by this mechanism and convert it into this density of domains, we get something which is sort of somewhat larger, like by an order of magnitude larger than the field that they measured experimentally. Well, okay, there are many reasons why, you know, in the real world effect can be weaker. So actually remember I told you about the mask, and in fact, like when estimating, I did analysis taking electric field right below the irradiated region, but in fact measuring sort of below the mask. But of course, light does not propagate on a straight line, right? There is diffraction, and in fact, if we estimate the kind of suppression of the electric field, sort of how much the system will see below the detector, it's also of the order like about a factor of 10. So that could be a big, one of the main reasons for why, let's say, our estimate is larger than what was seen in experiments. Okay, so now let me start talking about the second part, and this is Josephson plasma age. But for this, let me first introduce some kind of general concepts of how to think about pump probe experiments from the Flaquet perspective of photonic time crystals. So, you know, okay, the type of optics that a condensed matter person can do is just think, well, I have incident light and then transmit it and reflect it. And the way we think about it, we just have to find the wave vector, right, of transmitted light. And once we know the wave vector, we can compute sort of electric and magnetic field, write boundary conditions, and by matching boundary conditions, we can express reflection coefficient. So, nothing very fancy, and of course, like all this wave vector of light, of polaritons propagating in the system is expressed in terms of index of refraction. And now what we can do is say, well, let us take phenomenological model that index of refraction is not constant, but it's oscillating in time. And now let's ask, well, so as we saw previously to solve a Fresnel problem, the first question that we have to ask is, what are polaritons inside the system? And when index of refraction is not constant in time, there is frequency mixing, which is well known for people thinking about, let's say, photonic time crystals. But let's say for me, it's probably more physical to think about it as some kind of parametric resonance, that oscillations in the medium, they are generating pairs of excitation so that together they adapt to the frequency of the dry field. And so what this means is that when we write equations of polaritons, if we want to include this effect, like this parametric driving of the system, we have to write coupled equation now on the amplitudes of electric fields at two frequencies, which in the language of quantum optics are usually called signal and idler. And so one then have to, let's say, if we think about eigenmode, now it will be an eigenmode that has a certain momentum, but then it will have two frequency components. And of course, the strongest effect of parametric driving will be when signal and idler also sort of have the wave vectors match, and typically this just corresponds to when the frequency is half of the drive frequency. And now what you can do is just generalize, solution of Fresnel equation by saying, well, kind of the type of eigenmode which propagates inside the system has not just one frequency, but two, but I can still write the same type of boundary conditions. And so our original expectation was that what we get is something which is very sort of dependent on the details, but what we found is that actually the answer turns out to be quite universal. And but also somewhat surprising, because when you have parametric driving, you somehow naively expect, oh, we'll always get amplification, right? Because of the drive, we're pumping some sort of generating new energy in the system. But it turns out that there is a competition between drive and losses. So when we have strong drive and very small losses, indeed, we get extra kind of enhancement of reflectivity. We can, in some cases, we can even get lasing or at least amplification. But when losses dominate, we get more subtle shapes. In fact, some of them look like Fano edges. I'm sure most of you remember this idea of Fano, that if we are looking at sort of driving a system of two harmonic oscillators, and one of them is overdamped, and then if we look at the frequency dependence absorption of energy, then we can see that sometimes, like absorption by the two oscillators, it can be sort of interfere constructively or destructively, and when it interferes destructively, we can get edges. So in our case, you can also think about these sort of two channels, but these two channels signal and idler, and they can also interfere constructively or destructively, and in the case of destructive interference, we get these edges. Interestingly, we even get some EIT type structures in between. Anyway, so now what we can do is we can simply take this simple model and ask whether it can explain all this phenomena in YBCO, appearance of the new edge above TC and appearance of the edge-like structure below TC. So, okay, first of all, where does the drive come from? As I said, like in this experiment, they like to drive phonons, and these are so-called special phonons which move oxygens in the direction perpendicular to the layers where superconductivity lives. And it so happened that there are two of them. Also, there was some sort of, in the beginning, confusion, but I think by now it has been more or less sorted out that in order to see at least this Josephson plasma and H-type features, they have to drive both phonons simultaneously, and therefore, what is driving actually the system at low frequency we can think of as just the difference of the two phonons. And now what we can do is just say, well, now let's assume that we have our Josephson plasmons, but in addition, we have this drive coming from this beating of the two phonons. And in the superconducting state, Josephson plasmons are very sharp. They have very small losses, and immediately we will get kind of this peak, which we discussed before, right, due to parametric driving, which is exactly this high energy feature. And so the energy of this drive has nothing to do then with the kind of frequency of Josephson plasma, just has to do with the frequency of the phonons that have been excited. But what is more interesting is that when we take the state above TC and say, well, let's assume that Josephson plasmons still remain because we have short-range correlation, but they're so overdamped that, like in the normal state, we don't really see an edge. We actually just see some kind of like a smooth background. But now we will have this drive, and we'll just use our general scenario. Again, just by going through this calculation, we find that the induced changes in this case of overdamped Josephson plasmons, they have this sort of shape, which is very similar to what was seen in experiments. So in fact, like, so this is comparison of the theoretical model where we take sort of phenomenological, we don't try to derive from first principles, let's say how overdamped or underdamped Josephson plasmons are. We just make this reasonable assumption. They're underdamped below TC, and then they're present but overdamped above TC, and we choose parameters just to match what we know about equilibrium reflectivity, but then we sort of get the same shape of the driving induced changes in reflectivity. Okay, so with this, I'm sort of concluding, and I think I try to give you an examples, actually more studies. It's a very active field, but at least to give you a flavor of the type of experiments and theoretical sort of thinking that goes along with it about what is happening in this sort of light-induced phases. And hopefully, okay, sort of my main message comes across that at least in this case, we do not really have to assume that there was some mystical new light-induced phase created by the pump pulse. However, there is a very strong evidence about residual strong superconducting correlations, which by itself is super exciting. So like say this Meissner effect then tells us that at room temperature, there is still equilibrium superconductivity. It's short range, but we still sufficiently strong superconducting correlation between bilayers that we can talk about the Saint-Gordon type dynamics. So it's not light-induced phase, but from these pump probe experiments, we learn something quite important about the underlying equilibrium state. Thank you.
Does anybody have any questions for our speaker?
Thanks, Eugene, for the very nice talk. So I wonder this, on the drive, if you can define a enhanced TC, if it can be defined.
Well, they see where this Meissner, again, technically, okay, I don't like calling it Meissner because what they are really measuring is anti-Meissner, right? You see magnetic field generated in the direction of the applied field.
Right.
And they see that it disappears around 300 Kelvin. So I think that we could, and it basically is the same pseudo gap temperature.
I see. So this, okay, so it actually, the dope, basically I'm wondering the doping dependence of this phenomenon tracks the pseudo gap line instead of a dome shape like TC.
I'm not sure they have done, thorough studies of doping dependence, but what they have seen is that it's definitely way above TC. Like for that sample, TC was 50 Kelvin, they saw it up to 300. But again, maybe it's something I should emphasize. So the kind of biggest difference in interpretation, right? So if we hope this, well.
Okay, we have one more question back here.
Okay, yeah.
Oh, you can go ahead. Go ahead.
No, that you see, like the picture that suggested, like by experimentalists, is that there is diamagnetic effect in the bulk, and as a result, they see this paramagnetic effect field going in the direction of applied field. Whereas, like from our model, no, you actually get paramagnetic effect everywhere, including in the part. What's that? Within bilayer, that's very hard. You're welcome to try it. So far, nobody has done it.
This is indirect. In other words, okay, let's say you don't know the explanation, but increase show it's a superconductor.
I'm not saying it's a superconductor. It clearly is not.
Cavalieri didn't show that to me. What you can talk about is not experiment. Experiment is show anti-Meissner. That's it.
Oh, and now, but you see, now we provide an interpretation saying that you can explain it by residual equilibrium superconducting correlations. Now, it turns out that they can be fairly short range. They didn't go into many details. What is important for our purposes, I talked about Josephson length, but in this kind of weird case, it turns out that it's very tiny lengths, like tens of nanometers. So if correlation length decays of tens of nanometers, that's enough for us to see this dynamics. So it may be fairly short-range superconducting correlations, but they will be enough to see this.
Combination through interpretation. It's not really, I mean, experiment if you want to claim superconductivity. One should show superconductivity per se. It's a bit, so that's my view on this. When you want to claim an experimental claim, you should measure what you claim. It's model dependent.
Okay,
no, what I'm saying is that
the
interpretation is model dependent.
But you see, my interpretation is opposite from interpretation of the experimental team. So at least they're doing very fun things, which we're trying to understand. And this actually motivated us to find new nonlinear regime of the Sine-Gordon model. Like we looked into it and nobody has ever discussed it. Like in the case of Josephson-Jachin, just nobody thought about this strange regime of applying these giant voltages and having like tiny vortices.
Okay, let's thank our speaker one more time. Okay, while we're getting set up, I'm going to introduce our next speaker. Eugene Polzek is a professor of physics at the Niels Bohr Institute at the University of Copenhagen. He is the leader of the Quantum Optics Center, Quantop, and the director of the Novo Nordisk Center for Biomedical Quantum Sensing. His research interests are within quantum physics of matter and light, and quantum communication and quantum sensing. Among his notable results are the demonstration of quantum teleportation between material objects, a quantum memory for light, generation of entanglement between distant material objects, a quantum optical interference with ultra-cold atoms, and measurements of motion in fields not restricted by the Heisenberg uncertainty principle. Eugene Polzek has published more than 180 papers in referee journals, including a number of papers in Science and Nature journals. He is a member of the Royal Danish Academy of Sciences, Fellow of the American Physical Society, and Fellow of the Optical Society of America. Eugene Polzek is the Knight of the Order of Dannebrog, a recipient of the Herbert Walter Award of Optics, Society of America, and German Physical Society, and Gordon Moore Distinguished Scholar Award, the Scientific American Research Leadership Award, and the Danish Association of Academics Award. Let's give a warm welcome to our speaker.
Well, I have to retire, otherwise I won't have any time to give a talk. Everything will be taken by the introduction. Thank you very much to Sasha and Vlad and other organizers for inviting me here. And I'm sorry that the screen is small, but let's use a larger font. So entangled sensors for biomedical applications. And I believe it's the first time I give a public talk with the title Biomedical Applications. And the reason is very simple. The reason is called Novo Nordisk Foundation. And this reason is worth $20 million. So this is a new center that we're about to launch. Actually, we launched it a month ago. And it's called Copenhagen Center for Quantum Biomedical Sensing. It's a collaboration of my group at the Niels Bohr Institute, University of Texas in Austin with Mark Reisen, and Danish Technical University with Ulrik Andersen. And it is essentially the attempt to employ entanglement between atoms and photons towards biomedical sensing and cure of the disease. And you know, there are three reasons why the society is interested in science: military, health, and entertainment. And so we decided to concentrate on health. So I will be talking today mostly about the research at my group, and that would be applications of atomic entangled states for biomagnetometry, something about entangled light and its applications, and other things about atomic sensors. So, yeah, quantum technology we all know and love. There will be quantum cryptography. There is some quantum cryptography machinery around nowadays. And there is quantum computing on the horizon. There are some beautiful results which involve from a very few to a very large number of qubits. And then there is a quantum sensor, and the more qubits, the merrier, essentially. And the point is basically to understand that if you want to do quantum sensing, then you have two options. Either you can take a few qubits and make a super entangled state, or you can take a gazillion of qubits and make them weakly entangled. And you have to choose your poison and decide which of those two approaches works best. And so we're concentrating on kind of both directions, but this is probably the leading one. Okay, so measuring fields. Arguably, most interesting fields for many applications will be electromagnetic fields. And you want to measure magnetic fields from brain, heart, nerve, whatnot, and you use a spin. And we use in our work large collective spins. So you have this spin, and this spin is doing some motion as a result of those fields. And the name of the game essentially is to see whether you can measure this dynamics of the spin if it is within some quantum uncertainty. And what this quantum uncertainty is, I will tell you about in the next few slides. But of course, the basic of it is that we have the commutator and the two transverse components of the spin. They don't commute, and therefore you have the limitation on the signal that you have. And I put standard quantum limit in quotes because there are many notions of standard quantum limit in this business. I'll walk you through some of them. Okay, so that this lecture is not completely wasted, let's look at some famous example of quantum limits. And Heisenberg microscope. So it has nothing to do with measurement of the fields, but it gives you an idea of the balance between the measurement precision and the disturbance that you put on the system by this measurement. So you want to observe the position of the particle. One way to do it is to scatter a photon. You scatter a photon and you measure a photon and the particle flies away. But of course, those are also waves. Therefore, you essentially have to consider the uncertainty between the position and the momentum. And if you put those things together, you arrive at the standard quantum limit for the trajectory of the particle. And very similar standard quantum limits exist for measurements of field perturbations, of spins, for instance. So let's get a little more specific. We have a sensor, and this sensor is sitting somewhere here, and it is a collection of atoms. And in many applications, it's actually worth it to make measurements at the AC measurements. You know, for instance, I will talk about several medical diagnostics which are relying on measurements of AC magnetic fields. In the end of the day, if you think about it, you know, your brain signals, your heartbeat, it is all AC things. All right, so how do you measure AC signals? You want to use some kind of a resonance. So what you do is you have this sensor and you subject it to the field that you want to measure. And at the same time, you put a DC magnetic field, so the spin begins to oscillate at the frequency of interest. And then you have like a resonance enhancement to your signal. And how do you measure this dynamics of the spin? Well, for instance, you shine light. And of course, if you shine linearly polarized light, then this linearly polarized light will experience rotation of its polarization simply by the Faraday effect, because the spin is oscillating, and you measure those oscillations and you figure out the dynamics of the spin. Now, what would your limits be? There is a quantum noise of the light itself. You can use light in the coherent state, you can use light in a squeeze state, an entangled state, there will be quantum noise. The object, which is the spin, of course, also has its quantum noise, the uncertainty of the spin direction. There is a quantum back action of this measurement on the spin, and we will walk through that in more detail. And there is a quantum back action of the spin back on light. So there is a lot of interesting quantum mechanics going on, and as a result, you measure some quantum noise signals, and then you try to mitigate them. So let's look at this story in a little more detail. So once again, we have this large spin in magnetic field. So now I'm looking at it from the top. The magnetic field is orthogonal to the figure. The probe propagates like that, and I measure the Stokes parameter of the probe, which is just the polarization rotation. And normalize it so that it will be a normalized standard, P component of the light quadrature, just renormalize Stokes parameter. Okay, so if there is a magnetic field, then this spin, which let's say initially was looking in some direction, and we can define this direction again as a projection of the spin normalized to the square root of the length, and then it becomes the natural x component, and we can have the p component, which is orthogonal to it. The point is that because of this magnetic field, the spin projection will be oscillating around the magnetic field, and therefore in the first instance, if you measure the projection in this direction, then you put the back action in the orthogonal direction, and you keep doing it, and the more you measure, the more you see the quantum back action of the measurement. This is the first thing you want to do in the experiment, because that means that you are in the quantum noise dominated regime, and now you can start playing tricks with it. So the result will be that the polarization of light that you will measure will have the noise which is due to the short noise of light. There will be some signal, and then there will be a back action of light on the spin with some measurement rate as the projection. Okay, so those are really the bare basics. And let's now look at the system that we're using and what we can do about it. So we are talking about an entangled state of a large number of spins, 10 to the 9, it can be more or less, but it's definitely much more than 1,000. And only very special types of such states can actually survive. You think of the maximally entangled state of 10 to the 9 spins, it will not survive for an attosecond, of course. So high symmetry helps. Single mode squeeze states is a good example because they are highly symmetric. Two mode squeeze states, that is Einstein-Podolsky, Rosen, and Dangle, are also nice. And you can also think of Fock states, but the Fock states which are embedded into a collection of the spins. So you think about it as a single excitation of a spin motion, which is distributed over a large number of spins. And that would be a good example of the long-lived symmetric entangled state of many spins. So this is one of our platforms. It is actually a thermal ensemble of cesium atoms contained in some special environment with some beautiful engineering of this whole system. But the important thing is that the spins are in gas phase. They run around like crazy at 200 meters per second. They collide with the walls of the cell, and if we wouldn't do any tricks, then the spin state will be ruined in no time. So we use some special coatings of the cell walls, and the spin protecting coating of those walls prevents collisional decoherence. If we want to generate some nice collective atomic state, then we need to erase which-way information, which means that we need to couple light to all the spins in equal fashion. Motion helps a lot because motion does the kind of erasing of which-way information. And as I said, the lifetime can be quite significant. The lifetime of a quantum state can be a second or even more. So for all practical purposes, we can think of it as a single spin containing a lot of atoms and so on. A little more details. So one of the examples is with cesium atoms. We take two hyperfine states of the cesium atom, sorry, not two hyperfine, two magnetic sublevels of one hyperfine state, and we initialize all the atoms in one of the MF states, and then the excitations will correspond to collective jumps from M4 to M3. And you put the magnetic field in, and then the atoms move around without decoherence. And this is the example of a single excitation. And if you want to generate, for example, a squeeze state of this collective system, then it will be some superposition of 0 here, 2 here, 4 here, and so on, as any squeeze state is generated. Okay, so a little more about the quantum back action of the measurement. We take linearly polarized light, we put it through this, we measure the atomic spin, we take a measurement. And what we measure can be decomposed into the cosine and sine components of this rotation frequency. So you can write in the laboratory frame, you can write the projection of the spin on the axis of propagation of light through rotating frame cosine and rotating frame sine, and those two are non-commuting variables and therefore cannot be measured simultaneously. So the result, as I mentioned, you have the back action noise, and this is the experimental result where your measurement is completely dominated by the quantum back action of light on atoms. Okay, so what can you do with such a thing? You observe this quantum back action, but the point is actually that this quantum back action can be made correlated with the noise that produces this quantum back action. So if we're looking at this equation where we're measuring a certain quadrature operator of light going through, and in this case, this operator and this operator are uncorrelated. But if we start measuring a little different quadrature, and that can be done by some wave plates, then we can actually generate correlation between the measurement, between the noise of the light and the back action. And we can engineer the correlation, so measuring some different quadrature from those pure quadratures, you can engineer this correlation in such a way that, there will be a sine of this quadrature angle and cosine of this quadrature angle here, and this sine can be negative. And if sine is negative, then you will have the noise reduction here of the whole thing. So by engineering a correlation between the measurement induced noise on your system and the noise of the light itself, you can reduce the overall noise of the measurement. And yeah, this can be negative. And as a result, the light which goes through can be super squeezed. So from this relatively simple system of room temperature atoms, well engineered and this and that, we can generate on the screen, we generate 9 decibel of squeezed light. And if we correct it for the detector inefficiency, this is about 12 decibel of squeezed light from a relatively system like this. And interestingly even, if you do this measurement fast enough so that the gamma, the readout rate, is larger than the rotation frequency of the spin, which is the Zeeman frequency, then you can actually generate a non-classical state of light spanning all the way from the frequency of the spin oscillation down to almost very, very low frequencies. In this case, it's, what is it? It's below 10 kilohertz, and it can be even lower than that. So one of the outcomes of this research is that we would like to make a shoebox low power consumption source of 10 dB of squeezed light. Let's see if this would be possible. You can concatenate those interesting devices. For example, you can use one of them as a squeezer and the other one as a sensor. And in this case, so far what we have observed is the reduction of the back action, but we can also try to reduce the shot noise of the input probe by using another source as a squeezer. And in this way, you can improve the signal to noise even better and achieve nicer resolution. Okay, so what can we do with those things in terms of the biomedical applications? One of the early experiments was actually to measure heartbeat of a poor hamster. And we actually figured out that using those atomic spin sensors, we can nicely observe the heartbeat. And if we improve the sensitivity by squeezing of the spins, then we can do it better. Something like that. So the heartbeat is rocking the spin, and if you squeeze the spin state, then you can measure this than if you don't. All right. One of the future directions that we want to pursue possibly is the so-called memory-enhanced distributed sensing. So imagine that, so it is known that the efficiency of sensing can be improved if you have a memory for a quantum state. You can think of it as a combination of sensing with teleportation to the memory. Now, the point is that the memory, atomic memory, only wants to talk to certain colors of light, whereas your sensor may want to be on a coupling to a different wavelength. For instance, if you want to do distributed sensor, that can be a telecom wavelength. So instead of using one and the same light on both, you have to use entangled light. And we have ventured for more than one reason to generate entanglement between very different colors of light. And this is the result. So this is not the telecom yet. This is the entanglement between the cesium wavelength 852 and 106, because we are also interested in helping our colleagues who are looking at gravitational wave detection, and they're using 106. But anyway, the principle is the same. One can generate very highly entangled. Those are preliminary numbers published some time ago. By now we have close to 10 dB of entanglement between colors which of two different colors. And the point is that this entanglement can be maintained down to the acoustic band of the noise that you want to measure. And the acoustic band is where a lot of life kind of threatening situations happen. Okay, so this is one component of this distributed quantum sensing. The second component is that we have to have our spin memory working in the quantum regime all the way down to acoustic frequency range. And this is something that we have also achieved. So here you can see the result of quantum behavior around 18 kilohertz, and we can do it nowadays much lower than that. And so eventually the plan is to combine the spin memory with two entangled light modes and couple the sensor to one of those modes, couple the memory to the other entangled mode, and then combining the results of this detection and this detection, try to teleport the state of the spin memory on the sensor the other way around, and in this way enhance the sensitivity. I'm changing gears to tell you about one more rather interesting method of quantum sensing. So typically, if you want to achieve quantum limit of sensitivity for a large system, you want to go to higher frequencies. Because at lower frequencies, you have a lot of technical noise. Technical noise grows as a square of the number of particles. Quantum noise goes linearly with the number of particles. So the more particles you have, the more difficult it is to be dominated by the quantum noise. So this magnetic induction tomography is a method for measuring super low conductivity in objects by using rather high frequency magnetic fields. Why do you want to measure conductivity? Well, there's more than one reason why you want to measure conductivity, but for us, the driving force is essentially that if something happens to your internal organs, for instance, to your heart, then the conductivity of the heart changes. And nowadays, they use wires that they put inside you to measure the conductivity between different parts of the heart. We want to do it externally without cutting and sewing back again. Yeah, so how is this done? The magnetic induction tomography method is well known. Our contribution to it is that we turned it into the atomic magnetic induction tomography and used entangled states to improve the sensitivity. So imagine you have two anti-Helmholtz coils, and now you put my collective atomic spin in between. And if they are perfectly balanced, then there is no AC field here, and the spin precesses only because of the quantum noise, so it doesn't move like that. If you put an object which is closer to one of the coils than to the other one, then there will be an induced current in this object if it's weakly conducting. And this induced current will affect this field more than this field, and therefore there will be misbalance on the point of the sensor, and so your sensor will begin to sense something. And as I told you, we can measure the tiny motion of a large spin sensor by using light and going beyond the quantum limits and so on. So that's the method we want to investigate in terms of detecting beyond the quantum limits. And we started with just, forget about the entanglement. Let's try to do something to demonstrate that we can measure interesting stuff with our atomic magnetometer. And what is interesting stuff? Well, interesting stuff was, can we measure the presence of a cubic centimeter of slightly salted water? And slightly salted water is what you are made of, and I, and everybody. So if we can measure the presence of slightly salted water, then maybe we can actually identify the difference between the healthy tissue and unhealthy tissue, because they will have slightly different conductivity. And so this is the kind of this magnetic induction tomographer in schematic cartoon. This is the atomic sensor, and those are the coils, and this is the sample, and you move the sample around and you measure its presence. So a little more detail on how you do it in a way where you overcome the quantum back action. So this is your spin, and you want to measure the trajectory of the spin. And as I told you, if you have a sample that you want to measure, then the spin begins to oscillate. So the spin oscillates. I'm looking now from the top in this picture. And if you would be measuring it continuously, then you will be piling this back action more and more and more, as I told you some time ago. You don't measure continuously. You measure stroboscopically twice per period. And in this way, you measure this projection of the spin, and then you don't measure. And then when it comes back half a period later, you measure it again, the same quadrature. And so you are creating the knowledge about one projection of the spin along this direction, and you put all quantum back action in the other quadrature. And in this way, you generate the spin-squeezed state, which has the uncertainty of one quadrature less than the other one. So you do this probing in a pulsed fashion, and so you engineer entanglement between those 10 to the 9 atoms, which creates the spin-squeezed state. And lo and behold, you cancel the back action of light, and this is the result. So what I'm showing you here is our sensitivity to the position of this sample. So you want to be able to identify the position of, in future, the defected part of your heart, let's say. So how well can you identify it? Well, the blue points here are without entanglement, just for coherent state of the spin, and the red points are with the spin squeeze state of the spin. And you believe me that there is a significant improvement in the spatial resolution, which we achieve by engineering this entanglement. Right. So this is just to show you that our sensitivity is sufficient at the moment to distinguish different kinds of tissue. There is another thing which I don't have time to talk about, which is probably the closest to real world applications. So if you need to have the MRI scanning done, then you are put through this machine, and within this machine there is a huge gradient of the magnetic field, and because of this gradient they can figure out what's happening in your head. The point is that as soon as you move your head inside this machine, your very presence changes the field. And also, if you begin to move a little bit, or there is some heartbeat or whatnot, all those tiny changes, they are not tracked by the system because it's a superconducting system. And everything that they track happens at a certain distance from your head. What we can do is we can take our room temperature atomic sensors and put them on top of your skull, and in this way we can measure the corrections to the magnetic field gradients and hopefully improve the sensitivity of the MRI. So you may say, well, big deal. This might be one of the closest and more realistic implementations and the applications of this whole quantum business. Right. So I think I have maybe about 5 minutes altogether. So 2 more minutes for another platform. I've been telling you about large collections of atoms, high absolute sensitivity to magnetic fields. Now let's talk about the other extreme. We have an experiment run by Jean-Baptiste Beguin in my group and my colleague Jörg Müller, where we have here, it is shown 4x4, ultra-cold atomic atoms. We can now have, 10 by 10, 20 by 20. And this can be thought of as the highly spatially resolving set of sensors. So here I show you a cell, which is to scale, basically. So if we manage to use this lattice of sensors to look at the currents or charges or magnetic fields inside the cell, could be fun. So this is one of the long-term projects in this field, and we have all kinds of interesting results for that, because essentially the same system can be used as a quantum simulator, but I don't think I have time to discuss it. So I will probably finish. This is our new center, and this is the proof that Denmark is not such a cold country. Thank you for your attention.
Are there any questions for our speaker?
On one of your slides, you mentioned a spin protective coating. What is that coating made out of?
It's a long spaghetti type molecule, which is referred to as alkene or alkane. Some people also simply call it a paraffin fraction. And we studied those things for quite a while, and all we can say is that an atom flying at 200 meters per second gets into this coating, spends there no more than 1 microsecond. We don't know how exactly, but no more than that, and then just gets out. And the simple picture that I have is essentially that there is no way to exchange the spin kind of degree of freedom with this spaghetti thing. What I also know is that the smaller is the energetic difference between the two quantum states, the better it works, you would think. Otherwise, no. So if you want to protect the hyperfine coherence, then it leaves 10 times shorter than the Zeeman coherence.
Okay, let's thank our speaker once again.
There is a
Oh,
question.
we have one more
now.
question. Oh, sorry.
Oh, okay, here comes. So you entangled 852, which is close to a resonance for CCM, with a 1064. I guess that's not close to any resonance, right?
Well, 1064 is close to the heart of the gravitational wave detection community.
I understand. That is
That's
important.
why.
I'm just saying,
Right.
you can I mean, you pick this because that wavelength is important,
Right,
but fundamentally, you can do this over how wide a wavelength range in Tango 852 is something. I mean, what is the requirement? Do you still need to
We can, the requirements are purely technical.
Okay.
So you need to find the right nonlinear medium, spend a lot of money on various optical components, but in principle, we can do 1.5, we can do 1.3. With some investment, we can do maybe even 2 or 3 microns. Thank you.
Okay, we'll save more questions for the break if there's any more. Let's thank our speaker once again. So our next speaker is Professor Moti Segev, who is the Robert J. Shulman Distinguished Professor of Physics at the Technion in Israel. Moti's interests are mainly in nonlinear optics, photonics, solitons, sub-wavelength imaging, lasers, quantum simulators, and quantum electronics. He has won several major awards, including the 2007 Quantum Electronics Prize of the European Physical Society, the 2009 Max Born Award of the Optical Society of America, the 2014 Arthur Schawlow Award of the American Physical Society, and the 2014 Israel Prize, which is the highest honor in Israel. Moti is a member of the National Academy of Science, the AAAS, and the Israel Academy of Science. He is currently the Neil Armstrong Distinguished Visiting Professor at Purdue. However, beyond the great numerous awards throughout his career, he takes pride in the success of his graduate students and postdocs. Among them are currently 21 professors in the USA, Germany, Taiwan, Croatia, Italy, India, and Israel. Let's extend a warm welcome to our speaker.
Thank you. 25. This was somebody that changed. 25. Actually, very shortly, hopefully 27. Which is really a great pride, I think, for all of us educating people. So I'm going to talk about light matter interactions in photonic time crystals. And I'll tell you a little bit about the history on this. So I am from the Technion, and these are my students. The top 2 people here contributed, I think, more than others on this, although quite a few others. And we collaborate with Vlad and Sasha's group. Soham Saar, who was a student here, is now a postdoc. And also Colton, Mustafa, and Sarah. What you see here is actually a dielectric material where we change the refractive index in time at the rate of a single cycle, a single optical cycle, which means within on the order of 5 to 7 femtoseconds, okay? And it changes the refractive index by order of 1. I will show you also data later on. So everything that is in the perturbative regime, forget about it. Just forget about it. So my claim is that what Eugene Demler said there later on is not relevant here at all, despite all the things. And the reason is that he was talking about parametric amplifiers of light, which is okay when you are perturbative. This is completely unperturbative, and there is a lot of experimental evidence for that. So there are some papers that if you are interested, you can read that will tell you that we will never be able to do it. I like challenges, and what you see here is data that shows you within 1 optical cycle, 5 femtoseconds, we change the refractive index 0.12. In other words, from 0.3, these were materials that are epsilon near 0, are supplied to us by Sasha and Vlad. And we changed it by 0.12 within 5 femtoseconds or so. And if we look at, let it go all the way, within 7 to 8 femtoseconds, I think 8 femtoseconds, we change it by 0.5, which means that it's more than the 0.3 that was, plus 0.5 is 0.8 refractive index, a change of 100%, completely non-perturbative. And this one shows you is also something that was believed to be impossible. There are papers on this. And what you see here is actually like PIME probe. We, of course, change it with light, with a very powerful pulse. And then we look at the response by looking at the transmission through it by spectral shift, which I'll explain. What you see is that the rise time and the decay time are comparable, are on the order of a few femtoseconds. Decay time was supposed to be 200, 300 femtoseconds, and the system, the material should have been disintegrated. There are papers on that. This is wrong. In other words, we had a hunch that this is wrong. So we show here that, first of all, the system did not disintegrate. We used those materials for a month until by chance there was some dust on it and it burned. And so it obviously didn't disintegrate. And what you see here is also that the decay and the rise time are similar. So that was the story. Story is crystals, periodic structures. So crystals are periodic structures of, let's say, atoms or something. And we all know from the solid state physics that you get band structure. And sometimes you get them in nature by spontaneously. And sometimes you find them, you need to make them. Photonic crystals are materials where you change the effective index periodically, either in 1 dimension, 2 dimensions, or 3 dimensions. And yes, we can find occasionally some photonic crystals, usually 2D, not 3D in nature, like on the wings of a butterfly. But 3D, we have to make them. And to make a photonic crystal like this can give rise to a band gap. For the band gap to be significant, what you need is to change the effective index in 3D on the order of 1, and within on the order of something that is on the order of a wavelength. And when you do that, you reach to Ilya Yablonovitch's result of 1987. That is, I think, the most cited paper in optics altogether in the last 50 years or so. And what he said is the following. Now, before I tell you what he said, you need to go back and remember that photonic crystals were actually discovered by Lord Rayleigh. And people talked about this to some extent. Maybe you can say Fabry-Perot also discovered. If you go to the early 80s, late 70s, early 80s, everything about photonic Bloch modes and bands and this and that was discovered by Yariv and Potier. It's in the book. And then it was rediscovered by Philip Russell in the early 80s. So why Ilya Yablonovitch gets all the credit? Why he thinks about himself as a contender for Nobel Prize? Maybe he will get it. And the reason is that he looked at light-matter interaction. What he said, which is really where the point is, that if you have a photonic crystal in 3D and you have a complete photonic band gap, then spontaneous emission will be inhibited. So this is really the first paper where you look in a photonic crystal like that and you look at what it does to light-matter interactions. And I think that the claim that he's the father of the field is correct. So what we are interested is inspired by Eli, maybe because he's a friend of mine, but we actually look at materials that are completely homogeneous in space, at least as a beginning, but they oscillate in time between epsilon 1 and epsilon 2 within on the one cycle. So as I will show you, this actually gives you dispersion band. It's a dispersion relation between the frequency and momentum that is rotated by 90 degrees. You have momentum that are momentum band gaps, within which the frequency is complex and it has major implications. To do that, what I said before is that you need epsilon changes on the order of 1 within one cycle. Physically, the temporal boundary conditions in the switch are trivial, are similar to what you have is that all the tangential fields are continuous. And you can look at some duality between space and time, at least in 1 dimension, and draw a lot of ideas from 1D photonic crystals. Only that be careful. Things are fundamentally different, and that's what I'll be talking about. This is what we explore. So let's see what happens. So usually, with the way we look at the constitutive relations, we look at D of some function on the response to the electric field, and now it accumulates in time from some time until, let's say, minus infinity until this moment. Actually, this should have been here T, but never mind. Okay? And so then the Fourier transform of that looks like this. Now, usually, in our usual thinking is that we assume that epsilon is constant in time, which means that then the displacement current, the displacement is a function of omega, is a product of epsilon times the instantaneous electric field. But we are interested here today of something that is different. Here now, epsilon has an instantaneous response in time, which means that D at a moment in time has no memory. It's epsilon at that moment times E at that moment. We are really not here yet. We are close enough. We are pretty close. So we still need to take some history into account, but there's a lot of interesting physics in this. Theoretically, this is easier to analyze. So let's see what happens by analogy to interfaces. So let's say that we have a spatial interface at some point, going from one epsilon to another epsilon. It comes, this is time, this is Z, comes the electromagnetic field, part of it is refracted, so part of it is refracted. This system right here, if the medium is dielectric medium, so it conserves energy. And momentum, it conserves momentum in this direction. Now, the analogous system is the following. When this is time now and this is z, comes the electromagnetic wave. Medium is completely homogeneous. At some point in time, at t naught, we change the refractive index. So what would happen here is that now we have time refraction and time reflection, that which I will explain in a moment. And let's see what the implications. So first of all, the material is completely homogeneous. Means that momentum is conserved. Frequency is not conserved. It's not conserved. And it has nothing to do with the way you modulate it whatsoever. It has to do only with momentum conservation. So if you want to look at that, if momentum is conserved because the medium is homogeneous, it's translationally homogeneous, then K is conserved, 1D, which means that the old frequency now, which is frequency times the refractive index divided by speed of light in vacuum, is equal to the new frequency times N2, the new refractive index, divided by the speed of light in vacuum, which means that the frequencies will scale, the new frequency will scale like the ratio of the refractive indices. That has major implications. I want to say reiterate more because many people make mistakes. It has nothing to do with the way that you modulate it. There will be transients. If you do it abruptly, there may be a transient, but this is already after you finish the modulation. This is just one jump. Okay, so given that there are two new frequencies, we understand that the time refracted wave, you have electromagnetic wave going. The new one now, it will transition into a new frequency. But the whole medium will also generate a time reflection, which means that the whole medium wants to generate reflection at the new frequency, not only forward, but something else. In principle, you know, it should have been going back in time like this. But unfortunately, we are restricted by causality. I tried to go back in time, correct some mistakes, never succeeded. Maybe some of the younger people will succeed. But so it means that it goes back in space rather than in time. Mathematically, it looks like a negative frequency. It goes back in space, and therefore it will have the new frequency. So both of these will have omega 2. And the one when going back in space will have a conjugate phase. It actually creates instantaneous phase conjugation. So what happened to this? Some of these ideas are known since 2001. And then to look at the experiments on this, time refraction, this was observed for the first time, I believe, by Vlad's group in 2016 at CLIO. Time refraction of optical waves also. It was here, they didn't call it exactly this way. So several years later, Bob Boyd observed it. The results were actually worse than the results that were produced here at Purdue. That's how it is, but it attracted the name. Time reflection, because it's so hard to get a large change in the refractive index within one optical cycle, then time reflection so far was observed in microwaves, actually last year by Andrea Alou, and slightly later by Dimitri Perolis and his postdoc Tom Jones, 2023. Time reflection at optical frequencies has never been observed to this day. What was observed also is the presence of momentum gaps in transmission lines at radio frequencies. But time reflection, actually, the first time it was observed is right here. This is a movie by a friend of mine, Matthias Fink. And they observed it in water waves. What he did is like this. He created a big tank of water, okay? And then dipped something in. Now, because he's French, what he dipped in it is a little statuette of the Eiffel Tower. So you dip it in, and you create waves that are going out. And then you drop the tank. You don't keep in mind in water, what happens is that those ripples on the surface are gravity waves, are really created by gravity, the surface waves. So you dropped it out. When you drop it, free fall, there's no more gravity, it doesn't feel the gravity. So you change the wave that's in the medium. So you create time refraction, it goes out. New frequency, blah, blah, not important here because it goes out of the tank, reflected from the walls at some point. But what goes in has conjugate phase and recreates the Eiffel Tower. And that's what you're going to see now. Okay, so this is the story. Now he dips the Eiffel Tower in it. You see the ripples going out. He moves the statuette and drops the tank. Up. Nice. In optics, we never observed. What was observed until now is in microwave by Andrea Alou. And he looked one big pulse and the small pulse, and you saw them reversed. And what was nice here that was done, the experiments done by Tom Jones and Dimitri Peroulis, is that actually they put some phase structure and they saw the phase structure reversed, which is actually for the first time ever. That's nice. So with this in mind, okay, let's see what happens when you do it periodically, up, down, up, down, up, down in a periodic fashion. So we can draw, again, an intuition from photonic crystals. The wave equation 1D, it's convenient to do it on the magnetic field. The eigenmodes again, solve it for the magnetic field, it's easier. The eigenmodes are Fluke modes, actually, and what you get is this dispersion structure that looks exactly reversed. Mind you, we always talk about band gaps. What is unique about the band gap? What is unique about band gap in spatial photonic crystal is that there is a range of frequencies for which K, the wave vector, is complex. Many people know band gaps for bit and blah, blah. Pay attention exactly. It is actually K is complex. Here, if this is reversed, what happens now, and in the momentum gaps, the temporal frequency is reversed. It has to do with what I'll show you now. So the next thing is the following. Let's say that we have a crystal like this. So first, a photonic crystal, a special photonic crystal. And let's place a little bit of an antenna or an atom that wants to radiate exactly the frequency within the band gap. So what happens to it? So the two solutions it's in the band gap, so it has complex K, which means now that it will have something, the envelope of the electric field, or the amplitude of the electric field, will blow up as a function of Z to plus Z and to minus Z. But energy is conserved, so those diverging tails are unphysical, because it will go to infinite energy. So what you are left with is something that decays from the point of this atom, decays exponentially forward and backward. So there, if you solve Maxwell equations, you'll see that the magnetic field associated with this mode is also decaying at the same rate, but is to phase shifted, which means that the Poynting vector time average is 0. It's not decaying exponential, but it's 0. That's the role of evanescent waves. And this is why spontaneous emission is inhibited in photonic crystals when you have a band gap. Okay? That explains the Jablonovich. And what we are interested to know is what happens in a time crystal like this when the modulation is periodic. So now let's say that the time is equal to T0. There's a little bit of atom that wants to send a flash of light. Okay? The two solutions are, it's in the band gap. So momentum is in the band gap. How you generate it? You make the atom small. It's smaller anyway than the wavelength. So one atom. Oops. So as a result of this, the solution now have complex omega for temporal frequency that would diverge or decay exponentially. Since unfortunately we cannot go back in time, so everything that happened before the point of the flash of light, you cannot change. So these are unphysical because of causality. So what you have is something diverging, something decaying exponentially. How can it diverge? Well, energy is not conserved. Time translation is broken. So therefore, what will happen is that the radiation will actually extract energy from the modulation. Okay, will take away energy from the modulation. That's the logic. So in special photonic crystals, the electric photonic crystal conserve energy but not momentum, and the electric photonic time crystals conserve energy, conserve momentum but not energy. The idea, this concept, part of it already exists from the old times, but the one that really put his finger on this is a guy by the name of Peter Halevi, right here. He's a guy that actually is somebody that's the Holocaust survivor as a baby, as a little boy, and then immigrated to Israel when they changed his name to Peretz Halevi, did his postdoc, undergraduate studies and PhD at the Technion, my institution, came to the US to do a postdoc. His postdoc was not good enough, so he never got a position in Israel, so he went to teach in Mexico. This guy is now 80 years old and still publishes very good papers. Anyway, so he is the guy behind it. All the others are his students. So, and we got into this field actually around 2016 or 17, and it turns out that some of the ideas were actually rediscovered, not only by us, but also by Vlad, and we were quite surprised to see Peter Halevi. So Vlad decided not to publish, and I decided we go forward and we come up with new ideas, look at light-matter interactions. I continued that. After about a year, I convinced Vlad to go and join us and start working on these joint ideas. So this is the story about understanding the theory. So this shows you a little bit of what happens when you launch a pulse. This is time, and you launch a pulse, first of all, from the band. So you launch a pulse from the band, and let's see what happens. So time crystal starts here. So you can look at also here. So you enter the time crystal, so you change the medium. Now it goes into the bands of the time crystal, and you generate time refraction, time reflection from it. And then here you stop it, and you get again time refraction, time reflection, they interfere. So that's what you'll see here. This is not very educating, because what you see is just how you generate time refraction when the photonic time crystal starts and ends. But this is what happens to it when it is in the gap. So you choose to launch a pulse comprised of, or a wave function comprised of modes, two modes that are in the gap. So what happens to it, it goes in, and then the pulse stops stops by the modulation, and the amplitude grows at the expense of the modulation. So it takes energy from the modulation. There are very, very interesting questions of what happens to the leading edge. Why is that? Because in the dispersion curve, it looks like superluminal, faster than light. Group velocity is faster than light. So what happens? Actually, what happens is the leading edge is causal. We did this, we looked at this, we published it. And what happens when you trim it a little, you will see that the information goes on the speed of light. We can't go faster, unfortunately. Okay, so after we did that, we started in that paper, we wanted to have some new twist on something because it was known. So we looked at the topological properties. This looks, the modulation up and down, it's like the SSH, which is the, I would say, the zero model, the simplest model for topological insulators. Not very instructive, but we wanted to see what are the consequences. And we looked at the topology of the bands, and we found, we calculated the Zach phase. And what is really interesting is that there is a phase relation between time refraction and time reflection. It is related to topology, and that can be actually measured. And we predicted that if we launch a pulse, and you start with a time crystal that is from this band, and at some point you transition to another band and different Zach phase, then you generate a temporal edge mode, which will look like this at peak intensity. And that was nice. Next, after that, I asked my student, Natan Sharabi, what happens if you put some disorder? Will it be related to undersoul localization and so forth? And it does, but it's also different. It stops, the pulse stops, you put some modulation, it completely stops, and the energy goes up. And what you see here is that this is when there's no disorder at all, then group velocity is unchanged. You put a little bit of disorder, it starts stopping. And you put some more disorder, it goes down exponentially very fast. And then the pulse energy goes up. And there are several other interesting predictions, signal parameter scaling and so on and forth. And there were experiments in water by the successors of Matthias Fink. And they gave us nice credit. I wish we would have done the experiment, but with electromagnetic waves, we are not there yet. Given that what was done here by Dimitri Peroulis, we might be there right here, doing experiments here. Next thing is that it's calling for is what happens when you have a grating in space and you modulate in time. So think about my face as a grating, and now you start modulating it like this. It creates some interesting mixed gaps in frequency and momentum. There are exceptional points, there are higher order ones, a lot of sensitivity, a lot of interesting stuff, not observed experimentally, only predicted theoretically so far. But I want to go back to the light matter interactions in a time crystal. And this is the story of Eli Abronovich I just told you. And what we want to know is what happens when you do that in a time crystal. So what happens in a time crystal? By the way, at that time, this idea of Eli Abronovich led to many, many interesting applications, not only fundamental science. One of them is that you can make lasers without any threshold, because the fundamental threshold to lasers is driven by the fact that you excite atoms, or whatever, to excite atoms or charges to some excited state. And the decay is not only to the lasing mode, but also to the spontaneous emission decay is also to non-lasing modes. And this determined a fundamental limit on your threshold. Okay? And if you are able to construct a system that has only one defect mode into which all the lasing will go, you kill all spontaneous emission, you can make threshold-less lasers. And these are two examples in 2D and 3D. So we asked what happens. So if we do something like this, so I said to my students, look, it's very easy here to make mistakes. Let's start with electromagnetism, classical, and then go to quantum. Otherwise, you get all kinds of bizarre results. Given that causality here plays a very tricky role, we start with the dipole. So we started with the dipole, and we solved the way that we should do it. And the way to do it is to actually find the green function. In other words, find what happens. So what you see here is what we knew that we should get, that there are two modes like this. At time equal t0, you modulate it, and you let it modulate some dipole modulating, classical dipole. And let's find the Fluke modes and find the green function in a Fluke system like this. And we found it, and then given in one direction. And then we said, okay, so that means that we have like a plate with directional current that goes up like this. Let's find the green function. And the next thing after this is let's take a superposition of them and then construct a point source in a 1D system. And this is how it looks. If you take a superposition of these, it's very, very interesting. And the outcome of this is actually you have something that will decay. It's a point source, so it radiates all directions. Some of the directions correspond to the momentum band gap, And those directions can actually extract energy from the modulation and grow exponentially. The photon flux goes not only the amplitude. So this is how it looks. You see? Yeah, so let's say that you have a little antenna that radiates all directions. The real part of dispersion curve, or the refractive index, is the blue, and the imaginary part is the red. So you can see this is the region where the temporal frequency is complex. It's complex because of this. And this is half the modulation frequency. Okay? And what will happen now is that those directions that correspond to the band gap will be amplified, and they are amplified. Yeah, yes, you see they are amplified right here. This corresponds to this. But because there is a peak here, then it becomes narrower and narrower in time until it becomes monochromatic as time goes to infinity. There are additional issues. One of them has to do with what happens in the band as you get close to the band edge. It turns out that there's an exceptional point there, and the density of states goes to zero. So will the radiation actually grow or be decreased as you go to the band gap? Turns out that this happens how you prepare the time crystal. If you prepare it abruptly, then the vacuum state is one thing. If you prepare it gradually, then the vacuum state is something else. It's fundamental, it's interesting. You can engineer the shape of the spontaneous emission. So there's a continuation paper after our science paper that shows exactly how by designing how you turn on the time crystal, you can actually shape completely the spontaneous emission. That's very interesting. So the other thing is next, after we did that, we looked at, of course, at the quantum model. So what you have here is this is the new term that is very interesting, and that tells you that every time you modulate, you are generating pairs of photons with opposite momentum. Why opposite momentum? Because eventually momentum is conserved, so if you cannot generate one, you have to generate pairs of them, okay? And generally speaking, the bottom line will look like this. If you are looking at the band, the number of photons oscillates but remains small. But if you look in the gap, in the momentum gap, number of photons that you generate blows up exponentially. And this is, if you want to calculate what happens, the process, and let's say we start with an atom that in excited state, the atom in excited states can go down and emit one photon, or it can actually remain excited state, and the modulation in the medium can generate a pair of entangled photons, of counterpropagating entangled photons, and they can't go down. Now, anyway, this diagram diverges. We couldn't find a way to compute it, which is really an interesting challenge. But you can use Fermi-Golden rule to draw some conclusions. And there are a lot of interesting things, that, for example, the interactions of a two-level atom with a time crystal. It has interesting consequences. Perhaps the most interesting one is this one, that if you put this system into a proper resonator and set a preferential mode, you can have a laser, a photonic time crystal laser. What's unique about this laser? It has nothing to do with any atomic resonance whatsoever. And you can tune it, you can shape it, you can shape the spontaneous emission, stimulated emission, and also the lasing, and which is very, very interesting. Now, I've been asked many, many times, what is the relation to parametric oscillators? The answer is that if you take this change of the refractive index, which is on the order of 1, and you bring it down to the 10 to the minus 4, 10 to the minus 5, which is what we have in the lab today in parametric oscillator, the band gap closes completely, and what you get is something resonant. And indeed, we know that in a parametric oscillator, energy is conserved and momentum is conserved. What does it mean? It means that if you launch a pump, then the sum of the frequencies of the signal and idler must be equal to the frequency of the pump, and momentum is conserved because of phase matching. So we have a resonant, you cannot really go away from the resonance, it's highly resonant. Here, what I just showed you, there's no resonance whatsoever. There is a broad momentum gap, and you can be anywhere in the gap. You can emit at any frequency you wish, provided that the emission comes from a source that is smaller than the wavelength, that's all. And that actually has some interesting implications. There's another one. I told you a little bit that the pairs of photons you generated are entangled. It turns out that with some manipulations, you can actually make cluster states out of this. 1D, we have some ideas on how to go to 2D, which are not so easy, but 1D is actually easy. Nothing that we did, we looked at what happens when you take a relativistic electron and you launch it near this time crystal. It turns out that you can get radiation below the Cherenkov threshold, which is interesting by itself. And not only that, you can get quantum interference between the modulation that you generate, between the pairs of photons that you generate, and the photons that are emitted by the relativistic electron. Some of that was known already for a long time from Vitali Ginzburg, transition radiation he called it, but he didn't look at the quantum aspects of that, and there are a lot of, and the fact that it's really periodic modulation. Very, very interesting, has never been tested, and we are going after that. If I get to win the next ERC, then we can go into the lab and do these experiments on the ultra-fast transmission electron microscope. But what I wanted now to talk a few minutes about photonic time crystals in the lab at optical frequencies. So let's first of all observe time reflections. First of all, one can ask, why going to the optical domain at all? Why not microwaves or RF systems? And the reason is because light matter interactions, strong light matter interactions that are related to electronic levels are in the visible or near IR, mostly. So this is really, so it's not a coincidence that many of the experiments with lasers are done here. This is where we know how to work, and the relations, and the interaction is strong. So why optical regime? Because this is where we can be linked to light matter interactions through electronic energy levels. Okay, you don't need to cool anything and so on. So let's first of all see time reflections in the lab. So what you need for that, you need a large modulation of the refractive index of the order, at least 0.1. Usually it's not enough. And then nonlinear optics can give you 10 to the minus 3. This is high. Usually it's much lower than that. Or you can go to some other mechanisms that will give you large index changes on the order of 0.1, 0.2, but this is extremely slow. For example, liquid crystal, pneumatic liquid crystals and so on. So they are not relevant. So this is why you need to be able to generate large time reflection. You need to change the refractive index within a cycle. Okay, this is why it has never been observed, and observed only recently in a loose group in microwaves, but not at optical frequencies. So this I told you why optical regime. So what mechanism can give rise to an exchange of at least 0.1 within 5 femtosecond? And the answer was there in the air, but it was suggested for a different reason to go to ENZ materials, epsilon near 0. The first time that actually this was observed, this time refraction, that you can get significant time refraction, is by our groups in last year. So why do we look at ENZ materials? So I'll tell you why we looked at this. So we looked at this as we want to see time reflection. If you look at Fresnel reflections, then it is normalized by 1 over square root of epsilon. So if epsilon goes to 0, in principle, we can get enhanced reflection. This is why we went there. If I was smarter, I would have guessed that there is a better reason for that. But this is not the reason why, eventually this is not the reason why it succeeded. It succeeded because there's a mechanism that can do the things very, very fast by changing your plasma frequency. So the story is the following. These are materials that are transparent conductive oxides, TCOs. Okay, so they have, if you look at the conduction band, there is population at the bottom of conduction band. Okay, now you come with a short laser pulse and powerful, and you excite many of them to a higher energy state. Higher energy state, you can look at it from several ways. One of them is change the plasma frequency. Another one, you can think about changing the effective mass. It's okay. And then they go up. So once they are in excited states here, the change in the plasma frequency or the effective mass changes epsilon significantly, and the change is on the order of 1. And now if you think about this, every photon that comes from the pump will bring up 1 electron, then you'll see that the rate is proportional to the photon flux, which means intensity, and the total change is how much electrons you accumulate at higher energies. So it goes like the energy in the pulse. Okay, that's so far so good. How about the decay? The decay was believed to be through coupling to temperature lattice vibrations, which means that it takes long, 200, 300 femtosecond. And if you calculate what 1 pulse will do to it, if everything has to go to temperature, I can tell you that the material will not sustain it. This is why some of our friends wrote in some papers that there will never be something like this, and the material will disintegrate, and blah, blah. And it was interesting, but we saw the opposite. That actually, when it comes down, there is a mechanism that we don't exactly know yet what, but there are several possibilities that brings them down at a much faster rate. The rate is actually ultra fast, on the order of 10, maybe 20 femtosecond. And then you can see also the long time response. So it's there, but that one is after most of the kinetic energy was already given away by some other form, most likely photons. So this is, okay. So this is how we design such an experiment. We start with a Thai sapphire about 30 femtosecond. Then you launch it into a hollow core fiber with some noble gas in it. You stretch the spectrum, and then you play with the two gratings. You bring it down to 5 femtosecond at 800 nanometers, and you illuminate some region, some large enough region. We illuminate on the order of 1 millimeter of some sample. And then, from the same laser, you use parametric down conversion, and you create a pulse at about 1500. Pulses that we work today are about 40 femtosecond. At 1500, 5 femtosecond is one cycle, single cycle. And you launch them here, and you look at Fresnel reflection, transmission, and time reflection. This we haven't seen yet. This we measure. And the most interesting one is the transmission, because it shows you the spectral shift. And this shows you a spectral shift like this when the refractive index change from N1 to N2, okay, from 0.3 to 0, eventually to 0.8, okay? So you get there. So this is when the modulation is slow, relatively slow, 8 femtosecond. You can see 0 is when the pulses start to overlap, the pump and the probe. So you can see that it goes to redshift, to longer wavelength, up to here, which means that actually the frequency is changed to a lower frequency. And then this is the relaxation. And this is the 7 femtosecond. This is, I think, the fastest we could go is about 6.8, okay? And you can see already that this time, the time it goes here and here are about the same, okay? And this shows you what happens within a single cycle. In a single cycle, you can see this is a function of the model. The maximum index change of 0.5 occurring within about 8 femtosecond, which is very, very interesting. So we are there. We are close enough now. Unfortunately, our laser doesn't now work at its best, so we have been delayed with everything that we want to do next. So a few words about recent results. First of all, we have a paper now about at Clio about plasmonics and surface plasmons at the interface of a metal and the photonic time crystal. So we looked at single modulation, and also we looked at the time crystal. Extremely interesting, interesting dispersion relations, a lot of interesting physics, and in my opinion, actually, there is a lot of there's fundamentals in there because of the wavelength of the plasmons can be very, very small. So there's a lot of interesting physics in that. Next one is what will happen if you have an interface between, let's say, air and the dielectric medium, that you change dielectric medium once or multiple times. So it turns out that if you come at an angle that is larger than critical angle for total internal reflection, then several things happen. One of them is a CW wave becomes a propagating pulse because you are adding a degree of freedom. Now it's a 2D system. So you come at a particular angle, you're generating new frequency. Every frequency will see a slightly different Snell's law, and therefore now we generate a pulse that goes in some in a fan of directions, but it becomes a propagating pulse if you go above critical angle when everything was supposed to be evanescent. So the evanescent wave becomes a propagating pulse. Time reflection is enhanced, very sensitive at the total internal reflection angle, at critical angle. Interesting physics. This is now hopefully under a final review with PRL. And another one is how the preparation of a photonic time crystal, whether abruptly or adiabatically, how you can shape the emission of entangled photon pairs near the momentum band gap, or how you can actually shape the spontaneous emission. Experiments, there are experiments that what will happen if you have an index change now like a pump that goes this way and the probe that goes this way versus when they go like this. Interesting physics there. Another one, next one is an experiment that was actually suggested by my student Ohad and by Colton. It's sitting right here, and then actually the results are interesting. Not we understand them. We are about to understand them, hopefully. And maybe the most interesting one is what happens to nonlinear optics in time-varying media. So let me tell you, first of all, how to think about it. So in the most simplest case, when the momentum gap is not very big, then what you will have is now new dispersion relations, and whenever you're interacting waves, one of them is the momentum gap, then you can extract energy from the modulation, and you can get a lot of interesting phenomena like enhancement of nonlinear optics, enhancement of, so you can make from this an OPO, optical parametric oscillator, that is more efficient and so forth. Well, that is interesting. But the fundamental, really fundamental one is can you actually change the atomic dipole? If you can change the atomic dipole, think about the Lorentz oscillator. If you change the atomic dipole, the Lorentz oscillator gives you new nonlinear optics. So now think about, not about one, but think about a chain of them, okay, of Lorentz oscillator that are being changed. The spring constant, if you think about this, is changed periodically in time. Completely new nonlinear optics. This is where we are targeting. So theoretically, the first part we did already. The second part is now being done and finalized. And there are some talks about that in Clio. And sometimes it's good to do experiments, because experiments can reveal new stuff. So I'll show you, there are now 3 experimental groups. One of them that was before all the others is the group of Pendry and Sapienza. Unfortunately, they beat us a bit, and they put a nice paper on the archive. And there is also another one by Soham Saar, who was Vlad's student. He's now a postdoc. Also interesting experiment, and I'll show you ours. And this is in collaboration with Vlad and Sasha, of course, and this is the experiment on this. So what we do here, we are looking at second harmonic generation and third harmonic generation also, in some piece of material right here. And there is a modulator at 800 and probe at 1200. This, the spectrum is generated. As you see here, is what happens when you make the pulse, the modulation shorter. The regime that I'm interested in is 5 femtosecond. We are not there because our laser is acting up, but you can already see some interesting stuff. You can see that second harmonic is actually suppressed. And what you can see right here is a little movie. It shows what happens when you change, in a pulse like this, you change the overlap a bit. You can see that you change the angle and you change the spectrum. The vision is something that started over wine, I think, between Vlad and me. This is what we want to do. We want to do high harmonic generation. We discussed this, and sometimes when you drink enough, you come up with new ideas. So it may have been suggested by Vlad alone, I don't know, but I remember when it was, we drank. So apart from that, there are fundamental questions on material science that are arising from these experiments on the solid state front. So first of all, the TCOs, those materials are transparent conductors. They display ohmic conduction at room temperature. But what happens to them when they are excited at a very short pulse on the order of 1 femtosecond? Excited not a little bit, but you change completely the properties. So what will happen now is that Drude model doesn't work. Drude model means that the electron has to collide with the ions, and then you get ohmic conduction. So what will happen now? Are there ohmic conductors at these timescales? We don't know the answers. We are not there yet to test, but it can be tested optically, and we are going to test it. In other words, what is the relation between the current and the electric field? Will it obey Ohm's law? Of course, it shouldn't, and that is interesting in itself. Another one is that I told you, those materials return to, once you excited their electrons to higher energies, they return to equilibrium to phonons. But what we see from the experiments, actually, at epsilon returns to its original value within a few femtoseconds. Later on, almost original value. Later on, there is some longer decay. So we see the decay also, but there is a fast one. What can it be? So my guess is, this is my guess, we have not tested it yet. By the way, this was observed since then by another group, something related to that by Sapienza, who works with Pendry. And what I hope is that the relaxation of epsilon, of the electrons, the energetic electrons, will be through induced emission. These are not two-level systems. Rather, there is continuum of levels. In between them, it's quite empty. So it could very well be that we get stimulated emission right here, which is my hope. There are several other mechanisms. One of them, interesting one, was suggested by Evgeny. So who knows, whatever the answer is interesting and it's important. Another one is, if we model the electrons as plasma, then how fast can you switch a new plasma frequency? Is it instantaneous? You know, theoretically, we like to assume that it is, but it needs to be tested in experiments. Last one is, can the response at few femtosecond include the signature of quantum many-body physics? So we know that at femtosecond, before all these collisions happen, you should not get any decoherence. So therefore, there should be quantum many-body physics involved as we go shorter and shorter. So at some point, you should be able to see it and simply see the growth of entanglement. So there are a lot of interesting fundamental questions also on the materials or solid state part. So that's the list of some of our papers. And I want to say here that the photonic time crystals is, in my opinion, the next big thing in photonics, and I'll tell you why. First of all, because it's new. There are a lot of new aspects, and also because it has interesting applications. It's hard to get there, but it's possible to the applications in the optical regime. It is more likely that the first applications will be around terahertz, and the reason is that terahertz today has no good coherent sources. So that's a challenge. If that can resolve it in some way, then there's a chance that there will be a parametric oscillator like that with a big band gap, non-resonant, around terahertz. But there are many, many others. So usually applications help keep activity and create new ideas. A material, a topic that eventually has little applications will decay after some hype. This is why I believe in this one. And I will stop here, and I hope, as always, that the best is yet to come. Thank you.
Do we have any questions for our speaker?
Thank you, Moti. It's not a question, it's more maybe a comment where to look for time crystal physics. As one possibility is the coherent phonon materials where you can have coherent phonons. Those support long oscillation periods for dielectric function. And if you want, the only problem maybe is the modulation depth. But if you go to phononic ENZ regime where you have this phononic collective response, then maybe you can achieve the same physics. You can have enough modulation at the same time. You will have the long-lasting oscillation, periodic oscillations, because of coherent phonons.
You're absolutely right, and I will be extremely happy if somebody picks the challenge and does that. I don't do coherent phonons, so I'm not an expert in this. But I think it's a good idea. We thought about it quite some time, and I agree that we should put some suggestions in our papers so as to give some vision to the people. Yeah.
Actually, following up on these experiments of this type have already been done on silicon carbide. They saw light amplification after exciting one of the phonons. And we did talk about using this type of physics to get terahertz, lasing and amplification. So
from the phonons.
Sorry?
From the phonons, yes?
From the phonons, that's correct.
Well, did anybody do actually experiments or just?
Well, that's what I said. It actually started from experiments done on silicon carbide where they saw amplification. They saw that after exciting phonon, they got amplification in mid-IR.
Did anybody do coincidence, or at least to look at whether you see there's supposed to be entanglement involved in the photon pairs?
That's what we have been asking our friends for a long time, to do spectrally resolved experiments. Unfortunately, in this field so far, everything they have done was broadband pulse.
I see.
And they're saying it's, even for Max Planck, it's expensive, to try and limit the width of the pulse. But actually, the formalism, which is really kind of interesting, exactly the same way how you guys formulated, we have done, other people have done for the spam probe experiments, the same complex wave vectors K for a given frequency and seeing amplification.
Well, I hope that they are able to do that. And I don't know if the question eventually will be whether light-matter interactions will be as pronounced as via electronic levels. Maybe yes, but then you need to cool everything down. So.
And it's very easy to imagine that by actually already analyzing experiments done on superconductors, you can see that by exciting phonons, you can modulate Josephson coupling, you can modulate superfluid density very dramatically. And that has immediately strong impact on terahertz properties.
I wish you luck.
Is there any other questions? Okay, so we're going a little long. We'll probably take about a 10-minute break and come back for the next presentation.
Let's continue on. Have a seat and I hope you are all refreshed and ready to start again. It's my great honor to introduce our next speaker, Dr. Orit Wolf. So Dr. Orit Wolf is an internationally renowned concert pianist, composer, poet, and TED lecturer. She's an artist in residence at the Technion and a guest lecturer at the Royal Academy of Music in London. Her unique concert series, hosted by the Tel Aviv Museum of Art, has garnered a large following of subscribers who appreciate her interdisciplinary approach to classical music. Recognized as one of the top lecturers on leadership, innovation, and music, she's also named one of the 100 most influential people of the year by the Marker magazine in 2010. Wolf is a recipient of the Kahn Award for the Arts and the Rosenblum Prize for her unique interdisciplinary work in the performing arts. I'm very excited for this wonderful lecture. Please help me welcome Dr. Wolf.
Hi, everyone. I think we'll make it as short as possible just to make you uplifted, and you can have a seat a bit closer to me. I'll be so much happier if you can come in closer. It's a totally different session. I wish I could speak about physics, but I'm not. And I'd love to share with you some of my experiences as a concert pianist and a speaker on innovation and leadership. And I'm not going to teach anything. I'm just going to share with you some stories. So it'll be really nice if you can come closer. Great. The one thing I regret is we don't have a grand piano next here, because I'd love to give some live examples. But we had a really nice experience on Monday in a concert in the beginning of the conference, thanks to Sasha and Vlad. And I'd love to start with the 50% law by Edgar Dale, who used to say that we listen to 50% of what people talk to us and we remember 50% what we listen to. So how much percentage are we left with from every experience? How much are we left with? I see half of you haven't listened. Okay. Exactly. Yeah. I mean, we are afraid to admit it because we want to say, I was here. I wasn't on my phone. I wasn't on my internet. I was listening. And I'm sad to tell you the truth that sometimes, even if we really enjoy and we're really attentive listeners, after 4 months, if I ask you, how was the conference? You might say it was great. And then I'll ask you, okay, so what did he talk about? What he talked about? And you say, well, I can't remember, but I remember it was fantastic. So basically what I'm trying to say is that we think about it, what are we taking with us? This is the main question of my lecture. Edgar Dale said something very nice in his Cone of Experience in '69. He said that we remember 10% of what we read, but we remember much more, 90% of what we teach. Something that we engage with other people, something that we are doing together with others, that we are very involved with, we'll remember much better. So this is a beautiful pyramid. I really recommend to have a photo of this. And what he said is that the reading is the hardest one, but the more you're doing a very interactive and engaging session, you will remember it better. So great teachers are the ones who give not only examples, but really engaging the audience with something very active. So basically what I'd love to share with you is really not about how to lead a content, because I was sitting here and I'm thinking to myself, I don't understand anything about physics and photonics. And it's not about the content that I'd love to speak to you about, but rather about how to live an experience. This is my main issue. That's what I'm I love doing, that's what I love, searching and researching about really what's so special and what's the characteristics of those who leave a mark. What are the attributes of those who leave an experience behind, and how each one of us can actually do it really simply. It's nothing beyond possibility. So what I'd love to share with you is a sentence that Leonard Bernstein, one of my main mentors in life, he was one of the greatest conductors and pianists and composer who also wrote the West Side Stories. He said, people will forget what you said or did, but they will never forget how you let them feel. So for me, this is something that I really put next to me in my desk, and I really think about it, because we do so much into what to say, but much less on how to say. And really what people take from any experience is really the feelings rather than the content. And we live in an era that content is so easy to grasp. You know, even if you're not here the whole day, you can have a recording, you can be on the Zoom. It's easy to find the content, much harder to teach how to live an experience. So I want to take you to my own journey and to the Royal Academy of Music in London. This is my second home. I studied there my master's, and I'm teaching there every year, courses and master classes. I love this place. And the reason I would like to share with you about the Royal Academy is really to tell you what happened to me in my audition in 1995, when I come there for 2 days of auditions. And when you come to an audition at the Royal Academy, it's not just playing for them, it's also lots of interviews and music history, music theory exams. Okay, so I had to prepare 3 recitals, 3 different recitals, each one 90 minutes. So I want to share with you what happened. If I had a piano, I would do it. But I'm coming in to this beautiful hall. This is the Duke's Hall at the Royal Academy of Music. You can't see that there's a beautiful organ in the end and a grand piano style. So I'm working there and playing there, and I'm entering the Duke's Hall, and there are about 5 people in the jury, and they said, what did you like to play with, to start with, Miss Wolf? And I said, would I please start with the Moonlight Piano Sonata by Beethoven? And I was a bit nervous and shaky and shy, and I'm starting to play, and they say, sure enough, Miss Wolf, please start. And I'm starting to play the Beethoven Piano Sonatas. And after a few minutes, and you know this music, this is a very quiet and surreal and tender and slow music, right? The Moonlight Sonata by Beethoven, everybody knows this. And after a few minutes, I hear one of the jury members raises his hand and says, excuse me, may I, Miss Wolf, would you mind, with this British accent, and he said, would you mind, could you please play this music fast and loud? And I'm thinking to myself, this is crazy, you know, this music is slow and tender, and you know, how can I play this fast and loud? But I'm realizing something is going on. I haven't yet heard the word disruptions, which we're going to speak today, but I realized they're trying to check me in different level of preparation, different level of acting upon you know, disruptions. But I'm thinking to myself, okay, what should I do? And I'm playing this fast and loud. And then he says, thank you so much, that's lovely. Would you mind? Could you please take your chair out? So take off your piano bench. Now imagine this, to play fast, loud, and without a bench. I mean, it's impossible, because what you have to do when you play piano, and I'm sure some of you have played the piano, that you have to use what? Why is it so difficult? You have to use what? The pedals, exactly. And to use the pedals like this and play fast and loud, it's a little bit of rhythm. It's really difficult. So I'm taking the bench off, and I'm playing fast and loud, this very special music, and without the bench. And then they said to me, okay, so wonderful, you can have your seat back. And I'm sitting back, and I say to them, may I continue, please? And they said, would you mind? This is one by one, seriously. And then they say this, could you please swap your hands? Meaning, could you please play the right hand with the left and the left hand with the right hand? Meaning this, yeah? Now, I'd love to have the piano to show you how I did this, because this is scary. This is like 2 different computers in your head. No time, no preparation, no rehearsal, in front of 5 professors, which I don't even know who they are. And I have to play with swap hands. Now, this is really disruptive. And I do it. I do lots of mistakes, but I somehow manage. And they say to me, okay, so thank you so much. You can continue. the story is that I got to be in the school, and I got a scholarship to do the master's and the artist diploma, and I stayed, and I've really made it as a second home. This is my best time ever. But the reason I'm telling you this, the reason I'm telling you this, it's not a story about me. This is a story about a place that has strong vision, that has a very clear mind of what kind of students they want to get out of their institute. And I want to show you what they said to me. They said to me this sentence that really goes with me every day. We don't look for the best musicians. We look for the best artists. Now, this is really strong because, they say the best musicians are already coming, to audition with us. We get the best musician. We're looking for the best artists. And what I'd love to ask you before I continue is what it is for you is the difference between a great musician and an artist. It's a huge difference. Could you put your finger on the difference? There's no right or wrong. It's just really a feeling that you have. Wow. Wow, you're a poet. I love the way you describe it, Eugene. It's really poetry, the way you describe it. It's true. It's true. What else would you say for you is the difference between a good musician and an artist? Because it's really powerful. Yeah. Wow, wow, wow. This is my next slide, by the way, make it your own. This is really what it is. I'll show you soon. And you haven't seen my presentation. Yes, it's very true. Make it your own. You know this book by Malcolm Gladwell about the 10,000 hours, that you need 10,000 hours to be an artist in any field, to be an expert? I hate this book, sorry. I really say, you have to have 10,000 hours to be a great musician, to have the skill. But to be an artist, you need much more. Because it's not about having the great skill, it's about finding your sound mark. And this is exactly what you say without even knowing what I'm going to show. And this is Glenn Gould, by the way, who is a very provocative, used to be very provocative Bach player. He's not with us, he died at the age of 50. But he was one of the best Bach players, and you can realize that you're not agreeing with his playing, but you can't ignore it, you can't not appreciate his sound. And this is really what it is about the Royal Academy. And it's really not about the school, it's about concept of life. It's about being an artist. It's about thinking 360 degrees. It's about really understanding that it's not about you're now a student, listen carefully, and only after you graduate you start thinking what you want to do. No, you have to start what you want to be, not what you want to do. And this is a huge difference between what are you going to be, not just what you're going to do. And really, when they start working with the students, they tell them, we expect you to know which kind of BBC program you're going to direct, or which orchestra you're going to lead, or which podcast you're going to create, or which chamber music ensemble you're going to invent. So it's really about pursuing huge plans. It's not about graduating, having good grades, and get out. No, this is not interesting. And they have a career center, and they really tell you, if you have a dream, we're going to help you pursue your dreams. This is a huge difference. And by the way, to really encourage this, they let everyone study with 2 teachers at the same time. This is not happening at Tel Aviv University, for example, because each professor is very jealous for his own students, doesn't let any other professor touch his students. But over there, you must study 90 minutes a lesson with each different teachers, and every 2 years you switch. So it's really about learning from more than just from one. And this is a totally different concept of thinking. So I'd love to show you the Glenn Gould. Let's do an experiment. I can't play you, but I can, show you this. Let's see how Glenn Gould is playing the first prelude by Johann Sebastian Bach. I'm sure you all know this music. Let's see. Can we hear it? No, I can't hear it. Ah. Okay, good. Yeah, that's good. That's good. There's a very equal, very dry kind. I'll stop here. Here, this is Yeah, I'll stop here. I stop now because I don't want to have you hear it. I'm going to send you the PowerPoint if you like. But the reason is, it's a very special way of his own sound, and people can really recognize it's Glenn Gould right away because he didn't use much of a pedal. It's very dry, it's very clean, it's very articulate. And by the way, he refused to record. He refused to perform live. He only wanted to record. And it's very special. Now, if we move, it's not a music lesson here, but if we move to Vladimir Ashkenazy playing the very same thing, let's see what's happening. You feel the difference? So when we talked about, hold on, when we talked about the 10,000 hours, this is really not about the 10,000 hours. It's really about how you take, the music and you shaped it in your own way, in your own sound. And it's relevant to us because I always say, it's not the story you tell, it's the melody behind the words. And each one of us has a melody behind the words. It's not just about music. It's really about what kind of soundtrack would you like for your life, would you like for your lectures? And we can have full control of this. Let's move on. I won't have the time for everything, but let's. Sorry? This is on the harpsichord. By the way, which one you like the most? I can go on for many, many more. Which one did you like the most? Number one, who liked number one? Raise your hands. Okay. Who liked number two? Who liked number three? Wow, this is cool. So actually it's really third and third. Very, very interesting. This is the original Bach playing in terms of instruments because Bach did not have the grand piano when he wrote this music in 1742. He had the harpsichord, he had the organ, and we have a real problem. I just want to share with you something really tiny, that if I go, I go to international piano competitions because it's up to 32. If you're 32 in one day, you can't go to any international piano competition. It's really like sport. But if I would go to an international piano competition and play this Bach like number two, I would probably be kicked out. And you know why? You know why I would be kicked out of the competition? I mean, most juries will not accept it. You have any idea? Yeah, too much pedal, very romantic, like Chopin kind of style, right? I played, Vladimir Ashkenazy is playing very romantic. He can afford to do it, it's Vladimir Ashkenazy. But it's not appropriate for many jury members to play Bach in such a romantic manner. So there is no right or wrong. It's your choice. It's your own soundtrack, okay? But what I wanted to show you, it's not about music. It's really about the fact that you can choose the way you communicate. You can choose how you play your task. You can choose how you bring the same material in different ways. So let's go back to the PowerPoint. Yeah, where are we? Here. Good. So this is the original sound on the harpsichord. And I really, as I said, how is this relevant to us? And this is something I'd love to present for you. This is a model that I work with my students on. And when I ask them to present themselves, and to leave a mark, this is the first exercise that we do. And you can take a photo of this because it's very simple, but very strong. The 4 questions that many people miss, most people, when you ask them, can you tell me a bit about yourself? Most people, which are the questions that are really answering? Which are the 2 questions that are very much answered? It's usually, who am I, or who you are, and what you do, exactly. So most people, when you ask them, can you tell me a bit about yourself? They will tell you things that are already written in their CV. It's not interesting. When I stand with my students, I don't tell me something that I can read on your CV. Tell me something that you cannot write. And it takes a lot of courage to think, what can I say? I don't want to be too personal, but yes, you can find very special things to say and share with your audience. If you wanted to leave a mark, if you want people to remember you, if you want to live an experience, don't tell me the obvious. So most people are really telling who they are, what they are in terms of where they studied, what did they do, what kind of work they have, where they come from. Interesting, but not interesting. Sorry. And when people ask me, so what are you telling that is different? you know, you can find your way. For example, I had a student say, well, I have a twin sister, and everyone is confused between the two of us. You can say something special that, you know, it's not too much personal, but it's really revealing, it's really sharing. So, but the big questions are, how am I and why am I? And I'd love to really focus on this, because this is what I'm going to talk about the next 20 minutes. So how am I is what it is that is your strong attribute, your strong characteristic that really leads to your success. Is it your smile? Is it your humor? Is it your attentive listening? Is it your, I don't know what it is. Is it your quick answer? What it is that people love about you, and you always succeed because of that. Most people, when I ask them this question, they say, well, I don't know, I have to ask my friends. So start asking your friends, and mostly start asking yourself what it is that you know that brings you success. And why am I? This is the most difficult question. Unfortunately, most people don't ask themselves this question. Why do I do what I do? And sometimes, you know, I once had a workshop of lawyers, and each one had to present himself. And there was one lady, and she said, well, I'm a lawyer because. I said, why you are? She said, because, you know, all my family are lawyers, and I continue the tradition of the family. I said, yes, but why did you choose to be a lawyer? And she's saying, I just said, didn't you hear? I said, yeah, I heard, but why did you choose to be a lawyer? What kind of would you like to be? And she looked at me like, what do you want from me? I just told you I want to keep the tradition of the family. And it took me about 10 minutes, which is a long time, to actually bring her to say, I want to be a lawyer because I want to affect human rights. I want to affect the legislation of human rights. So this is something different. The why am I has to have not just your personal interest. It has to have social impact. I think each one of you who sits here, because I looked at your eyes when people spoke, and I thought to myself, wow, there's so much curiosity here, and so much aptitude to succeed and to learn. And this is really what I like to see, you know, these shining eyes that want to learn and really have this innovative thinking. So people don't ask themselves enough why they do what they do. And this is really about leaving a mark. So people spoke a lot about vision and purpose. You know, we have Peter Drucker, Stephen Covey, John Maxwell, Jim Collins. They have so many books about vision statements. But I'd love to mention this beautiful book that I'm sure you've heard, Start With Why. I see the smiles in the audience. And Simon Sinek, if you don't have the time to read this book, only read chapter 3 or see his TED Talk, which is a must. And the reason I love it, because he speaks about the golden circle, which is don't look at what people do. Don't look at how people do, look at why people do what they do. And it's both for individuals, it's also for corporates, it's also for academia. And this brings me to a great research in you know, through the Bank of England, which is one of the most financial research centers in Europe. And they say that they said already in 2017, we're already there, in 1 decade, 40% of Fortune 500 companies are not going to be in the list. This is scary. This is a scary thing. How come? I mean, are they not knowing what they're doing? They know what they do. So how come they're not going to be this? What do you think? This is really crucial. How come such a thing is written? Why would it not be on the list? Yeah, stop fighting for getting there. It's true. Yeah, what makes you stop fighting? Very good. Yeah, I agree. Preclude innovation. Fantastic. Anyone from the younger generation? I'd love to hear you. Yes. Yeah. No, I have some poets here and great. I'd love to hear the young generation. Yes, sorry. I agree. So the reason is that what they show that there is a new direction going from product, you know, but don't be concentrated on the program, that, you know, service is already an obvious, but we are starting to grow into value. This is very new. Now, everything I said about corporates, it's so relevant for individuals because we do want to speak about ourselves. Okay, I don't want to talk about corporates. We're not corporate people, and we are individuals in the academia world that we want to make a stamp. We want to have a signature in our work. So what it is to leave a value behind. This is very strong. And what it is to lead with values or to teach with values. So I can't go on without mentioning a very important notion that you must know, which is the CSR, corporate social responsibility. And this is really about what it is that companies, that corporates must do. And you know, it's a great question. Is it mandatory or voluntary? And there's a huge growth, if you can see, that in 2011, only 20% of Fortune 500 companies reported their CSR. And 2020, 90% are reporting. So there's a huge increase in understanding that we have to leave a value behind if we are corporates. By the way, France has a new law that if you have a company beyond 5,000 employees, you have to give 2% for CSR. Yes. Yes, I was about to say that Denmark and Norway are the next beautiful countries. Norway, Denmark, France are the best countries for real CSR. And it's part of their culture, it's part of their innovation. You're from there, so you know, Eugene. And really, what we learned that consumers admit that they want to buy. 53% prefer to buy from high CSR profile company. Investors, 70% want to invest in you. And employees, they want to work in a CSR company. They say they prefer. Yeah, I know what you're aiming for, yes. Okay, so from corporate to individuals, I would just want to go on and show you that what we really speak about, that how it reflects the individual, that we're really looking today for people who live values through autonomous morality. This is very strong. I won't be able to give all the details, but Piaget and his pupil, his student, Kohlberg, they both spoke about heteronomous morality and autonomous morality. It's a beautiful word. Heteronomous morality means that I do something nice, but out of what? I do something good, or I keep the law, you know, everything looks fantastic, but I do it out of fear. I do it out of, I don't want to be caught, I want to be nice, I want to be judged nicely. But if you are having autonomous value, autonomous morality, that means that you chose to be good, you chose to have the values. And we're really looking for people with great signature, with great mind, that to have strong autonomous morality and strong values. Now, if I look at CVs of the 2024, two things that I really tell my students that they must have is vision statement and volunteering work. We're looking for people, like the CSR for individuals, is you have to have community and volunteering work in your CV. This is a must today. It's really a must. And maybe you don't have, I always say, have 1 hour a month even. It's worth it, that you do something for others and you really bring value. Now, I want to talk about values because, you know, let's speak about the dirty word money for a second, okay? I want to speak about it. Because people who leave a mark, you know, they have special treatment of money. And I want to talk about the private piano concert case and to tell you the story of, as I said, I want to share with you some of my incidents. So I have a concert series at the Tel Aviv Museum of Art for many years. And one day I get a phone call and the woman says, hello, do I speak to Orit Wolf? And I said, yes, this is she. And she said, well, I'm your subscriber. Me and my husband are going for many years to your concert series. And next week on Friday night, my husband celebrates 60th birthday. And we want to invite you to help to give a private concert. And she said, I have this beautiful grand piano Steinway, and I have this beautiful house, and you know, I'll send a taxi to bring you and bring you back. And we bring a private chef from Paris. You know, I realize what I'm getting into. And she said, you only have to come and do this concert. So I said to her, thank you so much. It's very flattering, but I can't do Friday night. And she said, well, why? Are you religious? You're not playing on Friday nights? I said, no, I'm not religious, please, but I'll help you to find someone else. And she said, no, is your husband doesn't let you come on Friday night to play concerts? I said, no, it's not about my husband, please. I'll help you find someone else. I can't make it. This is the only day I'm with my family. I have 2 kids, please respect it. And then she said, how much do you take a concert? And there was a silence there, and I said to her, I don't take, I give. She said, don't start with me. How much do you take a concert? I said, well, I said again, I'm not taking, I'm giving. because it's always about you giving, not taking. And she says, okay, let me change the terminology. How much a concert cost? And I said, listen, it's not about money. Please respect my impossibility. I'll help you to find a great pianist who will do the concert next Friday, but please really understand my situation. And she didn't leave me. She was so obsessed. By the way, we love obsessive people in living in Mark and creativity. But she didn't let me go. She didn't let me go. I didn't know what to do. I felt very embarrassed about the situation. Then I said to myself, okay, if she keeps going, I'm going to tell her the best price I've ever wanted. So she's, keeping nudging me. And then she said, so how much a concert cost? And I tell her the number. I know you want to know, but I won't tell you. And I tell her the number, and then it was 30-second silence. By the way, 30-second silence is long on the phone. She's quiet, I'm quiet. She's quiet, I'm quiet. No talking, nothing. And then she says, well, okay. I want half a concert, please. It's half a price, yeah? Good, Evgeny. And I said, no, I'm sorry, Bracha, this is the same price. And then she's really angry, like a very Israeli one. She said, no, I have to understand. I'm sending you a taxi to come from your place to our place. You eat with the French chef. You play half an hour and you take so much money. I said, yes. It's half an hour plus 40 years of 8 hours a day that I practice. And I tell you the story because I want you to remember, and this is something that I want you to take from this time that we have together, that don't be afraid to ask for what you're worth. And really, it is not about the half an hour or the 1 hour. It's about the time. It's about the reputation. It's about the experience. It's about the expertise. It's about so much you're giving. And you're not a taker, you're a giver. So it's really don't sell your hour, sell your value. So we spoke about values in the corporate world, but really take it into your own private individual world. And I know it's hard. I know sometimes it's not realistic. Sometimes we say, oh, come on, eventually you have to sell hours. That's how the world works. But I have to say to you, sometimes it does, and sometimes you can determine and you can decide if you want to sell your hour or you want to sell a project or product or value. So try thinking about it. And again, don't feel yourself as students. Feel yourself as innovators. I don't have much time, but we started a bit later, so I want to really steal some time to speak about disruptions, coping with and generating disruption, because this is a beautiful word we'll deal with in creativity, in leadership, and especially in the academia. This is a beautiful thing. Try to read it. I know you can read it. This message, do you see that? I know you can do that. This message comes to prove how your minds can do amazing things, impressive things. In the beginning, it was hard, but now on this line, your mind is reading it automatically without even thinking about it. Guys, you're not with me. Okay, so Svoboda really showed in 2016 that we don't need all the sources in order to understand and solve problems. And sometimes we say, oh, we don't have the money, we don't have the human resources for this, we can't do it. No, you don't need all the resources. You can actually solve problems without having all what you think you need. And this is really strong because this is a rule about disruptions. It's really about taking you out of your norm, you're out of your zone, and see if you can still read it or can still act upon it. So what I'd love to really show you in two small films is really what I'm trying to teach my students, from the stimulus to the response. Okay, there's a huge opportunity to have responsibility. And when you cut the word responsibility into half, you actually receive response and ability. So responsibility is not something that people put on you, but rather something that you choose to act upon. It's something that it's proactive word. It's not a reactive word. And sometimes we always say, oh, I have so many responsibilities. It's the saying that people put on you. But no, you can choose how you act between the stimulus and the response. And I'm going to show you something really strong about this. And really, it's very, very special because so many people are trying to change the stimulus. Don't try to change the stimulus. We are living in a very disruptive world. COVID, financial disruptions, political disruptions, climate disruptions, interest disruptions, everything is about. So Maxwell said it in a very beautiful way in Attitude 101. He said, you can't change the stimulus, but you can change your attitude towards the stimulus. I think this is exactly what we speak about, leaving a signature, leaving a mark in a disruptive world. Is really about focusing on how you respond to stimulus, don't change the stimulus. So I'd love to show you a film of something that you'll see disruption happens here. Let's together. In London, let's see what happens to him. Hold on. I love this one. And I'll tell you why I love it so much. Because, again, stimulus, the phone rings. By the way, let's speak about the phone rings. 5 years ago, I was in the Concertgebouw in Amsterdam. It's one of the beautiful halls in Amsterdam, next to the Van Gogh Museum. And Daniel Barenboim, maybe one of the most prominent pianists ever, is playing the whole Well-Tempered Clavier by Bach, the 24 Preludes and Fugues in this hall. And I bought tickets in advance, and I come and I hear him. And there was after 20 minutes, there is a phone ringing in the audience. You know what he did? Same stimulus. What he did? Closed the lid of the piano and left the stage. Everybody was so, excited. What's happening? Is he coming back? He did not come back. We all left for a break. And then his agent tried to convince him to come back. He came back and he started all over the beginning. So just imagine how much time wasted we had. And this is, again, it's the same stimulus, different reaction, different responsibility. Beautiful when this guy is not just a great violinist, but he's a great improviser. And we love improvisation when we speak about disruption, when we speak about creativity, when we speak about leaving a mark. We love improvisation. I want to show you another example, which is even better. Are you ready? This guy is Bobby McFerrin, one of the greatest conductors ever alive. And he's not just a great conductor, but he's also a great improviser and leader and key TED talk, and very, very special guy. Look him up, Bobby McFerrin. He's here from America. And he comes to the Israel Philharmonic. This is a real video from 30 years ago. And he does something that is so disruptive, but so powerful. Let's watch and speak what's happening there. What happened? Yeah, here. I love it. Did you like it? Bobby McFerrin. Now, I tell you why it's so strong. I mean, you must realize it. I love it from different reasons. And I want to really talk about it for a second. What happened here, that you see a real concert, but it started from a dress rehearsal. This guy is staying in the Hilton. He gets about 200,000, and he comes in, and usually Philharmonic members don't like guest conductors because they don't like to be told what to do. You know, they're the one who plays the instrument, they're the one who know the music the best, and this guy is just showing them what to do. So they usually don't do what conductors do. And in order to feel that he's, you know, grasping their attention and really creating a teamwork, he's telling them, leave the instruments and just sing your music. Now, when you don't play your instrument, what do you get? What does he get out of this exercise? It's really genius. You know, what does he get? Number one, say it. Teamwork. In what way? It's fantastic. It's great. It is. But why? Why? What does it do differently? I mean, why is it so strong? Yes, because everyone is with his instrument, so worried, you know, that it's not going to put the finger in the wrong place, you know. So number one is telling them to do something completely different. Number two is telling them to sing it, which is so much natural than playing. So people are not occupied with holding an instrument, but actually rather watching people's eyes and watching others and laughing and humorous. But there is another thing which is very great. When you play in an orchestra, you don't have equality. Because if I play the violin and you're playing the horn or the drums, who is stronger? Obviously, right? The man. So I'm not equal. If I'm playing the flute and you're playing the horn, no. You're stronger. So for 1 minute, everybody in the audience is equal to one another. Exactly. Same rank, quality, teamwork, not just say, but do it. I always say, don't say thank you, make thank you. And this is exactly what it is. It's really real teamwork for a minute. And what they loved it so much that they told Bobby McFerrin, why don't we do it really in the concert? Let's start a concert with this. So what we see here is a concert that they actually bringing their rehearsal into action with the audience. And this is about leaving a mark. This is about disruptions. This is about signature. It's so strong, it's so powerful, but look how so easy the disruption was. It didn't cost money, it didn't cost time, it didn't cost an effort. It cost just very smart thinking and small, really small destruction. Well, I don't have so much time to go on, but I just want to finish with two things. You know, disruptions happen all the time, and being a pianist is not like carrying your own instrument. You're going to a beautiful place. Sometimes the pianos are amazing, sometimes the pianos are horrible, and you have no control over it. You don't bring your piano from home. By the way, there are some pianists who do bring their pianos from home. They fly them out, okay? So I want to tell you a story that about already 3 years ago, I go to give a concert up north in Israel, and I usually come about 2 hours before concert, you know, to practice, to warm up. And I go in, and I watch this beautiful Steinway, and you know, Steinway is the best company, beautiful large piano, and these ones are really amazing. And I open the lead, and I see one missing note. It's not the right piano, it's not the one, but I wanted just to show you. And the one who is missing is C sharp, one of the, you know, the central black key is missing. So I tell the person, the backstage officer, I said, David, you know, we have a problem. You've got to call a piano tuner to tune the piano. I can't really, I mean, I can't play like this, right? And the good thing is that I found the key that was missing on the counter on the piano. So I said, you know, it's not going to be a problem. You know, you just ask the piano tuner to come. He will do it. He will fix it. He looked at me, said, what's your name? I said, Wolf. He said, Orit, listen, I don't know where you come from, but here up north in this hour, no piano tuners. Forget about it. You'll manage. I said, how can I manage? You know, it's in the middle of the piano. I cannot manage. You know, it's not it's not in the side of the piano. It's right in the middle. How can I manage? So he comes, he takes my seat next to the piano. I said, what's your name again? I said, Ori. He said, how much you have here? 100? One less, who cares? So I realized who I'm dealing with. I said, David, I have a great idea. You don't tell anyone. You bring any glue you find, and we're going to stick that key into the piano, and you don't tell anyone. Now, you don't do this when it's a Steinway. You just don't do this. This is a very expensive piano. But we did it. We did it, and I never, people asking me, where is it? Where is it? I never tell where it is. I don't want to be sued anywhere. But this is a real story, and it's really about disruption. So we really, really want to, I want to tell you, the disruptions happen all the time, all the time. It's really about not the stimulus, but how you deal with the stimulus. Just to end with, this is it, yeah. I won't have the time for this, but I want just to finish with disruption through biassociation technique, which I love. Biassociation is a notion you should know. It's a notion created by Kostler already in '64, and he talked about biassociation with this double association. It's two ideas or two ideas or two, I would say, objects, right, that connect to one another in a nice new way that create an added value. So we started with value, and I'd like to end with some value. And look at this, it's very funny. Look at this, beautiful biassociation. And you watch it and you say, oh, this is great, how I could not think about it earlier. This is so simple and so great. And look at this. You have an empty hand to shake hands when you have this. And this. Or this. Or this. This is so nice. So simple, so powerful. Disruption. By the way, this won so many prizes because it's so simple. It's nothing. It's really using the material to create something else. It's so special. So just to say, you know, what I love to end up with is this woman, Tamami Honma. She studied with me at the Royal Academy of Music. And we studied with the same professor, Christopher Earlton. We worked really hard, 8 hours a day, practice. The only day that the Royal Academy was closed was Sunday. Sunday it was closed, and we would meet in Piccadilly Circus. You know where it is in London. It's a very central area, and we would go to Chinatown, we'd go to anything. And then she would take me, this lady, to the best streets, the new Bond Street, the old Bond Street, Regent Street. Now, even if you don't know London well enough, you must know those streets. And I see the smile, especially of Sasha. And you know what the streets are about, right? They're about what? One word. Best shopping. Yeah, really the best shopping. And you have all those stores of Prada and Gucci or Hermes, Tiffany, whatever. And she would go in and, you know, she would try everything possible. The nicest gowns, the nicest performing dresses and jewelry. Now, you have to understand, we were living on 80 pounds a week. $29.99 was the pass for the train, the weekly train pass. So we really went from one place to another, teaching privately, and we didn't have much money, but it was hard. And she would still go in, and she would try all those dresses and all those jewelry in Tiffany. And I would say to Mommy, why do you do this? We don't have the money to do this. And she said, well, we'll have the money. I'll know where to go and what to buy. And one day, Tamami became very rich. I mean, she married a husband who was very rich. No, I'm kidding. No, I just say to see if you're still awake. No, she married a rich husband, that's true. But if you look her up in the internet, you see that she's one of the very great pianists. And she has Deutsche Grammophon albums, and she has 4 boys. She lives in the West Coast. She's teaching really in the best places, and she's very famous. And what she told me, this woman, something that I want to end up with, she really told me that if you have the fantasy, if you have the dream, you're going to have it. And till today, she sends me the best stuff from Tiffany, and this bracelet that I'm wearing, that Sasha is asking me where is it from, is from Tamami. She used to send me this to Israel. Now, this is not a lesson of materialistic life. Don't take it to there. It's easy to say, oh, materialistic life. No, it's not about money, it's not about materialism, it's about people who dare to dream. And if I am to look at what we talked about, you know, the ability to have disruptions, the ability to look at the experience, the ability to make disruptions, and really it is about the ability to dream. If you have the possibility to, and most people don't let us dream. They want us to be so active and so efficient. And the best musicians, the best composer, they say, you know, we are so creative when we don't do anything today. So try not to do so much. Just because we are really working in between the lines, in between the words. There's a beautiful saying, and I'd like to end up with this sentence, that music is not the notes. Music is not even the sounds. Music is the time we take between the notes. Now, this is not about music. This is about our lives. What are those gaps that we take to ourselves, to reflect? What are those gaps we take to raise our hands, to raise our eyes, and to look at others, to listen to others, to be attentive listeners, to reflect, to have critical thinking, to enjoy, to just be. So I think that people that you know that leave a mark and have strong signature are those who take the gaps in order to create, to generate. So let's all take the gaps and make music. And remember, it's not about the story we tell to others, it's the melody we choose to accompany our stories. Thank you so much.
Yeah, thank you very much. The inspirational talk is just wonderful. Are there any questions? Yes, immediately, yes.
Thanks for the best talk of this one.
Indeed. Definitely.
Because I was thinking myself, I'm not belonging here. It's not my natural place to be here. But I'd love to have this as a tradition and to come back. Next time I'm coming back to play with you a recital and to really show what I'm talking about, not just to talk. It's very special. And I wish I had more time to show you other stuff, but we'll save it for next time. Thank you so much. Any other one who wants to share or, yeah? I can't hear you. What is it?
You mentioned about 10,000 hours, the common theory that you need 10,000 hours to become great at something. There is actually some work done by some scientists on, especially on musicians, for example. Like all musicians don't play the same instrument for 10,000 hours to be great at in an orchestra setting or in a philharmonic orchestra setting.
As I said, the Malcolm book about the 10,000 hours, I think it's a gimmick. Sorry, I think it's a stupid gimmick.
Yeah, I also agree. That's
yeah,
my general
who
point.
cares the 10,000? Why is it not 11,000, right?
No, it's more general. Like I can play 10,000 hours of chess. I'm never gonna be Magnus Carlsen.
Exactly. So it's really not about the hours, but as I said, the hours are only acquiring the skill. But if you want to put your own soul and really to carve the music to be your own, because if you think about Arthur Rubinstein, if you think about Glenn Gould, if you think about Daniel Barenboim, those people have a very special sound that we can recognize their sound. How they do it, not because of the 10,000 hours or 20,000 hours or not 30,000 hours, because they really have some innovative flair into their actions.
So our next session is going to be led by Dr. Eric Garcell. He's a technical marketing manager at Classiq, which is revolutionizing the process of developing quantum computing software by taking quantum software to a higher level. Dr. Garcell was previously innovation product manager for IP.com and an innovation research scientist at Kodak Alaris. He has a doctorate in physics from the University of Rochester and a master's in technical entrepreneurship and management from the University of Rochester Simon School of Business. Welcome our next speaker.
Oh, it's showing all the bottom bits. Is that all right? Yeah. All right. Good, good. Whew. Okay. Well, that's going to be hard to follow. That was amazing. Oh my gosh. So I got to figure out how to pivot and make sure that I can work with that stimulus. And yes, actually, one thing I did want to say for everybody, all the brave souls who have survived this long in the workshop, and for the talks, I brought just a ton of these laptop notebook cases from Classic, and I think there's enough for everybody with the number of people who survived this long. So I'll leave them up here on the top table, and everybody can grab one before they head out. Just as a small thank you for coming to the last workshop of the summer school here. So we're going to be talking about quantum computing, because that's the theme of this whole summer school, and we're going to be working on essentially quantum computing for end users. I was hearing a lot of the conversations going on the past couple of days, and kind of in the spirit of pivoting and working with the stimulus that's going on, I wanted to gear this a little bit more towards some of those questions. I heard a lot of business-focused questions. A lot of the lectures have been more academic-focused, hitting on research papers and things like this, but I wanted to go ahead and answer some of these questions I was hearing sprinkled about. So actually, before we get started, because a little bit of this is going to be a lecture, a little bit is going to be hands-on and workshop. So before we do get started, if you can go to platform.classic.io, create an account. You just type in your email address. You'll have to go into your your email afterwards and click that confirm button to make sure everything is all right there. Feel free to join our Slack community as well. And we also have a Python environment. So we will be going into the Python, so do your whole pip install classic. And just to get you started off so you don't have to copy all the code from scratch, I created a small tiny URL actually while I was sitting in the back of the room there. So we can speed this up, and so you have some code to start off with so you don't have to type it all out. We also have plenty of documentation to go over and have fun with, and a GitHub with a lot of really fun examples that are going to go much more deep dive into anything we're talking about here today. And since I'm seeing about half the people left have laptops, we will do at least one exercise. I'm going to try this out because I haven't done this before in a workshop. I'm going to try, we can all try and do a quantum algorithm on our phones together. You still have to get logged into the platform and have an account, but I think that's going to be fun, and you'll be able to say that you ran a Grover's algorithm from your phone. That'll be a fun one. All right, so some introductions. Now, Classic is an end-to-end software development platform. I'm sure you've seen plenty of these already. Kind of what sets Classic apart is that it's a programming framework and high-level modeling language, and it enables hardware-agnostic generation of your quantum code. Here's just a fun GIF I made the other day of kind of navigating through the platform. We have a friendly user interface, the IDE, and we'll be going into this as well as the Python as well. And a little bit about me. So this is the about me. I will get to the how about me and how I'm feeling, but I'm the head of technical marketing, as I was introduced. PhD in physics, master's in entrepreneurship. So I have all the skills necessary to help a business start off, but as soon as the company hits IPO or anything like that, I have no idea what to do and I should probably leave. I'm the father of 2 young daughters, and like I said, I've had quite a bit of odd experiences in my past, and kind of as the head of technical marketing and frankly as a physicist who likes to talk, I get to go to a lot of fun trade shows, meet some interesting people, talk to some people from HPE, from Google, AWS. The bottom left there is a course I taught at MIT for a little bit. It's some selfies with quantum computers, because whenever you actually see a quantum computer in person, it's fun to take a selfie with it. And just kind of showing you there's no one path to quantum computing. There's a lot of different ways to get into the industry, and it depends on what you want to be doing ultimately in that industry. Do you want to be working on the hardware? Do you want to be working on algorithm development? Do you want to be on the academic side? Do you want to be helping a corporation develop applications for quantum computing? So there's a lot of ways to get into it. And for the most part, most of them are interdisciplinary. You need kind of a mix of skills to get into this industry and to really be an expert in any of these kind of job titles. Now, I'm a technical marketing because I'm a physicist with a business degree, and I just like to talk, frankly. And apparently, if you're a physicist who likes to talk, you will have an easy time getting hired. There's lots of companies out there who just need somebody who knows the science and wants to talk about it. I've had brilliant professors out there who had technologies that could literally save people's lives, and they could not tell you why it was interesting without giving you a 2-hour lecture. Just the ability to say in a couple of sentences, why is this cool? Why should people care? Is a skill that not everybody has, and if you have it, use it. So we're going to go into some pragmatic quantum computing concepts. Like I said, well, yeah, pragmatic quantum computing, first of all, it's complicated. There's a lot of nuanced considerations when you talk to companies about how do you integrate quantum computing into their infrastructure? What does that actually mean? And as somebody who's talking to clients, going to these trade shows a lot, I hear a lot of what end users are wanting, expecting from these systems, how they enter the market, what they expect out of it. So a lot of things they're looking for at the end of the day, they want to have a couple of KPIs or metrics to benchmark against, and things like, what is that time to solution, right? It doesn't matter if, Grover's algorithm gives you an exponential speed up in the computation. If it takes, super long to compile, I'll get to you in a second. If it takes super long to compile, you lose out on any of that advantage. And yep, what's up? Yeah, there's yeah, exactly. But there's other algorithms that give polynomial speed up, exponential speed up. Depends on the algorithm, but yes. But essentially, right, the point's still the same. If it takes so long to load the data in, to have the data returned out to you, you're gonna end up losing out on any of the advantage that the algorithm was supposed to give you. That kind of time to solution, the holistic approach of when it, from start to stop, including the software aspect and algorithm development, including the hardware stack and integrating with the hardware. And if you're looking at, HPC integration as well, and a lot of companies are trying to figure out, how do I connect my quantum algorithms to my, Cray supercomputing cluster, that HPE has, or different supercomputing infrastructures. They want to know what that final time to solution looks like. They want to know what the cost is incurred if I used quantum versus classical. And in a very pragmatic sense, not saying I'm using the best supercomputer and, that's always, right now, the best supercomputer is going to beat out any quantum computer on computational tasks, but not everybody's using the best, most expensive supercomputer, right? People are using suboptimal strategies right now in their daily technologies, in their infrastructures, and they're investigating, how much does using quantum actually cost me at the end of the day? What are the charges that AWS has, for their hardware versus IBM, and how does that compare to our current deployment? Could we see some financial gain, even if it's, the same accuracy result? And that's the last one. The accuracy of solution is something that people are looking into, and different businesses value the three of those aspects to different weights, so their KPIs are all going to be different on that company. But at the end of the day, these are the three factors that almost every company wants to see and benchmark across at the end of their journey, at the end of their skunkworks projects that they have their engineers on. And most every Fortune 500 company has some at least small quantum investigation or quantum team investigating it, right? You saw JP Morgan was talking here before. They've been doing quantum for a very long time. In fact, they, if you haven't seen it, and a couple of people are asking about some of the more near-term applications of quantum, they have a really good Nature review paper they published late last year in quantum finance. Figure 1 is a really cool chart that just shows near-term, long-term applications of quantum finance. And I can show you that paper in a little bit too, but a lot of companies have been doing this. Most automotive companies are investigating it to different degrees. Some are looking at it for, better EV batteries for their renewable cars. Some are looking at it, for some of the AI aspects and, self-driving things. I was just at NVIDIA's conference a couple of, like a month or two ago, and everything there is AI and robots, and there's become more and more quantum dialogue in all these supercomputing conferences and automotive conferences. It's getting into these industries more and more, and they're investigating, how do I deploy this? What should I be doing? And frankly, when will it apply for me? And that's always the question, the when aspect. And it depends, right? There is no one answer to that question. Anybody who gives you a straight answer on it, it'll be 3.5 years. Hot no. Every answer depends on what the end user is trying to do and how sensitive they are to errors at the end of the day. So to actually talk about this holistically, you need to look at what the hardware stack does look like. You have to understand that fundamentally. I love the pancake analogy shown before when IonQ was showing it. And it's largely the same, right? You have your QPU, your quantum processing unit, right? At the end of the journey of all this, quantum will be integrated into the HPC stack, right? You'll have CPUs and GPUs, and you'll have a QPU. But right now we're not quite there. We're getting there slowly. So we have, the quantum processing unit. It's being read out by some control and readout electronics, handled by some microarchitecture. It goes to the instruction set architecture, which just pretty much says, how do I interpret all these gates and tell my hardware, how to rotate those qubits into laser pulses and whatnot, or however you're, putting that data in there. And above that, you have your compiler and transpiler that takes your higher level code and brings it down to that assembly or machine level code, frameworks that might go around your programming. And then with all that framework and programming, you can build some pretty cool applications and algorithms. Now, along with that, also, there's different levels of coding, right? That one programming block has different levels to it. You can program at kind of the machine code level, and all of this, there's lots of jargon in every industry, but everything in classical, everything in quantum computing is mirroring classical, right? So, machine level coding is essentially pulse level coding, right? The laser pulses you're sending to the different hardware infrastructures. Gate level is just assembly level coding. And some people have called it utility level coding, but just higher level architectures for programming sits on top of that. And the further you get away from the hardware itself, the easier it gets to code, the fewer lines of code you have to write, and the less fundamental minutia kind of quantum knowledge you have to have, kind of the less you have to interact with the block sphere. And frankly, there's a lot of competing technologies for both the hardware and the software end. My company's on the software end, so I always like to give a fair share to the software. I think hardware gets a little bit too much time in the limelight, so I always like to give equal time to both. Now, there's lots of different hardware modalities. Right now, there's a ton of different technologies out there, right? I tried to list it out as far as kind of technology readiness levels. If you're writing grants, that's very familiar for you. Just shows you how advanced is that technology, how close is it to being deployed and just readily sold without much hassle. Kind of superconducting trapped ions are right up there, right? IonQ is a trapped ion. A lot of other companies, QEra, kind of in that 3 to 5 range, they just sold a ton of quantum computers, actually. I think to Japan. It was a big announcement. And the industry always loves to see lots of hardware being sold. That means it's a good and strong industry. Now, there's a lot of other really cool technologies, right? Photonic qubits, solid state, topological qubits that Microsoft's starting to investigate there. Some of these technologies could scale faster than superconducting qubits, but it depends, and we'll have to see. But ultimately, from a business standpoint, 2 or 3 of these methodologies are probably going to survive the long run, because OEM manufacturers, people making the parts for these computers, have to consolidate to lower the price of the machines overall. I feel like it's almost the same as, if anybody remembers, when there was like the difference Blu-ray players and high definition discs. And at some point you had to decide, am I buying my new movie collection in one set or the other? And one of these is gonna die, and I don't know which set I should have my movie collection in. And if anybody invested in HDD, I'm so sorry, you can't watch those movies anymore. Even though, the technology was actually, arguably better HDD than Blu-ray, there's a lot of business, applications, a lot of business considerations that go into why certain technologies survive, different partnerships, marketing plays into it. So sometimes it might not even be that just the strongest technology wins. It could be for a number of different business reasons that a technology survives for. So it's really anybody's race on who is going to win this, quantum race on hardware end. But thankfully I made a graph on kind of where we have been on quantum and kind of the future projections of quantum. I got to say, this is the first industry I've worked for in innovation where the industry actually kept its promises, right? If you look at the roadmaps for like IBM, every year they say they're going to have a hardware out. They actually did it, right? This year they had this hardware, that year they had that hardware. They just came out with Condor, right, like 1,000 qubits. This really is an industry that has kept to all of its benchmarks, all of its roadmaps, and for a technology as advanced and kind of futuristic sounding as quantum technologies, you'd imagine we'd have hit a hurdle at some point. And it's more that it's not that we haven't hit technological hurdles. It's more that the industry is so transformative. There's so many possibilities enabled in this. Governments are involved in this and wanting the technology. So many people want this for various applications and for what it can do, that whenever we hit a technological hurdle, money just gets pumped into the industry hard enough until we pass that hurdle. So it really does show that so many people want this for various reasons. Governments want it because, one, they're worried about kind of Shor's algorithm and everything it can do there. The other is that there is this kind of, HPC race almost. There's always been the US and China who has the biggest supercomputer. Now it's who has the biggest quantum computer. And being second best doesn't quite cut it. So that's why there's also now export controls with quantum computing and things like this, because the US wants to keep its dominance and its knowledge and hardware in house. So there's a lot of reasons why it's advancing and continuously advancing, and why with all of this growth, it makes investors more trusting of the technology and able to continue investing to this degree. Now there's a lot of different languages. I won't stay on here for too long, but QMod is Classic's language, right? There's OpenQASM from IBM, there's Q# from Microsoft, PennyLane from Xanadu, right? And they all have their strengths and weaknesses, and it depends on what you're trying to do in quantum and what you want to enable and have as your end result. But there's multiple modalities, and people investing in quantum for their company wanting to investigate it have to figure out, okay, what am I teaching my developers? Which of these languages do I start off with? What hardware should I use? It's a big Venn diagram of, how should I mix and match the languages and the hardware, and what to use and why, and what's the right answer. So it's a difficult question to answer, and it partly comes down to also, at least clients who come to Classic end up coming to us because they see what we call the software challenge. It's that they've started off in some other programming languages, they've done computing, they've done the IBM, onboarding, they've rotated your block sphere, they've used Hadamard gates, and they find out that kind of programming at this Hadamard gate, CNOT gate level, it's not really scalable, right? If you try and do a circuit of 100 qubits, it starts getting really tedious putting in your Hadamard gates. And if you look at this, right, even just visually, it starts getting quite cumbersome to look at the intermediate representation of quantum computing, right? If you're dealing with single digits, it's easy to see. If you're dealing with tens of qubits, okay, I can still kind of get what's going on. Once you get to hundreds, it's gibberish. I can't tell what that code's doing anymore. Actually, at tens of qubits, I'm kind of lost already. But it starts getting quite difficult to both program, debug, review other people's codes, maintain that code. And essentially, without higher level languages, right, whether it be Classic or other programming environments, the industry does need to move over and move towards higher level dynamic languages. This happened with classical computing, right? We didn't stay with punch card programming forever. We developed higher level coding environments and coding platforms to enable and use the hardware that's coming out, right? Condor's 1,000 qubit quantum computer, I don't want to be programming at the gate level, certainly. So Classic, right? So I talked about this already, just to recap there, right? Classic is a higher level modeling language and end-to-end framework for quantum computing. We'll take you all the way from modeling your quantum language at this higher level, generating out your quantum circuit, visualizing it, and then executing it on any hardware vendor that's enabled on the cloud. QMod, our language, it's a declarative programming language. So that's most of the other languages that you're familiar with in quantum computing, like IBM's, like Microsoft's, they're imperative programming languages. You have to define kind of what you want to do one step at a time throughout the program, versus the QMod language, which is declarative. You say the functional intent of what you want that quantum circuit to do, and our synthesis engine will generate and compute for you the efficient quantum code that generates that. Now, kind of as a simple, that's kind of hard to say there, example, we have a couple of functions here where I'm just saying, I have a function, allocate 3 qubits to A, and then do quantum Fourier transform in A. That would be, probably 10 lines of code, nothing too large in assembly, but still, it's fun to go from 4 to, 20 there. Or just addition, and we'll go over some actual addition problems later, but I'm just defining out some integers. I'm putting integer 3 into variable A, integer 5 into variable B, and then I'm doing some maths on it. I want my result to be A plus 2 times B. I'm not telling the system, how do I implement this to the hardware at the quantum level? How do I enable variables into my qubits, and how do I rotate the probabilities to make it those integers? I'm telling the system what I want the functional intent of my quantum circuit to be, and the system's going to deploy for me and create for me the quantum circuit that enables that. Now, what helps with that is a synthesis engine, right? It takes that high-level code, it turns it essentially into a constraint satisfaction problem and finds the optimal solution for you. And there's some optimization parameters you can put on your code, like you could tell it, I plan to run on IBM Nairobi's computer, and it knows the native gate set for that hardware. It knows the qubit connectivity and will give you appropriate quantum algorithms and appropriate encode for that hardware in mind. Like in the last edition, I didn't have to worry, should I use a quantum Fourier transform adder or should I use a ripple carry adder? I don't have to know every way to do addition in a quantum computer or for any other algorithm, for that matter. The system will choose the best implementation for me, as well as do kind of end gate cancellations to make sure the code is both efficient and optimal for the hardware I plan to run on. And right now, that's not a trivial thing to be doing by hand. If you're trying to switch from like IBM's hardware to a Microsoft hardware, there's different native operations on there. There's different circuit connectivities, and building efficient quantum code is difficult if you're trying to switch between them, but also it's important. We are in this NISQ era. The hardware is a bit error prone, and the shorter and more condensed you can make your quantum code, the better. And frankly, also a lot of clients of ours come to us because they don't want to be stuck in any one kind of cloud infrastructure. They want to be able to deploy on IBM and AWS and Microsoft and try out the different hardware. And this higher level language lets you compile out to any of these encodes. It can compile out to, CASM, Q#, any of them. The visualizer is a fun one too, kind of an interactive visualization tool. We'll play with that together in a second. You can kind of expand out and see how the system went ahead and implemented your code. And kind of the last bit here is the universal executor, right? We're integrated with IBM, Microsoft, AWS, IonQ, Google, NVIDIA simulators, right? We're now integrated with CUDA Quantum, which is very fun. So hybrid jobs are very easy to do now on actually HPC structures. But in our GUI, we make it a drop-down list. You don't have to figure out what is the API call for this hardware versus that hardware. It's a point-and-click interface, and you can go ahead and execute quite simply. So how does this all actually come together? If you're interested, you can go ahead and scan this. It's a short kind of 3-minute demo if you'd like to see it, but for time reasons, I'll go ahead and skip over that one. But at the end of the day, what it does show is that Classic, you get to program your quantum algorithm, it requires fewer lines of code, and you get more efficient quantum circuitry at the end of your journey. Right, you have faster time to computation, you have more efficient quantum circuitry, and because it's a higher level code, you need less expertise in all the different hardware modalities and in quantum, how to manipulate the block sphere, just faster to deploy, right? Some of those circuits we were showing you, that quantum Fourier transform one was 3 lines of code for us. If you did that in OpenQASM, that'd be 70 lines of code. The adder was 7 compared to 142. If you do something like a Grover's, and we'll do that together too, is 11 versus 670. So higher level languages are just what's going to enable quantum computing, whether it is Classic or other platforms. And what's important to say is that it's free for academic purposes. So if you're doing for research, if you're a student, if you're a professor, Classic is entirely free as long as you don't try and sell or the code you come out with. So don't go and run off with this and be a consultant for other companies. But for the most part, feel free to have fun. In fact, I'm talking to some people about doing this for their quantum game clubs. We work with a lot of different universities. Actually, speaking of universities, I'll talk about that in a second. But case studies. The way we work with a lot of clients is they come to us and they want to know, how can I use quantum computing? What can it apply for? So we made just a quick chart just for fun, showing some of the major quantum algorithms, how it can be deployed, and how the same quantum algorithm can be beneficial across industries, right? QAOA is great for optimization, but almost anything can be thought of as an optimization problem, right? I was talking to somebody the other day about how they wanted to optimize whiskey barrel placement. And I had to think about that for a second. They were explaining to me that the different heights in the whiskey barrel room have different temperatures and humidity gradients. And you stack the barrels so many deep as well. So when's the next time you need to shift it around? And as my developers say, if you think about it hard enough, yeah, anything could be kind of turned into an optimization problem. HHL is really good for kind of systems of linear equations, which comes down to things like a lot of physics simulations, like computational fluid dynamics. which at the end of the day is going to play into larger narratives you hear in some of the industry conferences, certainly I go to, like digital twin simulations. That's a big kind of sphere that NVIDIA's in. Like I tell reporters or different people in industry, quantum computers aren't going to replace classical computers. They're not going to replace the GPU, but they are going to further enable those technologies, right? Some computational tasks like computational fluid dynamics are going to be offloaded from the GPU and run on the QPU because it's less computationally intensive in the same way that tasks were taken off the CPU and moved onto the GPU when that was developed. So it's going to enable a lot of different industries, speed up a lot of industries, and let us do some things that we weren't able to do before. So we work with plenty of universities, but like I said, that's kind of easy to say since we're free for universities. Actually, Carnegie Mellon sends us some of their videos from their classroom, so it's always fun to see how students interact with the platform, the questions they ask. And we have the Slack channel like I showed you. So actually, generally, whenever I see about 5 of the same question get asked in the same 10-minute window, I know that homework's due later that same day. So it's always fun to see that and help them out and figure out just, okay, how much time do you have? So I can figure out how much time I have to help you out. And we work with lots of clients as well, right? We did a fun project with Rolls-Royce and NVIDIA on computational fluid dynamics using HHL. We've worked with KPMG, kind of a major consulting company, and they looked at a whole bunch of different quantum applications to help their clients and figure out quantum. NTT Data was actually one of our first clients. They were doing a credit risk analysis, and they liked the software so much they became an investor. So that's always a fun accolade to say. We released a blog actually at Citibank very recently on doing portfolio optimization on AWS hardware. And that's just a fun one to go into because they're looking at cost functions and how to optimize cost functions to hopefully get a near-term return on investment. And some clients have even made GUIs off of our platform. So this is Infosys, another consulting company, but they were just showing their clients how higher level modeling languages can enable GUI applications, right? That's something that isn't possible when you're building things at this gate level, hard-coded methodology. You can't have a variable input. So actually they're just doing a traveling salesman problem where they are putting some pins in a map. This is the map of London here. It does some computation and they get the results back comparing the quantum versus the classical. And at the end of the day, that's what a lot of managers want to see. Quantum isn't beating out classical right now, but they want to see the apples to apples and in a way that makes sense to them. It translated it, or Infosys translated the computational costs, translated the solution that they got out of it into how long does it take for that driver to take that route and what's the gas cost involved, and comparing those two numbers, quantum versus classical. So with higher level modeling languages, you can create GUI applications that make sense to larger audiences, make sense to more people you're working with, and kind of takes quantum out of this purely science field and lets people see, okay, this is something I can use. It is something that's deployable, usable. I just pointed, clicked, and used quantum. That's so cool. Kind of the same way that IBM put their first 5-qubit quantum computer on the cloud. It's that next step in enabling quantum and making it less of a high-tech future in far in the future technology. Showing people what can be done today is important. So we're going to be getting into the hands-on portion of this, developing some quantum algorithms. So if anybody hasn't already gone ahead and gone to platform.classic.io, please do so now. Create your account. If you haven't done your pip install classic, do that now. And the tiny URL there is simple enough. It's classic start. All right. So for those who don't have laptops, let's have a little bit of fun. I'm actually going to go into the platform and show you, but I might even follow along on my phone as well. So if you're on the platform, so everybody, I just want to make sure everyone's good to start off. Has everybody made an account? Okay. Seeing some nebulousness. Okay. Just in case anybody hasn't, I just want to ask questions to give you some time. So I was actually curious, how many people in this room are undergraduates? Can you raise your hands? Okay, 2 brave undergraduates. Are the rest graduate students generally? Actually, raise your hand if you're a graduate student, because people just might not be raising their hands. Okay, cool. Very nice. So mostly graduate students, some undergraduates. And you know what? This is a one I like to ask too. Let's see, probably the best way to do this would be like this. So if you've created a quantum circuit before, raise your hand. Okay, we have 3 people who've made quantum circuits. Keep your hand up if you've made a quantum circuit that's more than 5 qubits. 2. Okay, how about more than 10 qubits? Oh, okay, more hands rose there. Okay, that's physics for you. I don't know. What's the largest quantum circuit you've built? Yeah. All right. Cool. Okay. Well, I will definitively say that by the end of this, if you're using your phone, will far surpass 10 qubits. And on your phone, right? That's kind of the cool thing that we want to show, that where quantum is and how we can enable this. So if you're on your phone on platform.io, let's go to model. Now, the phone isn't the most optimal, so actually if you have a tablet, that's a little easier. Of course, laptop is what this is made for, but it's always just fun to show that it's truly universal, right? You don't have to be stuck to a supercomputer to create quantum circuits, and it doesn't take all that much to create some cool stuff. Here was actually, I was making some interesting code for myself. I'll just copy that over so I don't lose it. But for everybody on the phone, just go to Grover Search here in the built-in apps on the side. Click Grover Search. It should be pretty quick to get to. And you know what? Right in the expression, we're just going to simplify this. So this is a easy GUI interface for the Grover's algorithm. We're just going to type in A plus B plus C equals, I don't know, let's put a number into it, 10. There. And to make sure that our system is something that we can actually run at the end of the day, if you go down to constraints, set that to 25 because that's the maximum number of qubits our internal server simulator can handle. And I don't want to wait on the queue for actual hardware right now. I think that'd be a bit too long for everybody's waiting for. So under constraints, we're going to say 25 on that. When you're all done with that, just click this little apply button. It's going to go ahead and convert that code for you within that interface. Just shifted it around. And we have this GUI interface so you can do some really interesting quantum circuits pretty quickly without having to be an expert in our syntax. So kind of all the things on the right are just being translated to the code that you're seeing in the middle of the screen. And once you're done with that, click synthesize. And this is being sent up to our server live. We're going to be generating our quantum circuit. All right, let's see how long this takes. There we go. All right, so we just generated out a 10 qubit, 267 depth quantum circuit. We can open it up, see, the Grover search. You have your Hadamard transforms, Grover operator, Oracle, and your diffuser. You can open up each of these and see how it was computed. What arithmetics were happening in there, what form of adder it chose, and it chose a QFT adder in this case. And let's go ahead and execute that. And yeah, just for simplicity again, just choose classic simulator. Check off that tick box on simulator. Put in your favorite number of shots. I don't know. I'll just put 1,000. It's a good round number. And click run. All right, huzzah. We have our answers from our Grover. A equals 3, B equals 3, and C equals 4. Life makes sense. Good stuff. Okay, so who was able to follow along on that? All right, did anybody actually do that on their phone? Oh, okay, no phone users, sad. I was hoping somebody would use their phone on here. I did it on my phone actually to test it out. It does work. It's a little bit hard to get to that interface. It's a little squished. Tablet actually works phenomenally well. And I've been thinking about, very cool. Yeah. Okay. So, we just generated out, how many qubits was that? What was it? I said 10. Yeah, 10 qubits. All right. So we matched you on that in a couple of, I don't know, a minute there. Building a Grover's operator, all the way from modeling it to generating that code to executing it on a simulator. If you ran it on actual hardware, it'd take you a little longer because you have to wait in the queue for all that. But like I was showing, right, the queue, just pick your flavor of the month on which cloud vendor you like to use. And if you wanted to use one of them, right, let's say if we're doing IBM's hardware, you can open up one of their hardwares, see if it's online, how many qubits it takes, depending jobs, and even see what qubits you're going to be using on that hardware. Now, if I were to click run on that, it's just going to say, can you type in your access token for the IBM Quantum Experience. You'll type that in, it'll hook you up to that. But anything on our servers, the NVIDIA simulator, our simulators, all free to go through without any extra click-through or access. Now that we've gone ahead and done that, let's check the time here. Ooh. All right, let's go into that Python SDK and we can go a little bit deeper, right? So that was the kind of integrated development environment. Really easy for a lot of clients and first users to get a handle of Quantum, start using some code, develop it, all within a nicely packaged interface. They don't have to do any pip installs, don't have to make sure that their Python package is updated. And frankly, that always causes a little bit of headache when you do kind of 100 people room. Someone in there is going to have some issues with Python. So in case that happens, I'm sorry ahead of time. All right, so who is able, or I guess, is anybody having issues with downloading that tiny URL? All right, that means I gave my Google Drive the right permissions. Perfect. You never know. Sometimes I forget to say share all and let everybody have it. Cool. So when we get into here, make sure that you do your pip install here, that it's the beginning. Let's clear that out. Here it's just saying that if you're not a new user, you don't have to worry about this step, but let's just click it. If I clicked it to true, it would give me a big fat error message saying you've already authenticated, stop trying to authenticate. It'll too many tokens. I'm just going to import everything because I don't like to go ahead and import every single package under the sun as I'm using them. It becomes a little tedious at the end of the day. But showing you a couple of examples. So seeing the time here, I want to make sure that we go through a lot of fun examples as well as allowing time for questions. I'm probably going to breeze through a lot of this code, show you some more of the breadth and sweep of the platform as far as what's able, instead of kind of following along and have you do some challenge problems, things like that. But if there's any questions or applications that you're interested in seeing, we can go ahead and navigate to that directly right after I just go through some of this basics so you understand kind of the simplicity of Classic and the pivotability of it. So this first function that we're going to be going through is just preparing a state, and we're preparing a probability mass function, right? We're initializing 50% probability of being in 2 quantum states. And in Classic, you can load in, Gaussian distributions, log normal, whatever your data looks like, amplitudes, you can load that in freely. And we also have in here, terribly important, doesn't get talked about too much when you're doing state preparations, is an error bound. When you're dealing with Gaussian distributions, larger data sets, more complicated probability mass functions, you have to figure out how closely do I want my probabilities to be dialed in. The more closely, the less error you want in that system and that data input, the deeper your quantum circuit's going to be. If you're okay with more error, it's going to be a lot shallower because you don't have to dial it in just as so. But that really does depend on how sensitive your end data, your end result is to the input, right? If having a little bit of error in your input doesn't affect your output too much, you can go ahead and sway that number. But it does depend on, every one of your applications and what you're trying to do at the end of the day. I always say, how circular can you make your cow and have your end answer still come out and be valuable? So it depends on what you're loading in and what your end result is trying to get to. So just showing that, right? Prepare states. I'm just doing 50% probability in the first one, 50% probability in the last one, outputting to variable A, and my bound is 0.01. Now, we're dialing in some pretty simple states, so it's just going to give us the exact answer, no problem. But if anybody's wondering, the error we use for this is L2, the L2 metric. Now, the second example, we're going ahead and doing some addition, right? I go ahead and I'm preparing this probability mass function and an integer. And I'm just saying prepare integer, prepare the integer 3 into variable A, and then again, just do some maths on that. I don't have to go into any of the fundamental quantum of it, except for the probability state. My data is quantum, but my end result, I'm just typing in what do I want that quantum circuit to do and execute. And I'm talking about this all in the agnostic. Let me just actually go ahead and run this code because it's more fun to see this whole thing go. And when you click on any of these and it generates your quantum code, you're going to be brought back into the integrated development environment. You can see that code. You can dynamically interact with it, see that Bell state preparation you created, see the adder. And again, right from here, you can go ahead and execute that. I'll just pick the simulator again for brevity and run that code and get your results pretty snippily. All right, we got 2 results from our addition, and that makes sense because we're adding 50% probability mass function to an integer. And our result is 3 is when A equals 0 and B equals 3. life makes sense. That's always good. And result is 6 when A equals 3 and B equals 3. So all of our quantum physics still makes sense. We're getting the right results we want. And because of the coding infrastructure and the way we dialed in our outputs, we're actually getting our results in human readable text, right? You don't have to go ahead and try and interpret what 111111110 is as far as a chart there. And that all comes in from these outputs. I said my results, I want output as a quantum number, A as a number, and B as a number. So I'm getting my results out that way too. And this is essentially defining out how you call out all the functions in Classic. You need to have this main function declaration. How do you encode superpositions, integers, maths. And really, once you're done creating your, what you want to be coding in, you define out, just create my model object, then synthesize that model object, and then I can go ahead and, visualize that model once it's synthesized out. Some info if you're curious on how to generate the syntax, if you want to go ahead and do this for any projects. And this was gonna be one of these that you kind of do on your own, but we'll just talk about it together. Just again, a couple of prepared states put together. We're doing some addition, slightly more complicated, but we're just doing, some 1/3 probabilities and things like this with the same bounds. Now, just again, going into a little bit more fun, we did the Grover's algorithm in the IDE. Now we're doing it in the Python SDK. All I'm doing is calling out my Grover model. Here's my expression. I have my variables A and B, and I'm giving A and B a register size of 4. I'm running that. Yeah, go for it. Mm-hmm. Mm-hmm. Did you, if you go ahead and click authenticate, it should give you a URL that you need to be running into. Yep. And if you're having any issues there, go ahead. You can authenticate using the IDE first. That'll simplify things as well. So yeah, we just created this quantum code. And a fun thing I always like to see is what the CHASM code looks like out of this. How many current lines of code would this have taken if I was doing it in assembly? Now, we just did that Grover's algorithm. It wasn't too long, maybe 5-6 lines of code. How big is this thing? Ooh, if it's going to load up for me. There we go. All right. Bit over 550 lines of code for, we have some preamble here, but this is all the CX, CU gates, Hadamard's, NOT gates, to actually go ahead and generate this OpenQASM 2.0 code. So, yeah, I don't know. Less than 10 lines of code to do that. And again, that's just the power of higher level modeling languages. It lets you do more in fewer lines of code. You can quickly start being a user of all this really cool quantum hardware that's getting developed, right? IonQ is scaling up, and they were talking about how do you scale up your quantum hardware, the need for scale up, but there's also the need for scaling up on the code side. How do you speed up your code development? How do you enable the new hardware that's coming out? How do you use that power and essentially make good on all the promises that quantum computing pertains, is set out to make? No, quantum promise that we've heard about is going to be on 10 qubits, right? We're not doing, weather analysis, drug discovery, portfolio optimization on 10 qubits, not even on 100 qubits, right? We're going to be using very large quantum circuits, very large quantum programs, and you need higher level modeling languages and coding to deliver that. And it also lets developers and industry more readily get into the field, right? They get intimidated when they see the lines of code, the amount of knowledge needed to go ahead and develop this, potentially the need to teach their developers 3 different assembly level languages, Q#, OpenQASM. It causes some worry, and be able to have a platform that you can dynamically switch between them to create code more quickly and pivot on your code, right? We didn't have to rewrite our code because we're pointing at a specific hardware or because we're changing a parameter. You can just go back to that same code set, switch out one of your optimizations, and re-optimize it for a different hardware set. Now, there's a bunch of notebooks that I was showing here that are kind of fun to go into. And you know what? I will take it from the crowd. Is there any that someone is quite interested in? I had some interesting code that shows some good time to solution calculations, which is always something that companies want to look at, right? We did a essentially Oracle generation and showing that as that scales up in the number of qubits and the size of your Oracle that you're solving out for, Classic's compiler compiles very nicely as that scales up compared to other kind of compilation codes. You know, do I have that? I do have that up, and I'll just, we'd have to generate it out. But in this notebook, you can just go ahead and click it. And I think it has one of the pre-generated graphs at the end of it. Yeah, there you go. Just showing that, you know, as the number of variables for your Oracle gets larger and larger, you do have some scaling issues, and it depends on the compiler you're using that's generating that code and how long it takes to receive that code at the end of the day. And if you actually want to see kind of the improvements from Classic, you need the improvements from Quantum, you need a compiler that can actually scale well. I don't know, what are some other ones? Yeah, so we also see, you know, improved efficiencies from quantum phase estimation and other algorithms, which also then plays into larger algorithms like, you know, computational fluid dynamics using HHL. Just because it was talked about so much in this workshop, I added in, during some of the other workshops and lectures, I added in a link to, you know, traveling salesman problems, doing QAOA. We use the package NumPy to go ahead and essentially create your nodal network map and compute that. But the Classic bit of the coding isn't very large to go ahead and just go execute on the optimization there, that QAOA algorithm. Let's see, what else was a fun one? Yep, the quantum machine learning too was a big topic during this event. I wanted to make sure we showed some of that. So if anybody's interested in doing, you know, because there was so much AI talk actually, we have quantum support vector machines, we have quantum neural networks, we have a number of notebooks, you know, showing things like, you know, generative adversarial networks and how to design those and analyze those in the platform. Yeah, I guess I just want to get a cue from anybody if there's questions from the audience on how to use Classic, the different applications we might enable in there. I do want to leave a little time before it is officially the 5:30 mark and we all start getting ready to go to our dinner. Questions from the crowd? You don't see Monte Carlo simulation. Ooh, yeah, that's a good question. I know we have it in the documentation. So if you go to, you know, if you're in the platform, you can go to user guide. And I know we have some Monte Carlo in here. Yep, there we go. Quantum Monte Carlo integration. So yeah, we don't have a GitHub one on that yet, but that's a good one to raise, and I'll tell the developers, you know, put a Python notebook up there. Yeah. Any other questions? Yeah.
You mentioned that Classic has the ability to compile to OpenQASM and since there are so many compatible devices, is it possible to transpile into across languages? Let's say I want to compile from Classic into Qiskit, and then I want to run the Qiskit in Classic.
Ooh. Yeah, to bring it back from Qiskit into Classic, we'll open up an OpenQASM file and let you run that code. But that's largely just the, you know, execution part of that, right? You lose out on the automated synthesis and the intelligence there. Because once you hard code in what you want to do in that imperative, you know, programming language, you can't fundamentally change the algorithm that you wanted to use. If you program hard-coded in a ripple carry adder, Classic can't backtrack that out and say, okay, take that ripple carry adder out and then replace it with the you know, QFT adder. So really the benefit from using Classic as far as the synthesis engine and that code efficiency is coding in from scratch using Classic, but you absolutely could just load in your code that you already have and just, you know, use some of the executions we have in there in the point and clicks. Yep. Yeah. Yep. What do you know? Oh, well, yeah, for simple addition, you don't, right? It's just showing some of the versatility and applicability of the higher level language, right? I like to do addition because it's a very simple problem to show. It's really easily understood and easy to see from a very far projector screen. And frankly, a lot of the problems that you start off with in these other platforms is some addition. How do you load in a probability mass function or a, you know, Bell state? How do you do addition on that? And showing the difference between what that looks like at the assembly level, that people have gone through that kind of initial process,
and what that looks like at a higher level, programming environment, gets people to start understanding the power of higher level languages. It's just more dynamic, nimble, and simpler, right? It should only take you 3 lines of code to do addition, not 20, right? If it's taking you 20 lines of code, that's hard to legitimize doing a huge project on, right? Especially when you start talking to these companies and their skunkworks teams, they only have so much time. A lot of companies are even figuring out, how do I allocate time, from existing groups? And, 20% of your time's on Quantum. Some don't have dedicated teams, and they really need to utilize that time as, much as possible. Yeah. Any other questions? Yep.
Just curious.
Mhm.
Part of our project, we do some quantum art. Because quantum computers are noisy, and sometimes you can explain the concept of randomness using visualization of the noise, or even making music from the quantum.
Yeah, no, definitely those sounds like some fun projects. I mean, even the quantum circuitry kind of looks like musical notes, right? If you're looking at it from the intermediate representation. So definitely I could see some fun projects. I've even seen some people make music from the assembly code itself. They brought some synthesizers with them on the trade show and were creating some music from quantum code. Shor's algorithm sounds wonky, but it's pretty cool. And actually, I realized I didn't answer your previous question about hybrid algorithms. And yes, like I showed you, traveling salesman problem, we have QAOA, which is a hybrid variational quantum algorithm. We're also integrated with NVIDIA's CUDA Quantum, which has a great kind of job manager for quantum and HPC infrastructure. So whether you're doing it on classical regular computers, or if you're doing it on larger supercomputers, we have the ability to do the hybrid algorithms. Yep. Very cool. Well, thank you all very much. I'm really glad that so many people stayed for the last bit of day here right before dinner. And I won't keep you. Enjoy. And I'll see you tomorrow if you're here.